conference, Nanotechnology and Nanomaterials, which take place in a very beautiful Ukrainian village. It's Bukovel, and it's part of Ukrainian Carpathian mountains. It's very great pleasure for me to welcome all you on this very important scientific event. And it is the biggest scientific conference in Ukraine, which we held last 12th year. This year, conference is organized in hybrid format, and we will have a live broadcast on our YouTube channel and our social network. This year, despite the war, we gather more than 600 application forms from scientists of different countries of the world. And it's a very pleasure for us that from year to year, our conference become bigger and bigger. And now I'm pleasant to give the floor to the representatives of Ministry of Education and Science of Ukraine, Directorate General of the Science and Innovation, and I invite Olena Makarenko to take the floor. Olena, are you with us?
Yes, dear colleagues, how can you hear me?
We can hear you well.
Thank you very much. Dear participants, esteemed colleagues, good morning. It is my great pleasure to welcome you to this important conference on behalf of the Ministry of Education and Science of Ukraine. And we are happy to see that this conference gathers so many scientists from different places today to work together across countries and develop science even in difficult times. I'm honored to convey the warmest greetings from the Ministry, and now, with your permission, I would like to read a letter of welcome on behalf of the Deputy Minister of Education and Science of Ukraine, Mr. Denis Kurbatov. Dear participants of the International Scientific and Practical Conference Nanotechnologies and Nanomaterials, on behalf of the Ministry of Education and Science of Ukraine, I would like to warmly welcome all participants and guests to the International Scientific and Practical Conference Nanotechnologies and Nanomaterials. This event has become a well-established tradition, annually bringing together researchers from leading academic institutions, not only in Ukraine, but also across Europe, East Asia and Middle East and North Africa. The range of scientists, as well as the breadth and depth of the scientific ideas proposed for discussion, confirm that nanotechnologies are among the most promising and innovative fields of modern science and technology. It opens up boundless opportunities for the development of many areas of life, from medicine and electronics to energy and material science. All conference participants have a unique opportunity to hear about the latest achievements, discuss challenges and prospects for development, and establish new contacts and cooperation. I am convinced that NANO-2025 will become a platform for the birth of new ideas, promote further progress in the field of nanotechnology, and make a significant contribution to the development of education, science, technology, and innovation in general. I would like to wish all participants fruitful work, engaging presentations, interesting discussions, and unforgettable impressions. May this conference be the beginning of new achievements and discoveries in the field of nanotechnology and nanomaterials. Wishing you good health, peace, prosperity, strength, and inspiration. Sincerely, Denis Kurbatov, Deputy Minister of Education and Science of Ukraine. Once again, from the Ministry of Education and Science of Ukraine, we wish you all a productive and inspiring conference. Thank you.
Thank you very much. And now we are moved to our next speaker. I kindly invite Maria Cristina Russo, representative of the European Commission, DG Research and Innovation. Dear Maria Cristina, please take your floor.
Thank you very much, and good morning to everybody from Brussels. I hope that you can hear me well. I am very happy to be with you again this year at the opening of the International Conference on Nanotechnologies and Nanomaterials. And I really would like to thank you for the invitation. I would like to thank the Deputy Minister for the addressive letter that he has conveyed to us for the opening of this important meeting. I also would like to say that this meeting today comes at a very important moment and recall that the European Union is strongly committed in supporting Ukraine against Russia's ongoing war of aggression. And we in the European Union stand firm with Ukraine to support a just, secure and lasting resolution of the war for a peaceful and prosperous Ukraine. In this respect, I would like to say that research and innovation is at the heart of Ukrainians' prosperity, and the European Union strongly supports Ukrainian scientific recovery. Research and innovation is the key for the reconstruction efforts, with the European Union's active involvement, and also research and innovation is the key for sustainable growth. I am very happy in this respect to highlight the key results and benefits stemming from Ukrainians' association to the Horizon Europe Research Framework Programme, which is, and I like to recall it, the largest multilateral research and innovation program of the world. In particular, let me give you some data. Horizon Europe supported 225 projects with over 61 million euro allocated for Ukrainian research partners. The Ukrainian participation fees were eliminated to address financial constraints. We published calls with mandatory Ukrainian participation amounting to over 20 million euros. We have funded through the Horizon Europe 35 million euro through Marie Skłodowska-Curie actions for fellowship to 170 displaced researchers, allowing to continue their work in Europe, with an additional 10 million euro announced under the Horizon 2025 Horizon Europe work program. With the Horizon Europe, we also supported the startups with 20 million euros from the European Innovation Council, and we initiated an innovation and investment agenda to enhance Ukrainians' technology infrastructure and innovation capacity. I would like to say all that in order really to show you the important results that we achieved in our cooperation. And also I would like to say that considering the key role of research and innovation for Ukraine and even the relations between the EU and Ukraine, the European Union has established a Horizon Europe office in Kiev to support participation and further integration of Ukraine in the European research area. We also have offered policy support to help Ukraine reform its research infrastructures, and also we supported the smart cities innovation with peer learning and twinning with our Horizon Europe missions. Now, thanks to these actions, the Ukrainians' participation in Horizon Europe has increased since the war. And I also would like to highlight two important announcements that our commissioner, the European Union Commissioner for Startups, Research and Innovation, Mrs. Harayeva, made at the Ukraine Recovery Conference 2025, which took place in July in Rome this year. First of all, the Commissioner has announced the launching of the International Coalition for Science, Research and Innovation in Ukraine to mobilize even more support and ensure more coordinated action in research and innovation. And secondly, the doubling of the Horizon Europe support to Ukrainian startups under the European Innovation Council. In particular, to the 20 million euros allocated to fund startups at a very early stage, the European Commission will add 20 additional million of euro, allowing to offer bigger tickets, 10 times larger, up to 500,000 per company, to help startups to scale, deploy, and attract more investment. Now, let me focus more specifically to the subject matter of this conference and highlight the strategic importance of nanotechnologies and nanomaterials. Advances in nanotechnology and nanomaterials enhance competitiveness, securing our economic future and also contributing to a sustainable, resource-efficient society. They play a crucial role in enabling the development of innovative products and processes, leading to new industries, promising to transform the manufacturing sector and creating new opportunities for growth and job creation. For that, the European Union has launched a dedicated strategy of advanced materials for industrial leadership, leading to setting priorities and supporting coordination for investments in this field. In this framework, we have established a Technology Council for Advanced Materials, and I would likely to warmly invite Ukraine to participate as an observer to the Strategic Committee, participation that can indeed happen due to the fact that Ukraine is associated to the Horizon Europe Research and Innovation Program. I would like to conclude my intervention by reaffirming the European Union's commitment to working together with Ukraine towards our common prosperity built on the foundation of cutting-edge research and innovation. I encourage all of you to make the best use of this conference to foster knowledge exchange, collaboration, and the formation of new partnerships in nanotechnologies and nanomaterials. I wish you a very nice day, and I would like to thank you for your attention.
Thank you very much, Maria Cristina Russo. And now we are moving to our next speaker. It's a very pleasure for me to invite academician Anatoly Zagorodny, President of National Academy of Science of Ukraine, to deliver his welcome address. Please, Anatoly, please take your floor.
Thank you. Dear colleagues, I have the great honor and pleasure to welcome the organizers and participants of the 13th International Conference Nanotechnologies and Nanomaterials on behalf of the National Academy of Sciences of Ukraine. This important international event was initiated by the Institute of Physics of our Academy more than 10 years ago. During this time, the conference has shown its effectiveness and has become very popular. And this is not by chance, since in our academy, research in the field of nanophysics and nanotechnologies is present in many of our institutes. In addition to the Institute of Physics mentioned above, these are the Kuryumov Institute for Metal Physics, the Lashkarev Institute of Semiconductor Physics, the Frantsevich Institute of Problems of Material Science, the Pisarjevsky Institute of Physical Chemistry, the Bogolyubov Institute for Theoretical Physics, Kyiv Academic University, and many others. The high international reputation of the conference is confirmed by the fact that the organizing committee of the current conference received more than 500 applications for participation in NANO-2025 from scientists and students from Ukraine and more than 10 countries of the world. Among them are our partners from Poland, Italy, Estonia, Algeria, China, France, the United Arab Emirates, and others. There is no doubt that this conference, like all previous ones, will contribute to the development of scientific research in the extremely important field of physics and material science, the popularization of science, the delivery of relevant information about promising technologies to representatives of the industrial sphere, as well as the involvement of students in promising scientific research. This conference is also very relevant because it concerns the development of a new field of contemporary science, quantum materials and quantum technologies. On behalf of the National Academy of Sciences of Ukraine, I would like to thank the organizers of the conference, including the Institute of Physics of the National Academy of Sciences of Ukraine, the University of Tartu, University of Turin, and the Pierre and Maria Curie University. I wish the participants of the conference successful work, interesting talks, fruitful discussions, and all the best. Thank you.
Hello. Thank you very much for very interesting welcome speech. And now we are moving to our best plenary session. And I maybe explain how we organize our plenary session. We will have invited speakers. After this, we will have common conference photo. And after the break, we will continue with several special sessions. And again, in the second part of the day, we will move to scientific sessions, such as nanocomposite and nanomaterials. And after this, we will continue our program next 3 days. In total, we will have 4 days of conference. And also, let me to remind you that all these days we will have live broadcast on our YouTube channel and social network. And this video records, so you will have opportunity to see this video in any time. As also I wanted to mention that as previous years after the conference, we gather scientific articles from our participants. And for example, previous years, we gather more than 800 scientific articles from participants of our previous conferences. And we had already published more than 12 Springer books in the physics area, and have published more than 25 special issues at international journals with high impact, such as Nanoscale Research Letter, Apply Nanoscience, European Physical Journal, Molecular Crystal, Liquid Crystal Journal, and others. And it's general information about our conference. And now we are moved to our plenary session. And it's I wanted to ask if we have our first speaker, Professor Mauro Fernandez Ferreira. Are you with us? Then we move to our next speaker, Professor Oksana Krupka. Oksana.
Yes, I'm here. I will just one moment because I think that I will be just after. So I will share my ecran in this moment. Yes. So I hope that you can see my screen.
Yes, everything is okay.
Yeah, okay.
But it is not in full screen. Oh, now it's good.
Yes, I just check my laser pointer. Be with you. So if you can see my pointer as well. Olena, if you can see my pointer as well.
Yes.
Okay,
We
perfect.
can see.
Good morning, participant, organizer of conference. For me, it is really very big pleasure to participate in conference Nano 2025.
Sorry, it's not full screen.
Pardon?
It's not full screen.
It's not full screen.
Mode.
Okay. it's full screen or not? Okay. If it's full screen.
Sorry, we can see your inside.
Okay,
part
I
of
understand.
the,
I will one more time do the same things because I had the
yes,
second
you should
ekran.
stop the sharing
Yes,
screen.
yes, I understand because I had second ekran and for that I have such effect. One moment, one more time I share my ekran. Probably it will be okay. If you can see my ekran, and now I will try to have full screen. If it's full screen in this moment.
Yes, now it's perfect. Yes, you can stop.
Okay, pointer in one moment.
Yes, pointer visible also.
Yeah. So what I would like to say is that in this moment we're not able to travel to Ukraine, unfortunately, because we not have permission from our institution, from University of Angers, but also from CNRS. And anyway, I will speak with you today about design of polyoxazoline-based drug delivery system in context of cancer treatment. So our laboratory of MINT, it's part of Angers University, but we localize in hospital near Center Cancerology. And as you can see from the name of our laboratory, Micro and Nanomedicine, this is laboratory of nanomedicine. We have around 40 researchers plus PhD students and postdocs from different fields. In general, it's pharmacist, physicochemist, and the third part, it's chemist. Me, I'm from third part of our laboratory, I'm chemist. And I'm looking in Wikipedia definition of nanomedicine. Nanomedicine is the medical application of nanotechnology, which can be realized in 4 domains, like diagnostic, therapy, monitoring and imaging, and regenerative medicine. If we speak about advantage of nanomedicine, of course, we can select a lot of different advantages, but one of the important one is delivering protection and solubilization. Today, during my talk, I will mostly focus on targeting in tumor cell, especially in the second part of my talk. So, and which mechanism of penetration usually we use in nanomedicine. It's one of the important mechanism of penetration, EPR, or enhanced permeability retention, due to high vascularity, especially cancer tissue. We can use such mechanism of penetration of drug delivery system. The second one, we can improve diffusion by charging positively nanocargo. And the third one is by lipid rearrangement. And if we look in different drug delivery system, it's not all present on this slide. We can divide on 2 parts, inorganic nanoparticles and organic nanoparticles. Inorganic nanoparticles, they have high stability, low biodegradability. If we now shift to organic nanoparticles, of course, if we use good biocompatible material, they will have good biocompatibility and multiply stability of drug functionalization, what is important for us as for chemists. And a lot of drug delivery systems, they need to be introduced with sales property, and this sales property can give polymer. And one of the useful polymer in pharmaceutical industry is polyethylene glycol. It's cheap and easy available, it's biocompatible polymer, and gold standard for drug delivery system. So, but few years ago, it was found that polyethylene glycol has some disadvantage, and you can see such disadvantage in red. And one of the important disadvantage, this one, generate an immune response of organism. So, such polymer can provoke autoimmune disease. For that, we're looking for alternative. And such alternative, you can see we present polyoxazoline. And polyoxazoline polymer, which biocompatible with cells property, cheap and easy available, and this is versatile polymer. But it's at the same time, by itself, it's thermosensitive polymer. It's thermosensitive polymer, but if we introduce pH-sensitive group or light-sensitive group, we will obtain multisensitive polymer. So it's not so bad as alternative. Chemistry of polyoxazoline give for us many opportunity, and in my group, we develop different drug delivery system, but of course we start from the simple multifunctional polyoxazoline as block copolymer, statistical copolymers, homopolymers with targeting moiety, and as well multifunctional POX star polymer. Today I will speak mostly about amphiphilic polyoxazoline. And what is this amphiphilicity? Amphiphilicity, when one part of polymer is hydrophobic and other hydrophilic, as you can see. And this gives for us possibility of auto-assembler, formulate auto-assembler structure as micelles, for example, and we also can formulate lipidic nanocapsules. In my team, also we develop plasmonic POX-coated gold nanostructure, and tomorrow you will have talk Pavlo Hort and Oles Fedotov. I invite you to join the conference of 2 PhD students. Such work done in collaboration with group of Oleg Yeshenko in Kyiv National Taras Shevchenko University. But I will not stop on this point. Today I will speak about lipidic nanocapsules and polymeric micelles. But what we can say about chemistry of polyoxazoline and properties of polyoxazoline, it's wonderful polymer. Why? Because you can easily change low critical solution temperature, which is quite important if we would like to use as drug delivery system. In drug delivery system, such polymer, we can change the completely properties from water soluble to non-water soluble. And we can tune low critical solution temperature, and even we can obtain precisely polymer with concretic low critical solution temperature by copolymerization of this polymer. So polyoxazoline can be obtained by cationic ring opening polymerization. As you can see, it's ideal platform. Why? First, we can control it. And this is one of the important things for chemists. We can control amphiphilicity, low critical solution temperature, dispersity, molecular weight, and during cationic ring opening polymerization of octazoline, we not observe side reaction. It's easy to functionalize. Why? Because first, in the etapal initiation, we use electrophile molecule, and we can in such way introduce moiety during a process of propagation, second process, and we can terminate. And usually we terminate with electrophile, and we can introduce in that way in alpha and omega position fragment, and even in side chain. And polyoxazoline can be used for aggregate and induced emission active micelle formulation. And for that, we need compounds which has such properties aggregated-induced emission. It is very known compounds, tetraphenyl ethylene, I will say TPE molecule, or in French TPE. So such compounds interesting for us in the way that in solution, they have free intramolecular rotation, and such compounds not emissive. We say not emissive, they have small emission, but it's negligible. So, but in aggregation, with restricted intramolecular rotation, it's very high emissive compounds. So, and we introduce such part as core of our micelles. This work was done together with Stefan. He worked with me as postdoc. And what we done with him, that first we synthesize hydroxy derivatives and by McMurray reaction, but in this etap we was not able to separate. But in the second etap after alkylation, we easily separate two isomers, Z and E isomer. Then after titillation, we obtain, we can say, pure isomer, Z and E isomer. So after we can continue our work and start polymerization. I show here just one example of polymer, which is our best one, I can say. Why? Because our aim was synthesize polymer with low critical solution temperature around 40 degrees. And for that, we need to have equivalent ratio which correspond and even the process of auto-assembler also we need to have some equilibrium between hydrophobic and hydrophilic parts. So you can see one block, it's block copolymer. This is one block, and this is the second block. But the second block consists statistical part, methyl polyoxazoline fragment, and propyl oxazoline fragment. And then we shift for formulation of the micelles. We formulate by micelles by thin film hydration method due to properties of our polymer, and especially that one part is hydrophobic, other hydrophilic. Due auto-assembler process, we able to obtain the micelles. Micelles which we can use for diagnostic, for therapy, and for drug delivery. Then we characterize our polymer, of course, and also characterize the micelles. We can see that the difference between micelles is evident. We start from a hydrodynamic diameter of the micelle, critical micelles concentration, and cloud point of polymer as well different. And if we compare two types of micelles, we observe the different critical micelles concentration during the formulation. For us, it was easy to determine such values due to aggregated induced emission behavior of TPE as core of these micelles. So then, of course, we go to the second step, and we would like to encapsulate NBDEX. What is it, NBDEX? It's anti-cancer drug with price quite important if we look for simple structure of this compound. So I say, Stefan, could you synthesize by yourself, because it's not easy to, it's not difficult to synthesize, and we synthesize by ourselves. Of course, we characterize, and then we use the other compound for encapsulation, DIL. This compound is very known for its thread pair for DID. It's a known thread pair, and we would like to see if we have Forester resonance energy transfer inside of our micelles between TPU fragment and diaryl molecule. So if you can see, this is part of TPU. If we excite in 320 nanometer, if we have Forrester energy, resonance energy transfer, we will observe emission of diaryl molecule in 580 nanometers. So what we done? As you can see, we excite two types of micelle, of course, separately, because we would like to see if encapsulation is in the same way for two types of micelles or not. We excite donor part. In our case, donor is TPU part. We excite in 320 nanometer. We observe Forrester energy transfer to acceptor, and we observe emission of diaryl. This is aggregated induced emission of TPU. We excite here where diaryl not have any absorption, and we observe, of course, emission, aggregated induced emission of TPU, because not all the molecule in the distance 10 nanometers or even less 10 nanometers. I speak now about acceptor part, and we also observe emission of diaryl. For us, it was question that we able to encapsulate in two type of micelles the diaryl molecule. Then we provoke collapse of micelles, and when we collapsed micelles and we excite in 320 nanometer, we not observe any emission of diaryl and any aggregated induced emission of TPU. So then we would like to see the efficiency and perspective of micelles and Z micelles loaded with NBDX against cervical cancer. And for that, we use HeLa cell lines, and we see that Z micelles and E micelle, they have different behavior. First question, if the micelles penetrate well in the cells, and for that, the next experiment was done. We check if in the cell line, we check emission of TPU, and we observe that in the case of a micelle, we can see clearly TPU emission. As well, for micelles, we see diaryl emission, and as well for micelles, we see FRET emission. For us, it was evident that we not have the same penetration mechanism for two type of micelles, and that micelles, they have different properties as physicochemical properties, as well during the formulation, we can see the difference in all etape, and penetration is not the same for two type of micelles. For us, it was important conclusion that it's quite important to separate isomers if we would like to use for nanomedicine. And the next part of my talk will be about lipidic nanocapsule for the release of drug. In our laboratory, it is quite known drug delivery system. It was firstly developed in our laboratory, in laboratory of MIN. And such drug delivery system can obtain by lower energy emulsification process. I will not stop on the details of this process. What we done? We would like to change important surfactant colifor on such a drug delivery system. We would like replace pegylated polymer, not polymer, but pegylated surfactant in such drug delivery system by oxylated surfactant, by POX. So for that, we synthesize two types of polymer. You can see quite simple polymer, amphiphilic polymer with cylinder chain. And the difference just here, we introduce imidazole part. Imidazole part is pH-sensitive part, and we would like to encapsulate photosynthesizer, of course, for photodynamic therapy. In my team, we develop a new method of synthesis of PDI photosynthesizer. It's quite new photosynthesizer, very efficient one. It is other talk about just photosynthesizer. So the mechanism treatment that combined light energy with medicine during the absorption through singlet excited state, PDI pass to triplet excited state, and then we have production of reactive oxygen species. By two mechanisms possible, type 1 or type 2. So, in type 2, we have a singlet oxygen. The both is very toxic for the cells, healthy cells and cancer cells as well. And for that, it's important to target exactly drug delivery system to cancer tissue and avoid targeting lipidic nanocapsule or drug delivery system to healthy one. So we encapsulate one of the photosynthesizer, which present on the slide, on lipidic nanocapsule. This work was done with Oksana. He worked with me as postdoc, and we, in collaboration with our colleague from Lviv Medical University, Solomia and Tatiana, it was a great pleasure to work together. So you can see the quantum yield of reactive oxygen species of generation. It's quite important in DTM. In PBS, we measure also quantum yield of reactive oxygen species generation. It's a little bit lower, but we not measure in such case ROS for photosynthesizer. We measure for all the system in PBS or also in water. It's not important. And you can see for comparison a non-photosynthesizer, which used in pharmacy. And we formulate lipidic nanocapsule. Morphology you can see on the slide and the quantum yield as well. And the quantum yield of ROS production. And then we test for two lines, for HeLa lines, cervical cancer, and melanoma lines. Then we see that the melanoma lines will be more useful for us, and we continue our investigation with melanoma line. So, in after treatment of cells with POX LNT, loaded and unloaded, also with imidazole part, without imidazole part, you can see. After illumination at 530 nanometer, it corresponds to absorption of photosynthesizer inside lipidic nanocapsules. We can see the results. So more important changes we observe for lipidic nanocapsules with imidazole on the surface charged with PDI1S. Also, we see such changes in the case if we not have imidazole. Here, diagram which summarizes the results. And then, for us, it was important to see if we have the same ROS production in the cells. For that, we perform confocal. And in confocal, we use fluorogenic reagent in green color. In green color, when we have production of ROS, it's like indicator of reactive oxygen species intermediate formation in cells. And blue, it's indicator, it's just, we would like to colorate the nucleus of the cells. And it's the same cell, thus the different excitation and emission wavelength. And it's clearly see as the ROS production for the cells, in the cells, if we have one SPDI loaded in POX LNC with imidazole fragment. It's the best result. Of course, we observe also for LNC without imidazole, but it was less important. Question one more time, if we have the same penetration in the cells, how we can answer on that? We need to do flow cytometry, and in such case, we use DID-DIE dyes as thread pair. You can see the absorption emission of two dyes. We need to excite in 488 nanometer, where we will not have any absorption of DID, and we will observe, if we have thread, of course, we will observe emission of DID. What we done? We encapsulate such two dyes in POX LNC with imidazole and without imidazole. We treated the cells of melanoma line, and after we compare here 4 hours and after 24 hours. After 4 hours, you can see that the difference is very important in intensity in thread medium, especially in 4 hours. This is for LNC intensity of thread for LNC without imidazole, and this one with imidazole fragment. Then in 24 hours, we still able to see the difference, but this difference is not so important than for 4 hours. So for us, it was answer that modification of surface of nanocargo, and in such case, we just introduce simple pH-sensitive group as imidazole, play key role for penetration. So, and as a conclusion, first, we formulate novel fluorescent polymeric micelles. We able to encapsulate active drug. Also, we able to see such micelles by fluorescence imaging, and we see the difference between Z and E micelles and the importance of two type of configuration. So we able to replace of polyethylene glycol in lipidic nanocapsules, and we show that lipidic nanocapsules can be promising nanocarrier for photosynthesizer, and this point not really investigated a lot. And also, lipidic nanocapsules has low dark toxicity, but high phototoxicity, of course, loaded with photosynthesizer. We investigate penetration, enhancement, and accumulation in cancer cells. I would like to thank all of our collaborators, of all my team and colleagues, and also the funding, and also you for your attention. Thank you so much. And I will be happy to answer to your question.
Okay, thank you very much for the good presentation. Do you have any question in our conference hall, or probably in Zoom? Still no question. Thank you very much, Oksana. If anybody will have questions, they can contact Oksana via email. And we will move forward to our next speaker, Dr. Volodymyr Lysenko, from the Institute of Light and Matter France. Dr. Volodymyr.
Yes, I'm here. Thank you for the introduction.
Okay, thank you very much. We are ready to see you. Please share your screen.
You see, I've sent my presentation via email. Could you please?
Okay, we can share it for you.
Yeah, please.
Okay, one moment. Okay. We can see your presentation. You can see it?
Sorry, it's not mine.
It's not yours?
Yeah, I've sent this morning. It's a PDF file.
Mm-hmm.
Yes, this is mine. Thank you.
Yes.
Yeah, thank you. Great. Okay. Thank you very much for the invitation to participate in this conference. It was a particular pleasure for me to take part in this very important event, scientific event of Ukraine. Today I will present some results related to our work concerning the studying of heat transfer in porous silicon liquid nanocomposites probed by Raman spectroscopy. This work was carried out in close collaboration between our Nanotechnology Institute of Lyon from France and Light Matter Institute, where I'm working. And my colleagues, Oksana Makucha and Ali Belarusi, are the members of the Nanotechnology Institute of Lyon. Okay, the next slide. Okay. First of all, let me shortly describe general context of this work. You see, silicon-based nanomaterials are already well known to be quite efficient thermal isolators, contrary to bulk crystalline silicon wafers, for example. And already several applications of silicon nanostructures in various microsystems have been already described in literature, starting from the beginning of 2000. On this slide, I would like just to give one example of this kind of applications of nanosilicon developed at industrial level by Seymour Group. As you can see, this company proposed an efficient thermal protection between lithium-ion battery units, and in particular, the nanosilicon composite thermal isolation sheet between the cells acts as a barrier, blocking the heat transfer to adjacent cells and preventing thermal runaway. This is quite original as for me application of nanoscale silicon for thermal isolation. And our research work is developed to study more heat transfer in nanoscale silicon structures and to see how these thermal properties can be tuned and in which way. Next slide, please. On this slide, I would like to present you a typical nanoscale morphology of porous silicon. Porous silicon nanostructures is a variant of nanoscale silicon, which is technologically compatible with classic silicon-based technologies and can be used for thermal isolation application, as I already mentioned. On this slide, you can see atomic force microscopy and scanning electronic microscopy pictures showing typical nanoscale morphology of porous silicon. A network of isolated and coalescent nanoscale pores can be clearly observed. agglomeration of silicon nanocrystals with typical sizes about 10 nanometers are localized around the nanopores. They are organized around the nanopores. Due to such nanoscale structure, porous silicon layers have high specific surface area. This is one of the important parameters which should be mentioned and defining the original properties of this kind of nanostructure. And this specific surface can reach several hundreds of meter square per gram of this nanomaterial. It's a quite huge value, and you will see after how it can be used for tuning of sample properties of this material. Next slide, please. Okay, now let me describe main morphological parameters of porosilicon samples which were used in our work. Different samples with porosity values ranging from 40 to 80% were used. You can see scanning electronic microscopy pictures of low porosity samples and high porosity samples. As you can see on these characteristic pictures, a columnar-like morphology of the nanopores networks can be remarked in both cases. The thicknesses of the layer, as mentioned in the table below, is about 100 micrometers. It was sufficient to perform this work, and from technology point of view, this is a characteristic layer thickness of the porous silicon layer. Sizes of silicon nanocrystallites constituting the porous layers are porosity dependent and decrease from about 12 to 8 nanometers with the increase in porosity. It can be easily understood. When we increase porosity, the sizes of silicon nanocrystals decrease. Next slide. In order to evaluate thermal properties of silicon, for example, thermal conductivity, Raman spectroscopy can be used. It's not a usual application of Raman spectroscopy, as maybe some of you knows, but I will describe. Now I will describe and explain how it works. The idea of this approach is schematically presented on this slide. Intensity of a laser beam used for Raman measurements can provoke a local heating of a silicon sample. Temperature level of the heated area depends on thermal conductivity of the studied silicon sample. The temperature value can be estimated from spectral position, as it's shown by the spectra on the right picture. Temperature level of the heated area depends on thermal conductivity of the studied sample. The temperature value can be estimated from spectral position of Raman peak, which is temperature dependent. This is very important. And the fitting of the laser-induced temperature with a model involving information about laser spot and optical properties of silicon allow to obtain thermal conductivity value of the studied samples. It's clear if thermal conductivity of silicon samples is relatively high, the temperature rise will be not so important. And in the opposite case, when thermal conductivity is low, with the smallest value of laser intensity, we can reach easily quite high temperature values. Next slide. Let me illustrate now how this measurements approach can be used for estimation of thermal conductivity of bulk silicon wafers. Being too high, about 150 watt per metric Kelvin, room temperature of bulk silicon cannot be measured because this value is quite high and approach the value for metals. No available intensity of lasers we have cannot provoke a shift of Raman peak. Thus, one has to hit a silicon substrate in order to decrease a little bit its thermal conductivity. In our experiment, silicon wafer was heated up to 640 degrees to move down the thermal conductivity of silicon substrates. As you can see, Raman peak position is linearly dependent on temperature of silicon substrate. Spectral shift of Raman peak toward low energies provoked by increasing laser intensity can be achieved, and this shift is defined only by thermal conductivity of the wafer. This is important. This thermal conductivity value were found to be about 55 watt per meter Kelvin, which is in good agreement with the known table value reported earlier. And for us, it was a test of our approach to show that the value which is already known, for example, for bulk silicon, can be easily estimated by Raman spectroscopy. Okay, next slide, please. The same measurement approach has been used to estimate thermal conductivity of porous silicon layer. Contrary to bulk silicon substrates, shape of Raman peak of porous silicon is slightly asymmetric. You can see a quite characteristic tail of the Lorentzian of the characterizing Raman peak of porous silicon about lower energy. Its spectral position is also defined by laser beam intensity. And the previously established calibration allows correlate the intensity-induced peak shift with local temperature rise. This dependence is perfectly linear, and its slope depends on thermal conductivity of the porous silicon sample. It means that for porous silicon, we can successfully use the same approach as for bulk silicon substrate as I've described before. Okay, next slide. Next slide, please. Could you? Okay, great. 3D finite element simulation of the local surface temperature of the porous silicon sample provoked by the laser heating allows to estimate precisely thermal conductivity of the porous layer. This is important. Thermal conductivity is proportional to the slope of the linear function between the temperature rise and the laser power absorbed by porous silicon sample, as you can see on this plot. It's interesting to note a significant and reproducible decrease of the slope after filling of a porous layer with a liquid, hexadecane in our case. Such decrease of the slope reflects an increase of thermal conductivity of the composite porous silicon liquid. Indeed, temperature rise go down, and it means that it's more difficult to hit porous silicon with pores filled with a liquid. It means that the thermal conductivity, global thermal conductivity of the composite was decreased. Okay, next slide. This slide summarizes thermal conductivity data obtained from the measurements described above. As you can see, thermal conductivity of the porous silicon with empty pores decreases monotonously with increasing porosity. This is normal porosity increase, portion of the air increase, thermal conductivity of porous silicon will decrease. Thermal conductivity value of the porous silicon hexadecane composite are systematically higher for all the porosity values. We see the same decrease, but this line is corresponds to higher thermal conductivity values. At the same time, the increase in ratio between thermal conductivities of porous silicon with liquid over thermal conductivities of porous silicon with empty pores as function of porosity reveals an increase of thermal transfer through the interface silicon liquid. Therefore, it was important to divide thermal conductivity values with filled pores over thermal conductivity values with empty pores to reflect increasing impact of heat transfer through interface, through the interface silicon liquid. Such kind of heat conduction is characterized in literature by interface thermal resistance. And in the both cases, we can remark that heat transfer take place through silicon nanoscale skeleton. But when the pores are filled with a liquid, a part of this heat will be transferred through the interface toward liquid. And the presence of the liquid allow us to reveal this effect. Next slide. Now, let me describe an impact of surface chemistry on the heat transfer in porous silicon liquid nanocomposite. First, to do that, porous silicon was chemically oxidized by nitric acid, and then chemically functionalized with different molecules using very well-known in chemistry silanization approach. As you can see, thermal conductivity of as-prepared porous silicon with empty pores and oxidized porous silicon with empty pores are almost the same. It corresponds to the blue columns, and we can see that thermal conductivity in the both cases almost the same. It means that in this situation, oxidation doesn't lead to any important increase of thermal conductivity. It means that heat transfer takes place through silicon skeleton, and no impact of oxide layer play a role in this process. Okay, at the same time, when the porous silicon layers are filled with hexadecane, this difference is much more pronounced, as you can see. This fact means a decrease of interface thermal resistance between the oxidized porous silicon and the liquid. In such a situation, hexadecane play a role of an agent, allowing us to reveal very important influence of interface thermal resistance in heat conduction mechanism. Okay, next slide. Now let's see what happens when a short molecule chlor-trimethylsilan TMS when it is attached to the oxide layer on the specific surface of porous silicon, what will be the impact of an additional surface functionalization with this molecule. Okay. In this case, formation of a TMS monolayer can be very easily controlled by FTIR spectroscopy with characteristic CH band around 3,000 inverse centimeters, as you can see on this spectrum. Only 5% of pores were filled with TMS. Only 5%. It means that monolayer doesn't impact the filling of the pore. As in the previous case, no difference of thermal conductivities in air can be stated, while a significant thermal conductivity increase was observed after filling of the pores with hexadecane. It means that the attachment of TMS on the porous silicon specific surface leads to an additional decrease of interface thermal resistance of the porous silicon hexadecane composite. It means that with oxide we achieved the first decrease effect of the thermal resistance, and now when we attach a molecule, this decrease is much more pronounced. Okay, next slide. Now, when the porous silicon surface is functionalized with APDMES it's another molecule which is a larger molecule in comparison with the previous TMS. The nanoporous filling reaches the value of 10%. It's twice in comparison with the filling of the pores by TMS. In this case, the difference between thermal conductivity in air, this difference will be already visible contrary to the previous case. This is because of the filling of the pores with APD-MES molecule. And when we fill again the pores with hexadecane, the difference start to be much more pronounced. As in the previous case, it characterized by significant decrease of interface thermal resistance value. Okay, next slide. Now let's see what will happen when we will attach to this porosilicon surface other molecules which are much more larger with quite significant carbon tails. And we will see the situation with two typical molecules, APTAS, aminopropyl 3-toxysilane and trichloroacetylsilane. In the both cases, chemical functionalization will take place on the previously oxidized porosilicon surface. Okay, next slide. The situation a little bit different because, especially for the case when the measurements are performed in air, I mean when the porosilicon is not filled with any liquid. And as you can see, in the both cases, thermal conductivity of porosilicon with empty pores increases after oxidation and after, especially after attachment of trichloroacetylsilane with porosilicon surface, because filling of the pores became really significant. And this effect is especially confirmed by APTAS functionalization. And you see on the columns APTAS 23, 60, and 73, this is the values of the filling factor of the pores. The more APTAS is present in the pores, the more will be thermal conductivity of porosilicon in air, because the pores are filled and this molecule play a role of a liquid, and we see a progressive decrease of thermal resistance of the interface. And the impact of hexadecane in this case will be lower, especially for APTAS, you see with significant pore filling factor, because the space leaving for hexadecane, remaining for hexadecane will be really very low, and the more important effect will be not already related to presence of liquid in the pores, but rather to functionalization of porosilicon with the molecule. This is very important conclusions. Okay, next slide. I will conclude my talk. It means that porosilicon is a really perfect nanostructured material for heat transfer studies. It's a perfect model which can be formed in a reproducible way. We can control everything: porosity, size distribution of silicon nanocrystalline, and we can fill the pores with different liquids and so on. And it's a good molecule. It's a good model to study evolution of interface thermal resistance in presence of different chemistry. And Raman spectroscopy can be used for heat transfer analysis in these kind of complex nanocomposites for estimation of local temperatures and local thermal conductivity values. It's a contactless approach. It allows us to understand and conclude on even on the mechanism of heat transfer taking part in our systems. Surface chemistry influences thermal transport through solid fluid interface. This is one of the important conclusions and corresponding to what is studying currently in literature, where various chemistry are attached to different solid states nanoscale materials, and the impact of the surface chemistry will observe to be play an important role in control of heat transport. And this knowledge is crucial for numerous applications. That's for sure in biomedical, energy, microsystems, and any other field. Okay, thank you for your attention. And I'm ready to answer the question if there are any.
Hello, everybody. Yes, everyone who wants to ask questions in the call, you can only hold your hand. The moment you have one question in the call.
Yes, I don't hear you.
One moment, I will bring the microphone for the participants who want to ask a question.
Yeah, thank you a lot.
So, did I need to present myself first of all? Okay, it doesn't. My question will be about in presentation you have slide about thermoconductivity of silicon compression with polysilicon.
Yes.
What's temperature on surface when you did your experiment?
Could you repeat please the question? I didn't understand well everything.
What is the temperature on the surface when you did your experiment?
Yes. This is yes. I will explain. It's a very nice question. You see, all the measurements performed on porous silicon was done at room temperature. But when we provoke temperature rise by laser beam, we control the temperature to don't exceed the value about 120 degree, more than room temperature. It means that in Kelvin we have about 390 degree. Okay, and but this is a local temperature. This is a local temperature, and the value of this temperature provoked by the laser does not exceed, because if the temperature will be very, very high, we will get an impact of temperature on the thermal conductivity, and we wanted to avoid it, of course.
So you tell that when you eliminate your surface with beam, it's about 100 to 200 degrees Celsius.
Yes, it's about 120 degrees more higher than room temperature. And this is the maximal temperature rise.
I don't remember exactly what it's the temperature to
Yes, no, yes, we have checked this impact. No impact of the temperature on his exadecane, because you see this temperature rise was very local. It's you see our laser spot diameter was about 1 micron, and this temperature rise was only in the area under the spot. It means that hemisphere radius was about 1 micron. Okay. And exadecane in the pores in the depths of 100 micrometers was not impacted by this laser beam.
Yes, thank you.
Thank you very much for this discussion. Do we have any more questions in our conference call? Or probably in Zoom. If anybody in Zoom can have a questions, you can or raise your hand, or just you have 1 or 2 minutes to do it. Okay, if we have no more questions, we will thank once again to Dr. Vladimir Lashenko, and we will move to our next speaker. Professor Mauro Fernandez Pereira is already joined us. Professor Mauro, can you start? I can see that Professor Moura is out in Zoom.
Oh, hi, can you hear
room,
me? I'm
but
trying to
can-
share the screen.
Yes, now we can hear you.
Yeah, you can hear me. I'm trying
Yes, we checked.
share. Okay, but I think you have to give me authorization because I don't see my screen when I click on share.
We already give you permission to share your
you
screen,
did,
so
you
you
did.
can click.
Yeah, okay. Right. Can you see? Wait. I authorized it. Okay, there we go. Can you see my screen?
Yes, now we can see your
All
screen.
right. Now you can see my screen. Very good. Thank you.
But we
Okay.
see our conference website.
You can see it, no?
We can see our conference website, not your presentation. Probably you should
Okay.
share another window.
I shared, but wait. Okay. Can you see it now?
No, you just scroll in the window of our conference website. Probably you should
Okay,
stop
let's-
sharing
wait,
and then
okay,
choose
let
the
me
right
close
window.
this. Okay. Let me close everything. Right. Not working. This one. Can you see it now?
One moment. Waiting. Yes, we can see it, but not in full screen mode.
Oh, do you see it now? Full screen mode?
Yes. Now we
Okay.
can see your another screen from the developer.
Okay, you see my presentation.
Your presentation, but like you should see it on your inside part.
Let me maybe turn my camera off. Wait. Oh, my video is off.
Previous one
Now
was
my video
better.
is on.
You can do it in not full screen mode. It was better because now it's like for phone, mobile phone,
Okay.
a small window.
Okay, let me try again. Sharing the screen. How about now?
Now we can see like developer mode. So your slide is very small in the left corner.
Okay, let me try again. Something else. Okay.
Oh,
The different
okay.
options. Because the system is not adapted to Zoom. It's only adapted for Teams, and sometimes Zoom gives me a problem. Okay.
Okay, this variant will be good. We can see it in quite good format.
Okay, can you see it now?
Yes.
Full screen?
No, when you jump to full screen, we always see the developer mode.
Okay,
So
how about
let's do
I
it.
increase it like this? Is it okay?
No, it's not. It's not. Now it's okay, but now you
Now
can
it's-
start.
Can you see it? Can I start?
Yes.
Okay, first of all, my apologies for all of this. I was having a hard time to connect and I had to use my mobile phone data. It's because of firewall complications. It's a pleasure to be with you here today. And I changed the title a little bit to add a bit more to the talk. So I'm going to talk about mid-infrared and terahertz devices. And we are a small team. It's myself, PhD student and my postdoc, and I have an external collaborator from my former institute where I'm emeritus. And we are a team of physicists and designers, and we design the materials and the devices that our colleagues somewhere else make. So I will start showing you an example of applications of mid-infrared technology to protecting the environment. I will talk a little bit about superlattice devices and how they apply to metabolomics. And then I'll show some of our photonic devices in the mid-infrared where we control light for specific applications. So if we look, for example, at water facilities, water storage, they are at risk because air and water are our two main resources. And sometimes our water reservoirs get polluted, either from terrorism or from simple accidents. And sometimes even the rain pollutes it because rain is acidic.
Dr. Mauro,
if
sorry
you-
to interrupt you, but your presentation worked slowly and the slides doesn't change. They change really particularly.
Do they
Probably,
change
did you send the presentation to us via email? Probably we can share
now?
it for
I
you.
did.
No,
I
you
can
didn't.
No, I didn't. I can do it. I can send it to you per email right now.
Okay. So what we will do, you will send us your presentation via mail, and we will start it from the beginner. And now we probably will give a floor for the next speaker, and we'll return to you in 10 minutes. Okay? Because now the
Okay,
presentation only now we
okay.
can see your second slide. It's a really big delay.
Sure. That's fine. Let me give it to you. Okay, I'm
Okay.
replying. Okay, go ahead. Go ahead.
Okay, now we will have some technical shift in our program. We will wait for Professor Mauro to send us the presentation. So now we kindly ask to take a floor Dr. Evgeny Yedisseyev from Francevich Institute of Problem of Material Science of NATO of Ukraine. Dr. Yedisseyev, can you hear us?
Yes, I can hear you.
So you are ready to start?
Yes.
Okay, please share your screen.
Can you see my presentation?
Yes, in full screen mode, so you can start.
Okay, thank you very much. I would like to thank the organizers for the great opportunity to present the results of our study devoted the ferroelectric nanorods in collaboration with Anna Morozovska from Institute of Physics and Dean Evans from Air Research Laboratory. Also, okay. Let me introduce the importance of our study. It is well known that lattice strain can induce remarkable changes of the ferroelectric and piezoelectric properties of ferroelectric materials. It is a powerful tool for enhancing performance of memory elements, energy conversion, and energy storage devices, so-called strain engineering. The curvature control of polarization distribution structure, the main structure morphology in ferroelectric sheets and became of significant interest due to the insight of strain gradient and curvature-induced changes of the ferroelectric long-range object dipole-dipole interrelation, the main wall structure and electronic properties. However, the possibility of strain gradient or curvature-induced changes in the main morphology of buried nanoparticles and nanosheets remained largely unexplored. Also, ferroelectric materials is highly sensitive to various kinds of strains. Let me describe a few words the methods of nanorods preparation. Barium T3 nanorods were synthesized using a single-step hydrothermal technique with different titanium sources, titanium oxide and titanium fluoride solutions, in different concentration of precursors of barium and oxygen. Different nanopowders were used. In this way, we obtained 4 different samples. Here, one can see it's their microscopy images, which allowed us to obtain the distribution functions of their sizes in all 3 directions. It is seen that most of the samples contain elongated nanorods of barium titanate. X-ray-D patterns of nanorods confirm their tetragonal structure. Not traces of impurities of secondary phases were observed. The splitting of some XRD reflections allows us to determine so-called tetragonality. It is the ratio of lattice constants C and A, which is found rather close to the bulk samples. Also, we performed high-resolution transverse electron microscopy studies. We obtained the images of barium T3 nanorods. Shows that here we have tetragonal structure. And also we determined internal strain independence of tetragonality, and it shows us some kind of correlation between them. Next, I would like to present the results of our modeling. Here we used so-called Landau-Ginzburg-Devonshire theory, which allows us to consider the distribution of polarization inside the nanoparticle cell. Also, we take into account the presence of internal so-called depolarization field and the coupling between the polarization and elastic strain. We propose the following model. We consider elongated porous shell nanorods with cubic shell, which is formed due to the presence of defects during the preparation of the nanorods. Here are the results of our modeling. We calculated tetragonality and the latest strains, it changes for the different misfit strain between the shell and the core and relative volume of the core. It is seen that there are different regions, namely paraelectric phase, PE, ferroelectric phase, FE, and there is also critical point where the second order phase transition is seen like the black circle, where the critical point where the second order phase transition transforms into the first order phase transition. Next, we consider the influence of the ferroelectric nanorods curvature in real ferroelectric nanorods, it's caused by the different concentration of the defects on the different surfaces of the rod or slab. So that we emulated this effect by supposing that there are some shear forces that causes the bending of the nanosheets, nanorods, ferroelectric. Here the results of calculation of the main structure of nanorods. We consider all three components and obtained their well-known classical picture of domain structure with closure domains. And we also calculated the distribution of internal strain caused by both flexoelectric coupling and electrostatic coupling between the polarization and strain. It is results for the mechanically free slabs without any internal external forces. Under the influence of the bending, drastically changes of the domain structure occurs. It is seen that presence of new type of domain structure, namely on one side of this nanorod, one can see the new domains, stripe domains, but in different direction, the compressed side of the shell core. But on the other side, where the stretching is observed, there are no, we observed no domains. This effect does depend on the curvature of the nanosheets. Here are some details of the, I would like to present some details of the polarization distribution. Namely, on one side, there are simple closure domains, but on the other surface, one can see the distribution of the stripe domains. This effect depends on the value of applied stress, or in other words, it is also determined by the curvature of the nanosheets. It is seen for the small forces, the upper row of this figure. The simple domain structure with closure domains, as one can see for the panel A. For the increase of the force, or the increase of the curvature, some of the closure domains on the other sides began to grow. And the first increase of the forces, stripe domain develops in the direction perpendicular to the developed axis of the nanorod. And the further increase, the domain structure changes completely. On the stretched part of the nanosheets, there are no closure domains at all, only the two C domains along the nanosheets axis. While on the other side of the nanosheets, there are stripe domains. Let me say about conclusions. It is confirmed that lattice strain depends directly on body oversaturation, with higher saturation resulting in increasing strains of body T3 nanorods synthesized under various conditions. However, strain does not directly influence crystal growth or lattice distortion. Instead, hydrogen ions incorporation can play a significant role in this process. This in turn affects both particle size and lattice distortion, leading to a tetrahedrality ratio about 1/30,000, 1/14,000. Oxygen ions induce lattice elongation along this axis, contributing to anisotropic growth, increasing of the rod diameter and their growth-induced bending. To explore the possibility of curvature-induced changes of barrier T3 nanorods domain morphology, we performed LGD Landau-Ginzburg-Devonshire theory-based analytical calculation and modeling, finite element modeling. This methods revealed the appearance of domain stripes and nanorods curved beyond a critical angle. This curvature controlled domain stripe formation may find application in flexible racetrack memories elements, flexotronics, and domain wall electronics. This work enhances understanding how the shape, anisotropy, lattice strains, and strain gradients can influence the domain formation for electric nanorods. Let me acknowledge the support of National Science Foundation of Ukraine, as well as European Office of Air Research and Development Foundation. Thank you very
much for interesting presentation. And now we open for questions. And if anyone has questions, yes.
Thank you for your talk. If I got your talk correctly, you described the effect of strain of your domain structure. Do you expect, in addition, some effect of pure curvature? I mean, something like existence of preferential direction for polarization vector regarding to the local normal of surface, something like this.
Sorry, I hear about the influence of curvature, but could not hear of on what influence. Please repeat your question.
Yeah. I mean, it might be possible that if you have a local curvature, that polarization vector would have some additional local anisotropy affected by the curvature or something like.
Yes, we considered all the three components of polarization vector, and one could say that we see its rotation. Curved nanorods is no longer is of tetragonal symmetries, rather close to the monoclinic one. So that additional anisotropy is also present here, to my mind.
Okay, thank you.
If we don't have any other questions, maybe in Zoom, then we can move to our next speaker. And I, with great pleasure, invite Dr. Roman Verba, who will share with us his presentation, nanoscale magnonic repeaters based on an online spin wave stability. He will represent Institute of Magnetism of the National Academy of Science of Ukraine.
Okay, thank you for kind introduction. Thanks to all the organizers for making this conference possible. My today's talk will be about different and not very common topic for this conference. It's about magnonics. And I'll present the results of our fruitful cooperation between Pleasant University, China, Innoven, Germany, University of Kaiserslautern, Germany, and University of Vienna. Okay, here a brief outline of my talk, and I will start with a standard introduction about wave-based computing and magnonics, and coming with our experimental result and explanation. What is the magnetic repeater and how it works. So all this talk is about computation and information processing, and you know the most popular, most common technique is the CMOS technology, silicon-based, and it has very nice features in terms of size, ultimate integration, very well developed, and it seems that for binary computing, while Boolean computing is the best technology available, and it's hard to believe that something could overcome it in terms of binary computing. But at the same time, we have many other needs in addition to simple binary computing. It is analog signal processing, a very popular current topic of neuromorphic system and artificial intelligence and quantum computing. And these systems could be somehow mapped into binary CMOS system, but this mapping is very far from being efficient, and sometimes is even impossible. That is why many people are searching for physical realization of analog system, neuromorphic system, and of quantum. So here we will be talking about analog and neuromorphic. Topic of quantum computing or other researchers. And the field of analog signal processing and neuromorphic computing, a very popular paradigm is the wave-based computing. When we code our signal not with electric current, with electric charge, voltage, but with the amplitude of phase of some wave. And this approach have many advantages, starting from infinite parallelism, which allows to realize some complex operation in a single one operation, and that increase effective speed of information processing and potentially low power consumption. And the left low corner shown one example of how wave physics can help us. It's an ideas of realization of a recurrent neural network mapped on the wave physics. You know that neural network requires many neurons to be combined each other, and this huge amount of connections is of course a big challenge for the physical realization of such networks. But it can be realized in terms of coupling between different waves, different modes in the reciprocal phase. And this is how it works. So instead of having many coupled neurons, people propose to launch the waves, certain frequencies, certain profiles, and change the landscape for this wave propagation. This landscape is work like a learning part of the neural network, and output with it located from after wave propagation. So it's just one simple example of how wave physics can help to process some kind of information or make some computational tests mass. Okay, which candidate for wave-based computing we have? Of course, we can use optical photons, we can use phonons, microwave mode, and which we could talk, I will talk here is spin waves. Each of these approach has their own advantages. But what I would like to highlight in Magnon, it's high nonlinearity, which is crucial for any narrow-mode class, and also high modulation speed, which can exceed the natural wave frequency. It is also very important for accessing many concepts of time-space crystals, time-space system, and so on. So we'll be talking about magnonics. Yeah. The field of magnonics has been developed almost 20 years, and it has been started from some very simple and naive devices like shown here, which is current controlled, simple interference-based devices. Of course, it was just a demonstration of proof of concepts, which are far beyond real applications. Next slide. Yeah. Now this field is rapidly developing, and many different subfields has been appeared, and just a few examples are shown here, and you can read this huge roadmap if you are interested in this topic. Next slide. For instance, many analog signal processing elements has been developed, like shown here, and some of them are hard to be realized in other systems, like this all-linear signal reversal with time-space concepts. Next slide. Also, many efforts has been made to develop all magnonic logic gates, where magnon signals is controlled by magnon itself. It is very important in terms of energy efficiency, because we don't need many other interconnection from spin waves to electric signals and backs, and it was, of course, lose any efficiency. And the first demonstration shown in the left slide, which was microscale, and now we have reached to nanoscale realization of some integrated elements of magnon logic, like integrating magnetic half adder. Next slide. And of course, a big step forward further development and towards potential real application was the development of inverse design algorithm, which is a numerical algorithm for designing elements on your demand, this functionality of your demand. It is something similar to how it works in CMOS, but it's also available in magnonics now. Next slide. But of course, if we want to combine, make some real large working system, we need to combine many different elements in a signal integrated circuits. And many problems arise. It is interconnection which is needed. It's launching the spin waves between different roads in 3-dimensional or 2-dimensional. It depends on how the system is designed, and a particular problems which we are talking Here is the compensation of losses and corrections of level. Here, this could be amplitude level or phase level, depending on how your system is designed. Next slide. And here you can see the sample and setup of our experimental part of our work. This is an yttrium iron garnet magnonic waveguide of 44 nanometer thickness, magnetized out of plane, and see two yellow microstrip antenna of different dimension, different sizes, which excite spin waves. Next slide. What is important for physics of our work is that spin waves and pump antenna and the microwave antenna exhibit a bit stability if we reach some nonlinear level of excitation. So depending on how we swap the frequency, we can reach higher amplitude or lower amplitude states. Next slide. Yeah, the physics is quite simple and is very similar to a fold-over effect in a simple nonlinear Diffin oscillator. Here, due to nonlinear frequency shift, we can sweep up the dispersion. This is a red nonlinear curve, and to higher values, and reach the situation when low K spin waves, which is ferromagnetic resonance spin waves, has our excitation frequency and match the excitation frequency. And this is this corresponds to high amplitude state. In contrast, if this nonlinearity doesn't happen, if we start from linear dispersion, the excitation frequency in the stable windows match some highway numbers, and it's simply inefficient to be excited by quite a large antenna. That is the physics of this stability. Next slide. And we want to switch between the states and play with it. How it can be done? It could be some thermal noise, it could be sweep of frequency, but of course sweep of frequency is not technological approach. And it could be triggered by some another additional signal. And this is exactly what I have here. So first we apply just a pump signal to the large antenna, and nothing happens. We see just a thermal background. Next slide. Some problems technical. Oh, it's problems with internet. Okay. Yeah. So when we apply a signal to another antenna which has a different structure, we see that spin waves are launched with certain amplitude and period as defined by the excitation pulse. Next slide. But if we applied both signal and pump simultaneously, we see a huge amplification of the spin 6 times. And next slide. If we apply this signal and pump at different period, we see that only spin waves are amplified only when both source and pump is applied. So the reason of amplification is, of course, the pump signal. Next slide. The output amplitude characteristic is shown here, and what is important is it is threshold light. Basically, above certain threshold, we have the normalized amplitude. So we not just simply amplify signal like it could be done by other means like parametric pumping. We also have the normalization of the output. And next slide. And it concerns not only in terms of amplitude, but also in terms of phases. Here is the lower amplitude waves on the right part are waves which are excited if only source is applied with different phases. And of course, different phase of source means the different phase of waves is launched. But if we apply both source and pump signal, all the output spin waves has well-defined phase. So we reach simultaneously normalization of the phase and normalization of the amplitude. Next slide. Yeah, and this is exactly what we expect from a repeater in terms if we use amplitude codon. So our device works as a magnetic repeater. Next slide. The physics of operation is quite simple. It is related to the nonlinear frequency shift of all the spin wave spectrum when another spin wave is applied. So when no spin waves is applied, or it is very low or has a low amplitude, our working point is within this stability window. But next slide. If input spin waves reach the threshold, it shifts the whole spin wave spectrum up, and which can be imagined like that the whole characteristics of the pump antenna simply shift to the higher frequency. And our working frequency appear in the single valued range where no stability, and we should switch to this higher amplitude state. That's how this device works. Next slide. Yeah, and with this, I would like to conclude. So in our device, we observe a large stability effect with the stability window exceeding 1 gigahertz. And I would like to underline that this becomes possible only in nanoscale waveguides. In some extended ferromagnetic films, people were able to reach no more than 10, 20 megahertz of stability, and nothing of these ideas can work. And having this stability, huge stability windows, we can switch easily between the low amplitude and high amplitude state and realize a functionality of magnetic repeater in magnetic waveguides and pumping with a microwave antenna. And the detail could be found in this paper mentioned at the last line. Thank you for attention, and the talk is open for questions.
Okay. Okay, do we have any question in our conference hall? Okay, probably in Zoom. Also, I invite every participants to write a question also in the chat during the talk, so we can already know does anyone have a question. So I cannot see question yet. Probably they will appear next later, so you will be able to do it during the lunch. But now we will move forward to our next speaker. And we received the message from the Professor Mauro Pereira that he already solves his problem with the presentation. So now we are able to give him one more chance.
Hello,
Professor
everybody.
Mauro?
Can you see the screen?
Yes, now we can see it in full screen mode. So probably now.
Okay. So can I start?
Yes.
Okay, thank you, everybody. I apologize for all this. So I'm going to talk about some of our devices in the mid-infrared and terahertz. Okay, and we are a team of theoretical physicists and designers, and we make our designs here, and some colleagues in other places make the device for us, and other people test them. So I would like to start with a very important problem. As you know, water is one of our most important resources. And together with a team in in two European Union projects, we have been analyzing water real time. So if any dangerous substance is dropped in the water, the best way to find it is to use the mid-infrared, because all these substances have very strong mid-infrared resonances, and they are very well, the signatures are very well defined. However, we have a very big problem. Water itself has a number of very strong resonances, and we have to somehow bypass this problem. We originally considered using just an evaporator, and then it turned out that for the main substance that we are trying to find in real time, which was ammonia, we couldn't do it. So our device, which was actually built by Mirsense in this European project, Aqua, and Odysseus, these two, this employs a splitter mechanism. So you separate the ammonia from the water, and then a quantum cascade laser excites the molecule, and a photoacoustic detector detects it. So we managed to detect ammonia in very small quantities, real time, by connecting to the water reservoir with this system. You see the box here. And we are now extending to a number of other substances. This is very important because in the past, this analysis has always been done by taking samples, sending to a laboratory, and coming back. But if there is a serious accident, by the time you do this, it is too late. The water already, the polluted water already reached people. So we are hoping that with our scheme, it would be much easier to detect and protect water everywhere in Europe and in the world. And this will be extended later to possibly detect remaining explosives in soil, which is unfortunately an important issue now to recover land that has been affected by war so that it can be used again. Right. So this is then made with a 9-micron quantum cascade laser and a photoacoustic detector. I'm going to cover also devices based on superlattices. So the quantum cascade laser itself is some kind of superlattice, a very complex one. But mostly when you talk about superlattice, semiconductor colleagues will think of deposits of, for example, gallium arsenide and aluminum arsenide. But if you are also working in photonics, a device like this, like ours, with a number of waveguides one after the other, is also called the superlattice. So I will be talking about those two types of superlattices here. For the semiconductor materials and devices, we will be looking into intersubband transitions, okay? The usual semiconductor device, like a laser diode or a pointer or a laser printer, will have an interband transition. And we look into transitions between the subbands. And these can be made as small as feasible so that we can reach frequencies in the terahertz and mid-infrared. So we designed the systems using one of our simulators. Here are examples of our different types of simulators. This is a terahertz laser. This is current voltage. This is a mid-infrared laser given in here, and we use the non-equilibrium Green's functions model. For the super lattices in the low terahertz range, we can't really use the quantum cascade lasers because the frequencies are mixed with phonon lines, which lose all the energy. So we use the nonlinear response, the nonlinear current that we induce in a superlattice. And this nonlinear process is completely different from, for example, Chi2, Chi3 types of nonlinearities. So this parameter here is proportional to the electric field, and you see that the maximum output is not for maximum field, it's for a precise combination of the applied gigahertz field and an applied voltage that we apply. So for other harmonics, we want to avoid external voltages. For even harmonics, we break the symmetry, applying a voltage, and we get a very high output, like here for the second harmonic. Right, so how do we calculate these things? Our non-equilibrium Green's function simulator doesn't work below 4 terahertz. So what we do, we take the structure, calculate the IV precisely, and find out these parameters here. Once we have them, we plug them into the Boltzmann equation, for which I have an exact analytical solution. And then I can go to the gigahertz range, and I can look into multiplications. So originally people only expected odd harmonics, but real superlattices have problems with the interfaces, and these problems break the antisymmetry of the IV. By breaking the antisymmetry, we can have also even harmonics. This is described by a rough interface. I have a self-energy for that. And the exact solutions that we have don't work for non-antisymmetric IV. So I have an ansatz solution. This was the original ansatz solution that I had a peak here, a peak there, and a turning point here and there, which I introduced by hand in the equations. And that explained very well the nonlinear output of the superlattices, third, fourth, fifth, sixth, seventh harmonic is here, and for different frequencies as well. However, there were some numerical complications with it, and we came up with the more involved path integral solution for the problem. Worked quite well, but it's very consuming in terms of time. You have to run the code for a very long time. Based on this, we looked at other solutions. I came up with a first solution for a better ansatz, and I could also explain asymmetric IV output that people detected, and they couldn't explain. They saw these things, this asymmetric curve, but their theory only explained it this symmetric way. So I could explain that. And we have another ansatz beyond this one here that allows us to eliminate all numerical problems and calculate curves all the way to harmonic 50. So it's very powerful and very fast. So with this, we can go and predict the nonlinearities in the superlattices, and these things have been measured. Okay, here you have two superlattices. One use the source in here, and the other uses this detector. And you see that we can make a theoretical prediction, and it's quite close to what our colleagues measured. So once we have this, we can also play with the interfaces and get those, for example, even harmonic nonlinearities enhanced without having to put too much voltage in it. Because there's a problem of putting voltage together with the gigahertz power because it breaks the sample. So we have a combination of breaking symmetry by either design or voltage or both of them together. So we have analyzed a number of possible device inputs, and we have maximized how to generate the harmonics that we wish to have, either with a SLED input, a BWO input, or with other types of inputs. We can maximize the system, and our colleagues can build the system and apply, for example, spectroscopy, like in here. Here in this kind of spectroscopy, we have colleagues, medical teams looking at people treated by cancer. Okay, and if you have chemotherapy applied to your body, you can ruin the kidney. By the time you can make a diagnostics 1 month after, it's too late. And our analysis of urine using the superlattices allows us to see changes in the liver, in the kidney due to chemotherapy 1 day after application of the medication. So we can change the medication and save the kidney of the patients. So we found a number of markers. We're studying this more, and we are currently looking also into prostate cancer. So I cannot show the results yet. Next year, I'll show them to you. Right, so this was mid-infrared terahertz. Now let's look into photonic devices. What we do is to imprint patterns with e-beam in silicon oxide waveguides. And with these patterns that we print in, we can induce functions on the light. For example, we can rotate light, we can split the light, we can make optical logic gates. And we were very successful in the near infrared. Our devices worked extremely well in the near infrared range. And then we are now taking our ideas and our technology and migrating to the mid infrared. So this is still the near infrared. You see those superlattices here work extremely well. And we have very broadband polarizers. Okay, we can sometimes you need only TE or TM light. This is a very efficient TE pass polarized, okay, based on these adiabatic S bands. We have compared and contrasted our technology with everything else in the literature, and in most cases, our technology is superior. So it's simpler, cheaper, and has better output and makes smaller devices using less power and losing less power than other devices in the literature. So what we are doing is quite okay. We have also made dense superlattices for the O band. They worked very well. The comparison between theory and experiments was very good. And we also managed to have superlattices with very little crosstalk between one channel and the other, allowing us to have different functions between the different channels. We have simulated and tested them experimentally, and they work quite well. So you see here that we managed to get very much what we want out of our simulations. There are many different ways of adding polarization and control to the system. We can have different devices. We have everything in one device. Okay. And this is, again, one of the examples compared to other people showing that we are doing better than the others. Our TM polarizers also work extremely well. This is our design here. And again, based on imprinting the form into the TE and the TM passes very strongly. We can also split the light extremely well with our devices, and this is all based on birefringence. So, of course, the birefringence does not work for all wavelengths. And when we go for the near infrared to the mid infrared, we have to change a number of things. But you see here that our TM polarizer worked extremely well. Okay, you kill the T and TM passes super strongly. And our TE polarizer is even better. So you see here, you simply rotate the light. This is extremely important because the main device for the mid-infrared is a quantum cascade laser, and the quantum cascade laser emits TM light. So this allows us to rotate the QCL light to TE and exploit a number of applications which really require TE polarization. So we are basically focusing on patents and commercialization. So we still have a number of things to publish. And after we send the patents, we'll be able to show this one. We have successfully submitted its patent, and then we published later. Okay, here's from our scientific reports. Most of our publications, I think all of them are open source. You can download everything. And you see here how our device looks. And this can also be used as logic gate. So you see here that our solutions give much smaller footprint than anybody else in the market, okay, which will open the path for quantum computations, which need very small devices so that quantum effects can take place. So we combine very small crosstalk with a small footprint, and also with very small power rejection. So this is our dense superlattice in the mid-infrared, which we are testing right now. I can show you the slides now because we already sent the patents. And we have a number of other devices being evaluated, and all going from near infrared to mid-infrared and further into the mid-infrared and next to terahertz. Things change as we go to longer wavelengths. And for much longer wavelengths than that, when you go to 10 microns range, we cannot use silicon oxide. And we have now new materials that we are testing, and should allow us to operate also in the 10 micron range. This operates well up to 3.6, 3.8 micron. After that, forget it. We cannot imprint the functions because we lose a number of properties, including the birefringency. So we can have a number of inputs, we can control them, and we can control each of these. This is an actual sample that we made. We do not make the samples here. We design them and we get them from foundries. And this is the actual sample, which is spectacular, made in Canada, in a very good foundry there. So in summary, what we do is to develop the theory to the limits, both for the quantum cascade laser sources and detectors and for the waveguides. And we have the samples made somewhere, and we apply them to the environment and medical physics. We expect to get even deeper into medical physics by translating our low sub-terahertz devices to the mid-infrared by looking at the resonances of the substances that we have detected in the near infrared. That will allow us to use our technology and our Mach-Zehnder interferometers to detect the substances the same way that we have been doing in the gigahertz and low terahertz range. So this is what I wanted to show. And if you have any questions, I will be happy to answer them.
Dear colleagues,
Okay, thank
maybe
you.
we have one moment. Maybe we'll have some question from conference call.
Yeah.
No, seems not.
Okay.
And thank you very much, Professor Mauro Fernandez. that you
I apologize for the
that
comment.
yes, that finally you contact with us and join us and present your interesting presentation. Yes, it's a scientific approach to go to the result, and I wish you in the future to be successful and continue very interesting research. And now we are moving to our next
Thank you very much.
Okay, and now we are moved to our next speaker. It's very great pleasure to invite for me Leonid Dolgov. And it's very pleasure that we started with Leonid Dolgov from the first conference to cooperate very close. And it seems that all 12 conferences he together with us, he always takes part in our conference and always present his research and very often he is moderator of our conference. So Leonid, are you with us?
Yes. Can you hear me?
Please, yes. We can hear you, and please pay attention that your presentation not in full screen mode.
Okay, just a moment. I try to do it in full screen now. So, how it looks now?
Now it's very good. So
Okay.
please take it on.
Okay. So thank you for introduction and possibility to make a report at this conference. So I am Leonid Dolgov. I work at the Institute of Physics, Tartu University. And today's talk will be about laser-induced periodic surface structures, about their formation and potential uses. And this work is made in collaboration with Ukrainian scientists. And I would like historically to say about this collaboration, how it started and what questions were interesting and still interesting in this sense. Saying about the laser-induced periodic surface structures, here you can see the first work, one of the first works in this topic, and the authors say about semiconductor surface damage produced by ruby lasers. You see that people say that damage, it means that something, when they invented it, something, first ideas was that it's undesirable effect, and they try to understand why it's happened, and probably in some applications, they want to avoid this effect. Therefore, they say about the damage. But you see that the damaged things can be reassembled again. And here I just put example of one Japanese technique when they use some broken pottery and then making glue with the gold, make a glue again this pottery, and it looks very nice and beautiful. And the idea that came to the mind that probably it's not only the damage, but this effect can be useful. And indeed, if we just look more precisely, you see that the structure is nanoscaled and periodic. It has period here maybe 1 micron or even maybe even more, even less than 1 micron. And so they have periodic nanostructure which appeared after laser treatment, and the people started to think why it's happened and how it can be reproduced. And in this sense, I would like to say about collaboration during which such questions arise for me. And it was collaboration with a group of Ivan Blonsky from the Institute of Physics, National Academy of Science of Ukraine, and such guys as Ruslan Kravchuk and Andriy Rybak actively participated in preparation of the structures, and discussions how the effects which they obtained can be explained. And they worked in the femtosecond lasers complex, which is still active in the Institute of Physics, National Academy of Science of Ukraine. It's based on the titanium sapphire laser. And the samples which they prepared, basically the simple idea was that they can just make some laser treated spots on the titanium sample, on the titanium plate, and they vary the time of treatment and see which structures were obtained under such femtosecond irradiation. And it was interesting that if we look on the optical microscopy of these structures, it was obtained some kind of ripples on the surface, and these ripples were parallel to the polarization of the laser beam. And the more time of treatment, the more ripples were on the surface, and finally, all this micron area of the surface was covered by the ripples. And if we look more precisely on the nanoscale of these ripples, you see that they have period also near 1 micron, and they look quite periodic. So the first question raised how the structures can be formed. And the very first ideas of this formation that the surface is not ideally polished. It's kind of like, it's not ideally flat, but there are some initial defects on the surface. And when the light beam comes to the surface, it scatters from these defects. And interference between the incident and scattered light can give some interference pattern. And this interference pattern is usually periodic, so it can give also picture of periodic ablation of material. When we have the maxima in the interference, the material is ablated more. In minima points, the material is ablated less. And by such a way, we can obtain the periodic structure with periods comparable with the wavelengths of exciting light. It was excitation near 1 micron, maybe 18 nanometers, so the same period we have. So it's a reasonable idea. But then we start to think how this, let's say, scattering wave can be. And when we analyze the literature, we see that people say about the surface wave, that the idea that the incident light excites some electrons because it's very powerful pulse, it gives some electron plasma excited, and it can be an interaction between the incident light and plasmon waves on the surface. But here is important thing that the plasmons usually need some wave vectors equality. It means that when we have the surface wave, plasmonic wave, it should be a sum of the wave vectors of the grating vector, which we have, because basically we organize the grating on the surface. So here M is the order of the diffraction from this grating, and D is the period of the grating. And also we have the projection of the wave vector incident for incident light. So basically we have three vectors. Vector of the surface wave Ks is the sum of the projection of the vector for incident light plus this wave vector for the grating. And these conditions should be satisfied. And this is working is in cases when the polarization of light is perpendicular to the ripples of the grating. So polarization should be such and ripples should be such. But in our case, it was situation, let's say, unusual for us, and the ripples are parallel to polarization, and we start to think how it is possible. So first of all, we analyze the surface with Raman spectroscopy, and we see that when we have the area with ripples, it's marked here the spectrum 2 corresponded Raman spectrum labeled by number 2, and first is untreated surface. You see that untreated surface is metallic, therefore it does not give any pronounced Raman bands, but for the spectrum 2 we have pronounced bands which we initially associated with oxidation, and when we try to see more exactly, we see that it's kind of like oxynitride of surface, because in the area, in the air, we have both oxygen and nitrogen, and both molecules can be chemically adsorbed on the surface. So it appears that probably in some areas of the surface we have metallic part, and some areas we have oxidation or nitrization of surface. Therefore, we have the ripples not perpendicular to the polarization of incident light, but parallel to it. And then we come to the nice idea that if really we have some plasmon effects which influence on the surface formation, that probably when we already have such formed nanostructure, it also has some plasmonic properties. And we try to obtain some kind of like plasmonic dips in reflection, because for plasmonic gratings, it's known basically for, if we consider gold grating or silver grating, if we excite it with the light and analyze the reflection, interference reflection from this grating, in some angles we will have some so-called wood anomalies. It will give some dips in the intensity, and it will testify and confirm that we have the plasmons in the structure. And we try to measure such angular dependencies for the incident and reflected light, and in reflected light we indeed see some fall, like not very sharp, but it's like decrease, and we just when we publish it, we associate it with the plasmons, but still we are thinking that titanium basically is not plasmonic metal, and for us it was a kind of like non-usual behavior. And then after some time, I just was switched to another problems, but after some years, I found very interesting collaboration. By the way, Elena Fesenko from the Institute of Physics helped to organize it, because we meet very interesting guy, Yaroslav Gnilitsky. He works in two organizations. One is Lviv Polytechnical National University, and another, he has a startup company, Novi Nano. And basically, the main business of his company is just they make nanostructuring of different surface using femtosecond laser. And they examine several materials. Yaroslav has experience of work in Italy in the same topics, and in Turkey in the same topics. So he defended thesis in this business. And what is interesting in his work, like it appeared that for plasmonic metals, like for gold, cuprum, aluminium, they obtained a less kind of like less ordered structures than for the non-plasmonic materials. And they make a kind of like more advanced technique, because they scan the laser spot along the surface. It means that you excite not only one spot on the surface, but you can scan the beam. Your beam are traveling along the surface. And if you make just traveling together with the pulse activity, you can basically nanostructure big areas, not only micrometers, but maybe centimeters, square centimeters of surface will be covered by the nanostructured periodic nanostructures. And they recognize they specifically adjusted regimes by such a way to obtain very uniform structures. And they obtain that uniformity of structures is good for the non-plasmonic metal like steel, titanium, molybdenum, but for the gold is less. And the reason it's like contradictory on the first glance, because you are thinking that if plasmonic plays a role there, then the more plasmons you have, the better result. But it appears that not, because in the gold and other plasmonic metals, you have longer plasmon lengths, like they're traveling longer distance. And because you initially excite the narrow spot, like small spot, and if the site of the spot is less than the traveling distance for plasmon, you, let's say, this periodic picture becomes spread and periodicity become lost because the plasmon are traveling too far. And therefore, they specifically found such materials for which these plasmons travel less. It means that the materials are less plasmonic, but still they have some electrons to interact. And by such a way, they achieved very nice uniform periodical structures on the square centimeters areas. And such approach is quite novel in a sense that it allows make wider surfaces with perfect nanostructures. And what is another kind of like reason, a mechanism which is essential for formation of such structures. When you have materials with a smaller refractive indices, usually such materials provide kind of like structurization in which the ripples are indeed parallel to the polarization of laser. But for that material, for those materials for which a refractive index is higher, it's possible to obtain the ripples which are perpendicular to polarization. So here, the local absorptions play more role than this interference scattering, because if to analyze it more precisely, like using this Seipp-Drude model, when you just solve the Maxwell equation and using dielectric permittivities and analyze permittivities for different states, when you just excite it with laser, you obtain the plasma. It appears that the more efficiency of absorption you have, the more beneficial formation of these ripples parallel to polarization of incident light. And finally, when they prepare these surfaces, which has already like centimeter squares of nice ordering, we just had a collaboration. They transferred to us the samples, and we tried to grow the living cells on these surfaces, because you know that if you have the rough surface, the living cells are like this rough surface because they can easily kind of like catch the surface and spread, grow, and proliferate more advancedly. And this effect can be used for the medical implants treatment. For example, if you have the medical implant, metal implant, which you need to incorporate into the bone or into the body, you need nice biocompatibility. So living cells should nicely accept this implant and grow around it. And indeed, when we try to make first experiments with osteoblast cells, with the bone cells, you see that in the left, it's untreated surface, and on the right, the cells are depicted on the laser-treated surface, and definitely we have more cells, they are proliferating more actively on this surface, and it is promising for the usage in medical application. So in conclusions, we can say that main origin of femtosecond laser-induced periodical structures is interference of incident wave with scattered or surface waves and related ablation of material. Orientation of laser-induced periodical surface structure depends on the local light absorption at the surface and its surface roughness. And these structures are suitable for growing of osteoblast cells, which can be promising for their usage in medical implants. So I thank you for your attention and waiting for your questions. Okay. I see that some question in the hall, but I don't hear. Maybe for some reason I don't hear. I don't know why. I will check my headphones. Now okay. Now I hear. Okay.
Okay. You said that the mechanism behind the surface structure is laser-induced ablation. Then could you please clarify how Polaron can smear your picture behind the laser spot? Does it mean that the energy of Polaron is so high to cause ablation too, or?
The idea, no. The idea that ablation, it's a kind of like joint effect. When you have incident light, it's just heated the surface, and it also gives energy to electrons, and these electrons come to the kind of like plasma-like state. In a sense that you have maybe 5 orders more concentration of electrons, and in terms of dielectric permittivity, it, for example, for titanium, if in the room conditions it has some -2, -1.5 epsilon for optical these frequencies, but under laser irradiation it can be like -10, -15. It's like orders jump in the permittivity, because you turn your metal to the basically to the plasma state near the surface. And altogether, this working several mechanisms. If you have femtosecond pulse, it's very short, then you already have preliminary competition between this kind of like interference mechanism dominates. But if you use nanosecond laser, then you also will have some hydrodynamics, because you have the melted material on the surface, and this melted material start to travel. And when you say about nanosecond pulses, it will also include some hydrodynamic mechanism. But in case of femtoseconds, since the times are too short, then this electromagnetic kind of like interference schemes are dominating. And indeed, these plasmons will give much energy.
Okay, thank you.
Any more questions? Okay.
Dear colleagues, do you have any additional question, maybe in Zoom? I will check chat. Not. It seems that it was last question to Leonid, and now we are moving to our last speaker. Not last, sorry. We have two speakers to the end, and the first one will be Professor Sergei Nedilko with a scientific report, luminescent marking of cellulose containing materials, approaches and application. It's very pleasure here on site. So we will have a presentation from conference hall.
Hello. Okay. Hello, dear colleagues. It's a pleasure for me to be here at this very important conference. And first, I'd like to thank the organizing committee and personally chairman of the conference, Elena, for the great work on preparing this set of conference, especially taking account the very difficult situation now. Thank you very much. There's the presentation. I see. I see. We will tell about luminescence marking of cellulose materials. Really, we deal with marking or labeling is the same in everyday life. When we mark our clothes, the bags for transportation, and so on. But when we deal with high technology, now this high technology is related with nanoscale materials, so we have to deal with a marker of associated size. What's the problem? Right? There must be molecule atoms and clusters or particles. When we want to see the mark on daylight or in the condition of low intensity of light in 10, we can use luminescent marker. I'm sorry. We go to the start. Right. I'd like to present as a co-author of my work. This is Viktor Borisyuk and Vitaly Cherny, also from Kyiv University, Taras Shevchenko. But Vitaly Cherny also present the National University of Light and Environmental Science of Ukraine. And Boyko also has position in this university, and Vadim Shelutko, he present the Alexander Dovzhenko National Pedagogical University. My presentation consists of four main parts. Why It's not good. Why we're dealing with cellulose materials, cellulose and its derivative have attracted considerable attention as materials for modern electronic devices, especially flexible electronic devices. This is a natural polymer, and it can be made from the plant. You can see on the slide the various scheme of preparation of the cellulose materials. This figure perfectly illustrates the origin and hierarchy of the structure of the cellulose form from trees, meter in the scale, and to the molecule in atoms and to the scale of 1 angstrom. There is a variety of cellulose materials application, as I noted before. This is a flexible electronic devices, also biocomposites, biomedicine, pharmaceutics, then this packaging and agriculture also. Somewhat about cellulose forms. You can see here the chain of the cellulose molecules. It consists of repeated units. It's the glucose, really. Glucose molecule. Cellulose nanomaterials can be divided into several nanoforms. In particular, there are cellulose nanofibers, cellulose nanocrystals, and microcrystalline cellulose. There are many pores in the structure of solid form of cellulose, of nanocellulose especially. Materials with any additive from molecules to particles. Yeah.
Dear colleagues, у мене немає. Dear colleagues, yes, we know that slides disappeared because we have that connection, internet connection. But now we will return back to you in 1 minute.
То відповідно звести добавки, це певне на якихось інших спеціальних матеріалів. І це вже це потім. Навіть це це проблема. Я це але між частинами із самої цієї на її технології є багато доцільних. І саме завдячу чому ми знали, досить таки покінчення клінічних зв'язок, не може бути спільно, тому які використовуються для матеріальних інших матеріалів, енергетичних. Це може бути конкуренти, матеріальні конкурси, це може бути конкуренції, які будуть виконувати переселі, це може бути ексцесії, нанопостійні, і патентні. Далі робота виконується і подивитися на нормальний
Так, екран до нас повернувся, тільки це не режим показу слайдів. Поки що. Хай хоча б так, да? Добре? Добре. Це про те, що я тут вже сказав. Так, є у нас на іноземців, так? The most commonly used luminescence marker are various systems such as organic dyes, metal ligand complexes like lithium lattice, semiconductor, carbon or silicon quantum dots, fluorophore targets, latex and silicon nanobits, luminescent organic and lanthanide doped inorganic nanoparticle, and so on. While the monomer and cellulosic are soluble in water, cellulose is remarkably recalcitrant to many solvents, including water. But the peculiarity of the cellulose-water interaction are important from the point of view of labeling, because they determine the behavior of the cellulose in water-soluble markers. Let's try to go to the next slide. Правда? А тут включено. Тут потрібно. Щоб не вийшло. Бобов. In its various form, the cellulose derivative also, and cellulose-containing materials are able to reveal visible on intrinsic luminescence without any additive. Here you can see the form of the spectra of luminescence and spectral excitation of the cellulose product produced from various origins from various plants, and also for bacterial cellulose. The main, it is very important that the male photoluminescence characteristics of various cellulose materials are quite similar. A point of issue confirms the possibility of utilizing the inherent luminescence of cellulose for tracking the response of cellulose-containing materials to external factors. Such a response allows considering the own materials has limited applicability due to the low peel intensity and dependence of the peel characteristic of various, sometimes uncontrolled factors. In order to overcome the drawback, different techniques and methods have been applied. Photooxidation is one of the simplest methods applied in order to increase the content of carbonyl, carboxyl, and hydroperoxide groups, aiming at improving cellulose-based materials. But obviously, I'll answer you on the 80 examples. Generally, the following strategy has been employed. First, one side. This is incorporating compounds with fluorescent properties into cellulose solution, coating luminescence molecules this some it's the next one. The next, please, and the next, please, and the next, please. Onto the surface of cellulose fiber, and grafting four molecules onto the cellulose fiber through chemical bonding. Before preparing the mixed solution, the most commonly used cellulose luminescence markers are various systems preparing with the method 3, chemical bonding. It is better to use cellulose derivative, for example, cellulose triacetate, cellulose terephthalate, and so on. You can see here the pattern of the films of the cellulose incorporated with luminescence markers, and also some of the optical characteristics. The use of cellulose esterification and carbonation methods allow for the improvement of the luminescence functionality of the cellulose. The various type of solution can be applied for the esterification. I will not tell the name of this compound on this abbreviative. This is the TBAF, DMSO, you know, and some other. And here you see the scheme of preparation of the cellulose, and also images of the prepared films, and also below you see the spectral characteristic absorption and luminescence. The cast films with an elastic model stress and strain were prepared. One more example of the luminescent marking is based on the dialdehyde cellulose and DPD fluorescence probe for detection of hydroxyl sulfide. It is known that abnormal concentration of hydroxyl sulfide may be an indicator on diseases of metabolic system, as this gas is one of the most important transmitters in the living organism. So the slide demonstrates the scheme of preparation of this luminescence marked cellulose molecule and the scheme of the registration of these changes in the property, and you see the images of prepared colored samples. And the limit of this gas detection was low than 1 micromole. One more. This is a schema used two luminescence marker in the same cellulose matrix for detection of volatile amine vapors. In this system, the FITS is indicator and PP9 is used as internal reference. You see the scheme of preparation of this market cellulose. You see the example of the sample colored, and this material is characterized by linear response to ammonia in wide range, and they provide a color responsive sensitive tool for amine detection. Various dyes can be used for marking the cellulose materials. You see this example of using fluorescein isocyanate. You see the scheme of preparation at the top, and also you see the scheme that demonstrates that the intensity of fluorescein luminescence is higher in free states, and it decreases when fluorescein moiety is attached to the cellulose molecule. This is at the bottom image. Rhodamine, you know, this very known luminescence materials. You see the patterns of the prepared cellulose materials. And the spectra of luminescence are the superposition of own luminescence of cellulose and also of rhodamine C luminescence. The same point concern another system. This is a bacteria cellulose incorporated with carotene. You know that the beta carotene is a precursor to vitamin A. It is an active antioxidant that neutralizes the effects of the free radicals. The dependence of the luminescence shape and intensity on the concentration of carotene has been measured, and it's possible to detect carotene on the background of other luminescence on the background of the cellulose. This result described show an interaction also between cellulose and carotene molecule. As you can see, the difference in the temperature dependencies of cellulose emission when it is free and when it is interact with carotene. Also, we can use as luminescence marker now. Перед ним. Okay. Can use the simple molecular inorganic anions groups as luminescent agent, owing to porous morphology of the cellulose in the solid state, as I have noted before. You know that a high level of nitrite or nitrate in living organisms may cause cancer and so on. But introduced the alkali metal nitrate to the cellulose. You see the result of spectroscopy measurement, and this compound revealed in pale spectra the series of narrow lines formed by radiation electron vibration transition from the excited to the ground states. Just observing narrow lines allowed to improve the lowest concentration limit of the nitrate determination in the water solution. And you see this value at the bottom of this slide. Unfortunately, this is also exotic example of the molecular inorganic anions luminescence, which exhibit narrow lines. Using inorganic compounds topped with rare earth ions, look through more perspective way for luminescent labeling. Here you see the data about luminescence study of cellulose matrix incorporated with potassium terbium phosphate. It shows very intense narrow lines, green PL, which can be effectively excited in the wide spectral range from vacuum, ultraviolet to visible light. Appropriate selection of excitation condition allow optimal luminescence labeling and visualization of cellulose materials incorporated with terbium-containing compounds. Moreover, such cellulose-based materials can be used as luminescence sensor, for example, for some toxic cases sensory. It's interesting example is the use of so-called long-living luminescence markings and the practical application. This long-living luminescent marking allowed to continue the emission up to the seconds or minutes or hours after interruption of the excitation. One of them is very known strontium calcium aluminate. You see the formula of this compound. We have prepared the set of the cellulose paper with this luminescence marking. This was made by Valery Barbash, Olga Yashchenko, and Polytechnic University in Kyiv. And you see the view of this paper on the sunlight, and after 10 minutes in dark room, here you see the dependence of the shape of luminescence on the concentration outside and the dependence of intensity. This depends. And so you see the decay curve of this luminescence that can continue up to 24 hours and more after excitation. And one more example of using this. Okay. One more example of using this luminescence marking. We prepared the suspension, what we do for suspension, and cover it by its leaves on the tree in the natural condition. And you see the set of the view of this leaves in 10 minutes, 12 hours, 240 hours, and 2 weeks. And separating the luminescence of leaves, this luminescence of cellulose, and some chlorophyll and carotenoids. When we separate it from the luminescence of this phosphor, we are able to found the dependence of luminescence intensity on time. You see this dependence. So this, I'd like to emphasize that described labeling can be used for remote monitoring of plant growth using modern digital technology like the Internet of Things. And some conclusions. Despite the fact that cellulose-containing materials are widely used in industry, in technology, and science, the luminescence mark is not very common. The characteristics of the cellulose cell luminescence are sensitive to the influence of water, alkali metal cations, which allow to speak about luminescence self-labeling cellulose materials. A specific example of the application of such type of marking for cellulose materials have been described with the use of the results obtained in various laboratories, including many of the results obtained by the author of the paper. Future research should be focused on improvement of luminescence performance, optimizing the stability of composite labeling systems, and expanding the application in biomedicine, agriculture, and here you can see the list of references that have been used in this presentation. Extending in detailed information as well as near 400 references about luminescence labeling mapping, including related to the some cellulose materials, can be found in our fresh web, luminescence marking of the cellulose-based materials, published in Exploration Biomathematics Journal, special issue, in August this year. Many thanks for your attention. Thanks to Nano Organizing Committee. Other thanks to Professor Valery Barbash, Olga Yashchenko for the preparation of nanocellulose suspension and composites, and also thanks for Katerina Krylenko, graduated University, for producing bacterial nanocellulose and composite state and experimental measurement provided for me and my colleagues at the Institute of Physics of the Polish Academy of Science, now during Russia war against Ukraine. Thank you.
And we have, thank you very much for interesting presentation, and sorry for some technical issue. We have alarm now, that's why the internet connection is not stable, but we try to do all our the best, and now you have seen that we finalized this presentation. And we have two questions to you. in chat. I will read this question. Did you try some micro or nano printing technologies to label not all the cellulose sample, but its certain areas, just to make fluorescence imaging? Do you label samples, demonstrate photo bleaching?
It is known disadvantages of organic luminescence marker is population after during action of the light of high power. But the way to contradict this, we now mainly engaged in inorganic nanoparticles luminescence marking. These oxide nanoparticles are very stable. The light, chemical impact, and so on.
And one more question. Please describe how dyes were incorporated into cellulose. What kind of cellulose was used and how cellulose samples were prepared?
In this case, we used very simple methods. We prepared the mixed solution of the water alcohol solution of dyes and water solution of cellulose. Then this mix was undergone to ultrasonic treatment and mixing for one time. And after
So if we will have additional question in the hall, we have? Yes, we have.
Okay, one more question.
Thank you for your presentation. May I repeat, did you try to combine some fluorophosphate dyes with metallic nanoparticles on your cellulose layer?
Thank you. It's very interesting, and really we try to incorporate the metal nanoparticles in cellulose materials, but I don't tell about very interesting results in these cases. We use the water solution, water suspension of argentum nitrate, argentum nitrite, and so on. Some of them you can see on one of the slides, this result. Figure where I presented the result of investigation nitrate incorporation in cellulose materials.
Thank you very much. As you could see that you have some compensation. Yes, you had some technical problem with presentation, but you have quite a lot question. Yes, you have 3 questions. And from Zoom, it means that everyone had the opportunity to listen to your presentation. And yes, and also you had question from conference hall. And now we are moving to our last presentation. And it's great pleasure for me to invite Professor Anna Mrozowska. We work together in one institute, Institute of Physics, National Academy of Science of Ukraine. And it's very great pleasure to invite Anna to make a presentation. It will be the last presentation in this plenary session. And the topic of presentation, the influence of flex of chemical strains on the emergence of popular hierarchical nanostructures. Please, Anna, take your floor.
Thank you very much, Elena. It's also a pleasure for me to work with you. Let me try to share my screen. Oh, yes. Okay. Is
Not
this
full screen
okay?
mode.
Mm. What means not
You
full
should
screen
probably
mode?
stop sharing, then start the full screen mode, and then choose the right windows for sharing.
I'm not sure that I can do this, Andrei, because in this case
Okay,
I cannot share. I cannot share. Yeah, I can try,
okay,
but I'm not
this is
sure.
quite big,
But I'm
so
not because okay, now I do that, but я не знаю, как это получится.
Ми бачимо, в принципі, в досить великому розмірі всі слайди, так що не страшно, якщо не повний.
Ну, вот перешла. И что мне, как мне теперь расшарить?
Тихо. Где зум?
Вот.
Вот это?
Вот зум, вот ты на нем.
Теперь share нажимай. Вот этот вот. Выбирай share.
And now. Is now you can see it in full screen?
Yes, mode on. Yes,
I am very grateful for thanks to my colleagues. Okay, let me present this talk. This is talk from a group of co-authors from the Institute of Physics, from the Francevich Institute for Problems of Material Science, from the Strasbourg University, France, and from the USA Air Force Research Laboratory. This is a review talk about the influence of the flexochemical strains on the emergence of polar chiral nanostructures in ferroelectrics. Since it's a very specific topic, let me first of all to introduce what is flexo effect, because what is chemical strains, I hope that everybody in this conference know. The flexoelectricity is a universal phenomenon, very strong in the nanoscale and almost elusive in macroscale. Direct flexoelectric effect describes the appearance of the electric polarization in response to the strain or stress gradient. The inverse flexoelectric effect describes the appearance of strain or respectively stress in response to electric polarization. During last 20 years, we study this phenomena in nanoscale ferroelectrics using Landau-Ginzburg-Devonshire approach. And several words about modern problems in ferroelectricity. Despite the basic principles of their theoretical description at the nanoscale was well established decades ago, some physical mechanism ruling their polar properties and topological states remained a challenge for fundamental research, similarly to the ferromagnets. Their properties at the same time hold significant potential for a broad spectrum of advanced applications, such as innovative storage, low and high frequency optics, innovation information storage. And also let me read that their structures may involve nanoscale modulation of their electric polarization, which is important for the flexoelectricity. And this modulation remains stable in the absence of applied electric field. Then you can apply a localized electric field above some definite coercive value. And this field is required to switch the polarization between the two or several metastable states, allowing the control of domain structure, its direction, and the main thing for this talk, topology, morphology, chirality, quantities related not only to the direction, but to the structure of the carving. And for the non-destructive visualization of the written by electric field structure, you require much lower fields than the coercive values. This is important because coercive fields are relatively high for ferroelectrics. And this is their drawbacks in comparison with ferromagnets. But on the other hand, the advantage is that there's structures, both topological and simple domain structures, can be very fine. So the information density in ferroelectrics can be much higher in ferromagnets. We have gain in information density, but we have disadvantage in the speed of writing. That is why non-destructive reading by small fields seems very important. And now to the questions of my talk. You can see a classical example of ferroelectric nanocylinders made of multi-axial ferroelectric barium titanate, and we subject it to two physical mechanisms, flexoelectric coupling and electrostriction coupling. And when both coupling are absent, this is the left figure, you have a simple dipolar kernel in the structure. When you switch on the flexoelectricity and the electrostriction, you can see so-called flexons. Flexons look like chiral bobbers, like user bobbers at the water. You can see here. But the direction of curling in these flexons of the polarization vector is determined by the sign of the flexoelectric coefficient. When the flexoelectric effect is absent, flexon is absent too. Next example is flexosensitive polarization vortices in ferroelectric thin film. This we have rather close similarity to the vortex-antivortex pairs in the ferromagnets. But in distinct to ferromagnets, here the flexoelectricity changes the topology of these vortex-antivortex pairs in a very specific way. As you can see here at the plot D, when the flexoelectric coupling is absent, we have a symmetric picture, polarization up and polarization down. When you switch on the flexoelectricity, you see that the polarization curves becomes asymmetric. And again, their slope and shape is dependent on the sign of the flexoelectric coefficient. The specialists which characterize their structures by so-called topological indexes, integral invariant, also see the difference between the red and blue curves, which corresponds to the inverse signs of the flexoelectric coupling. The curves are also inverted. Next examples are core shell ferroelectric nanoparticles, where you can distinguish soft, elastically soft shells and elastically hard shells. And you can see that under the absence of flexoelectricity, this is the top row, figure B. You see no specific topological structures, block structures, easing lines, or block points. The structures means the point where the polarization is zero. Again, this terminology comes to the ferroelectricity from the ferromagnetism. But in the case when you switch on the electrostriction coupling, you can see an Ising line. When you switch on also the flexoelectric, both flexoelectric and electrostriction, this Ising lines transforms into the two block. And situation in the particles placed or covered by a hard core is vice versa. Without flexoelectricity, you see Ising line. With flexoelectricity, you see central block points, which are dependent on the core deformation, and also the field is determined by the electrostriction coupling. I forget to say that all the three examples which I show is a barium titanate, classical ferroelectric, known for more than 15 years, but in the shape of nanocylinders or nanoparticles. And now some part of recent original results. Let us imagine that we have a spherical nanoparticle made of uniaxial ferroelectric space, stannum, plumbum, and sulfur, and you applied the step-like electric voltage to this nanoparticle placed in incapacitor and applied this field. And we model the behavior of polarization. Under the absence of flexoelectric coupling, this is the top row, you can see that the random state of polarization gradually transfers into the maze, or Lagrangian domain structure. Then, when the field increases, we polarize this maze into a unipolar structure. Then we apply a negative field, and this maze reappear again polarize, again reappear, but you see this two images, image 5 and image 3, have inverse polarity. So the final state in this case, depends on the history, on the polarity of applied voltage. This also can be used, in our opinion, for information storage. When we switch on the flexoelectric coupling in the same other conditions, you can see that the random seeding transforms into the spiral-like structures. And the polarity of their spiral-like structures after switching on and off of the applied bias is determined by the flexoelectric coefficient rather than by the history of the bias. So in this case, flexoelectric coupling counteracts some sort of memory by the bias. Is this good or bad? I do not know, but this is a fact. More precisely, the situation is illustrated in these cross sections. The top rows show chiral structures in the equatorial cross section of the particle, and you can see that when the flexoelectric coupling is absent, top figure A, you see the maze in the cross sections and random lines in the polar section in the direction of polarization. Then, when we switch on the flexoelectric coupling and increase its relative strength from 1, say, to 3 in arbitrary units, you can see that this maze gradually transforms to the spirals or more chiral structures. The situation in the polar cross sections looks less pronounced. Here, the period of the stripes changes. Also, this figure illustrates what changes when we change the size of the particle. For small particles, we have a maze, and this maze gradually disappears when we increase the coupling. The same we can see in the polar section where the period of the stripes increases. So you have two factors: the size of the particle and the strength of the flexoelectric coupling. And by using these two factors, you can control the morphology of the domain structure inside the core shell nanoparticles. Next example is more close to the applications. And here we have, again, barium titanate nanosilicate placed between strontium titanate layers, and all the system is placed in the plane capacitor. This geometry is for the observation and usage of the so-called negative capacitance effect, which is when you use some magic layer, say ferroelectric layer, the total capacitance of the system placed in series increases. And here, the mechanism of the negative capacitance appearance is demonstrated. When you see a pure strontium titanate, you have parabolic well. When you have pure barium titanate, you have double well potential inherent to the ferroelectric, first order ferroelectric. And when you have this heterostructure, strontium titanate, barium titanate, you have the situation with the so-called flat wells. And in the region of flat wells, you can see negative capacitance regions and how to control this region. You can control this region by the help of effective strain, which can be, in this case, either mismatched at the boundaries of the barium titanate, strontium titanate, or flexochemical strain, some sorts of defects. Also, we observe flexons in this system, in the similarity which I showed you earlier for barium titanate, and the direction of these flexons is governed by the strength, by the positive or negative of the flexoelectric couple. Similar from the physical point of view situation is observed in the van der Waals ferroelectric cuprum indium P2S6. When we place a nanoflake in the capacitor geometry and study its domain structure in relation to the flexoelectric coupling, you can see then when the flexoelectric coupling is absent, you have some irregular domain structure. This is the middle image C in this slide. When you switch negative or positive flexoelectric coupling, the masses disappear and you have some domain spots. Also, as you can see at the bottom of this slide, in this case, the situation with the flat wells is very pronounced. These van der Waals materials now are regarded one of the best for the negative capacitance devices. And also independence on the chemical activity of the ionic defects, placed here on the top layer, you can govern the appearance and the strength of the negative capacitance region. This bottom diagram shows this effect. Independence on effective strain and activity, you can make this dark violet region of negative capacitance wider or thinner. This is quite important because it is difficult even to predict the appearance of negative capacitance in the ferroelectric heterostructures. And despite the theoretical predictions can be rather far from the experiments, at least it gives us an order of magnitude. Nanoflake thickness, the strength of flexocoupling, the concentration of ionic defects, and so on and so on, to predict that yes, in this region, experimentator may expect the negative capacitance. The origin of this effect is illustrated here. This is the cross-section of this cylindrical nanoflakes. And you can see that the flexoelectricity where the strain governs the domain structure. You can compare the maps of polarization, the top row, with the maps of strain. And you can see that the domain walls corresponds to the lines at the strain maps. This is one cross-section, and this is another cross-section and another components of the strain. Since we're out of our schedule, let me announce briefly the conclusion to my talk. To summarize, we state that the flexoelectric effect significantly affects the polarization structures in thin films and core shell nanoparticles in multi-axial ferroelectric. It leads to the noticeable carving of the flux flow domain walls in their structures and generated three-dimensional vortex in corresponding structures. Under certain conditions, flexoelectric polarization vortices can be formed. Moreover, anisotropic flexoelectric effects give rise to Miron-type polarization states, which we named flexons. In core shell nanoparticles of uniaxial ferroelectric, the flexoelectric coupling can control the polarity and chirality of equilibrium polar structures. And we observe a gradual transition of labyrinthine domains from branch to spiral morphology with increasing of the flexocoupling strength. Well, and also the combined action of the flexoelectric effects, electrostriction coupling, lattice and mismatch strains significantly influence the polar properties, phase diagram, Curie temperature, domain morphology, and chirality of ferroelectric nanoparticles. Applications of the flexosensitive polar structures in the nanoscale ferroelectrics hold significant promise for nanoelectronics and catalysis. For instance, it appears that multiply degenerated labyrinthine domain states may correspond to the negative capacitance states stabilized in the ferroelectric heterostructures. The flexoelectricity control their structures, and it is possible in many types of nanoparticles, being useful for applications in advanced cryptology. And also, I would like to maybe last remark that the paraelectric state of lead wells in van der Waals ferroelectric covered by ionic electronic screening charge reveals a very pronounced negative capacitance effect in accordance with our theoretical predictions. Let me thank our funding energy, National Research Foundation of Ukraine, and many thanks to your attention. Deepest gratitude to wonderful organizers of this conference. And last remark, this is our topical review where you can read the content of my talk in details. Thank you very much. Maybe you have some questions.
Thank you, Anna, for interesting presentation. And now we have two questions to you. The first one will be from conference hall. One moment.
Thank you for your presentation. I have a question about how replicable are this labyrinthine structure from time to time?
Thank you for your question. This is numerical modeling. It depends on the initial seeding. When you change the seeding, you obtain another maze, but the period of these mazes and their overall characteristics, such as topological, are independent on the seeding. If you have the question regarding experiments, in experiments, the maze structure are determined by the defects, of course.
Okay, thank you very much.
And we have one more question from the Zoom, as I understand.
Yes, I have seen the hand in Zoom. It's Anatoly Evtuch, correctly. Please take your floor.
Yes. The question is like this. Did you estimate the dynamic of the polarization changing and how it depends on the size nanoparticle?
Yes, thank you. We make this during every finite element run because we start from the seeding and end with the relaxed distribution of polarization. The dynamic is determined by the so-called Landau-Khalatnikov relaxation time, internal characteristic of ferroelectric. It is also weakly dependent, in my experience, on the size of nanoparticles because this relaxation time is an intrinsic characteristics of ferroelectric. But again, if you include the defects which are present in real materials, the dynamics of polarization is determined by the creeping of domain walls as defects.
Thank you.
Thank you.
Now we will check. Maybe you have additional question in Zoom. No, it seems no. So it's a great pleasure to me to close a plenary session. And now we will have a common photo on site. Sorry, our Zoom participants only can't to join to us for common photo, but I'm sure that next time you will have opportunity to join us on site. So now I invite everyone to scene. Так? На сцені будемо робити. On the stand, and after this we will have also another location. So thank you very much to everyone who was with us in Zoom. We will have a break now, and we will start our job at 2 p.m. Now we have a coffee break. See you soon.
Раз.
Чути вас.
Dear colleagues, we are happy to continue our conference, and now we move to our next session. It will be a special session, boosting commercialization of materials science and innovation for knowledge-based communities in Danube region. This session will be supported by RTIT project. And we will have only 3 speakers for this session. And it's a very pleasure for me to share with you main information about this project. Materials as a cross-session technology are of central importance in the digital and green transformation. Materials and materials technology are a key asset in time of geopolitical instability and represent a highly dynamic sectors with technology challenges and high innovation potential, such as sustainable, smart, and responsible materials, advanced composite, surface engineering, light weighting, and energical optimized materials. The Danube region is strong in the production and manufacturing of materials and a key region within EU. To reduce the dependence on markets outside the European continents, the Danube region countries S3 strategies reflect that ambition clear. However, the technological challenges, the growing needs for sustainability and resilience demand of much higher level of research, technology, and innovation, RTI. But for a more effective RTI transfer to the business community in order not only remain competitive, but improve their composition as key player in European value chains. Yet innovation support system, as well as RTI management and valuation policy struggle with finding the right strategies and measure the narrow the gap to European innovation leaders and master the upcoming challenges. RTIT institution at this moment not enough cooperate with the business support organization. The lack of sustainability long-term relationship and cooperation with actors from well-functioning RTI support system prevent access to prospective RTI project. Administrative fragmentation, lack of human resources, and finding in RTIT transfer system make the challenge with EU innovation levels even harder. The transnational cooperation with innovation leaders helps finding the right strategy and approaches to fasten the catching up process in RTIT transfer and narrow the gap between East and West. Through experience and knowledge sharing from highly innovative regions to moderate and emerging innovators countries, the less developed regions are supported in the introduction of new approaches. The RTI consortium, RTI, it's the title of Danube region infrastructure project, will develop and uptake the transformation action plan to accelerate RTIT transfer in the field of materials and materials technologies in the Danube region, that is based on the new industrial strategy for Europe 2020, detailing policy measures and actions for decision make in academia and business support infrastructure, focusing on capitalization the region strengths and advantages and delivering new know-how to the region on RTIT transfer, design management, and know-how communities. All 11 territorial and countries demonstration partner will take the 3 sets of tools development, field tested and validate through an innovative hosting approach, focusing on the 3 components of the RTIT transfer: the transfer itself, design management, and know-how communities. So it will be 3 different instruments. It is RTIT objective to strengthen the innovation potential of SMEs in the field of material technologies by improving the collaboration of SMEs with RTIT partners and creating a respective network. We will build up know-how communities, introduce a new RTIT to markets, as well as a market pool of RTIT mechanism, and support SMEs in the commercialization RTI through design management. By creating better framework condition and structure for RTIT transfer in the key technology areas such as material and material technologies. RTIT contributes to resource efficiency, sustainability, and digitalization, and strengthens the resilience of SMEs in Europe value chain. And it was a short introduction from my side about RTIT project. And now I'm very happy to invite for speech Kruna. She is our partner, and she will share with you very interesting information. Dear Kruna, please take your floor.
Yes, thank you so much. This is Olena, I suppose. So thank you, Olena, for this kind introduction about advanced, sustainable, and bio-based materials, but also about a little bit about the RTIT project. Now I will share with all of you a bit more about the action plan. And let me first share my screen, please. Normally, just let me. But it does not allow me to share my screen, just the layout at this moment. Just let me try. At this moment, I cannot share my screen.
One moment, we will give you rights.
Thank you.
You have rights.
Let me
Please
see.
Try again.
But here I have just
green.
Yes, I know what it is. It's not a problem, but it doesn't want to do it. I don't know why.
If you want, you can send Leonid's presentation.
Too complicated. I mean, it's not a problem, but just a second. Just a second.
Okay, you have 2 options, or you will do it yourself, or you can send by email to Leonid presentation, and we will share for you.
But I can do it as well. Okay, I can send it, but okay, I'm so sorry. Just a second. I will do it in a second. Because it just provides me some layout and not the option to share my screen. I will do it in just a second. Attach document. Voila, I have just sent it. Olena, you're also in the, it's just sending now. Okay, so sorry. but it principally doesn't allow me to share, however, but okay. Have you received it now?
Yes, we received, and we will upload. It's several minutes. Not worry. Everything will be okay.
So I can talk in the meanwhile. Okay, so I will just introduce myself. So first, thank you all for attending the conference and for inviting me, first of all. Thanks to you, to the team from, to Evgeny and to Olena as well. So my name is Kruna Ratkovic. I have a kind of specific background because on one side I have an academic background. I'm a university professor. I'm a mathematician. But on the other side, I'm also co-founder of a small startup, an SME, which now has a bit more than 3 years is old, our SME. Our SME is oriented to development of some hardware and software solutions in the domain of ICT. And somehow, if I can say so, the aim of the RTIT project is somehow really connected to this linkage, which is never too strong or strong enough between the academia on one side and the industry. And of course, the RTIT project is focused on the RTI transfer, so research, technology, and innovation transfer, but in the domain of these 3 specific pillars, which was mentioned earlier by Olena, which are in particular bio-based, sustainable, and advanced materials. And somehow this is always difficult, if I can say so, to really transfer that knowledge that we gain in academia or in our research institutions or research institutes and through the companies, so that the companies can really gain this good value also for their incomes, but also to be sustainable, etc. So this is somehow, and the action plan that I will be sharing with you in just, I hope, 1 minute, is dealing. The action plan is one of the key outputs of this project. And this action plan... Yes?
Sorry, I interrupt you. We already ready to share with you.
Yes, please share it. Do not worry. Yeah, please.
1 moment.
Yes, that's it. You just put it in full screen, please. In presenter mode, just in the
yes.
Right.
1 moment.
Thank you so much, Olena. Thank you. Now I cannot see it, but perhaps it's... Yes, that's perfect. Thank you so much.
Yes.
But I will need to just to say when you need to move to the next slide. I'm sorry. Sorry. Thank you so much. So what I was telling just earlier, that of course the aim of this action plan is somehow really to make strong this link between, on the one side, academia research center, and to try to push this transfer, if I can say so, on the other side for the SMEs and startups, etc. So we can move to the following slide, please. Yes. So of course, when you are trying to talk about some solution or about some plan, as this will be my subject now, we also need to emphasize what is the problem and what we are what is the problem that we are facing now. So on one side, if we are, of course, this project, the RTIT project, is a Danube Interreg project. What does it mean? It means that it consists of Danube region countries. So and we have, if you compare, of course, that we have some fragmented innovation ecosystem across Danube countries. It is not, you cannot compare, for example, the innovation ecosystem in Slovenia with, for example, the innovation ecosystem in Montenegro or in Bosnia and Herzegovina, etc. So there is some discrepancies, and this gap needs to be somehow at least lower and decreased. And on the other side, we have companies that are facing barriers to assess advanced materials technologies. Sometimes it is they do not even know, or they do not even try to do so, or they believe that it is impossible. So there are different kind of barriers, okay? And on the other side, also, I believe that there exists some weak transnational collaboration in the context of commercialization pathways. And somehow there is always this problem, which I emphasized just at the beginning, before the slides, that there is some need for faster transfer of research results into business solution. This is always the problem. It does not need to be only in the domain of advanced bio-based or sustainable materials, but it is always the problems. On the other side, we have some, Europe has defined some important pathways, if I can say so, some important policies, some important frameworks that are really pushing, if I can say so, the actors. And these are us, all of us, such as Green Deal, Digital Europe, and some specific smart specialization strategies or policies that are really pushing that we need to integrate, for example, in this context, these kind of technologies in our production, please. Yeah. And I will just, perhaps from some other angle, just try to say a couple of words, as I already did, and Olena also provided a nice descriptive on the RTIT project. It is somehow creating know-how communities for accelerating the RTI transfer. There is the consortium is quite big. It consists of 13 partners, and there are 8 countries collaborating for this project in the Danube region. And of course, what is the concept? I just put here some notes. The main concept here is that we will create some know-how communities. Also, we will design and have some design thinking tools, some tools that will be provided. And then we will try really to integrate these tools into these know-how communities and to transfer them into the industry. And this will be done by some demonstration and by some pilots. And all of these processes that I just tried to give you some sketch, some idea, are nicely and really precisely defined within the action plan that I will be talking about just a couple of minutes later. Of course, what is the mission of the project itself is really to try to turn material science excellence, so which now remains like something that is not really used so much, into market-ready innovations. Okay, and that can boost companies. That will also is very important for some other concepts of sustainability, etc. And of course, what is the long-term goal is to strengthen, and to have some sustainable innovation capacity, of course, beyond the project lifetime. Olena, please. You need to go on this is the slide before. Yes, thank you so much. So here in the context of the RTIT project, we have here, as I already told a little bit, we have strategic focus on materials. So what is this? We have, on one side, we have bio-based materials. So now we have this substitution of fossil-based with some renewable solutions. This is the first one. And then we have also, of course, sustainable materials. Then we can see here some circular economy and eco-design in practice. And of course, some advanced materials such as nanotech, composites, and smart materials for Industry 4.0. And of course, then the use of these 3 pillars, if I can say so, will provide some strong impact on the energy sector, on the mobility sector, healthcare sector, but also in the ICT. And this aside, it will also drive competitiveness and resilience in regional economies. Please. Yeah. So what is the goal of this action plan? I try just to give you some hint or some idea. Okay. So it is the approach of this action plan or the project itself, but it is based on 3 strategic pillars, the 3 important things. And one is this push and pull mechanisms between research and what are the SME needs. And this is always difficult. From my experience, from my personal experience, I must say. And on the other side, we try to design, to have some design-based tools okay, that will increase the innovation capacities, and of course, to create some know-how communities that will cluster these actions in the 3 specific domains that I earlier already emphasized, which are bio-based, sustainable, and advanced materials. Please. Yeah. And how will all this be produced? How this will work? So the main framework of the action plan is saying, okay, we will first, in each country, we will match knowledge communities and expertise. Okay, this is the first. We need to map everybody and everything. And then we need to design some rollout plans for transnational collaboration. I will talk later about them as well. We will pilot some demonstration activities in 6 countries. And here you see already that we have some challenges there. Why? Because even if we project that these demonstration activities are similar in the sense are being based on some same model, but of course that each country has its own challenges, and we need to adapt and make some country-specific demonstration pilots, okay? And of course, the final step will be, of course, to extract some policy recommendation for sustainability. Of course, which are the stakeholders within all these activities? Here we have higher institutions, we have research and technology offices, we have digital innovation hubs, we have, of course, SMEs, so startups, different clusters, and policymakers. To try to do all this, of course, that some prior work has been done. And what was this done? What has been done? These design thinking tools have been created, but also in each country has provided the current state of its country. What does it mean? What are the strategies existing? What is happening, etc. So we know what is the starting point. From that starting point, we can know how we can go further. Next, please. So here is some kind of pictures. My colleagues already know this picture because it is part one of the figures of our action plan, and it somehow try to simulate this process of action planning. Okay, how does it work? Okay, how it is going. And if you go from the left, we have some know-how community mapping. Okay, and then after this mapping has been done, we will create we have some SME engagement and some call. This is already being done at this moment. It is ongoing. And after that, we will have some pilot process implementation. When we are finished by the pilot process implementation, of course, that we will gather some feedback collection. And of course, for this pilot process, we will use some design thinking and RTI tools that has been already, we have a base of these tools. And we will try then to adapt or to refine these tools if necessary. And then we will repeat this pilot process. But this is all if we look at the first loop, the interior loop, if I can say so. But we will also try to further upscale this at the transnational level. So as you see now, if you go to the bottom right, if I can say so, there will be some at one moment because we'll create some bigger bases then on a transnational level. And then there will be some cross-border matchmaking and joint, of course, value chain exploration. And then we will try to scale from national level to transnational collaboration. Next, please. And in order to do that, indeed, we are somehow supported by these, on the horizontal line, if I can say so, by these transnational rollout plans. So what are the objectives? Objective is to, of course, to align material technologies with regional smart specialization. Of course, everything you do and you want to do somehow needs to be aligned with some policies, existing policy, of course. Which are the actors here? Mainly the same as earlier. So we have universities, SMEs, digital innovation hubs, some clusters or R&D organization. And these transnational rollout plans will be executed through some cross-border innovation calls or some demo clustering also across pilot countries or some expert matchmaking events. And of course, that this will create some new values, some strong value chains and new cross-border collaboration. Next, please. And we And if we are talking about these demonstration activities, so demonstration pilots activities, as I emphasized earlier, we have 6 pilots that should be running in parallel. Now, these pilots are just in their development phase, and that they will be really fully implemented by the end of this year. And we have 6 pilots running in parallel, so Montenegro, Slovenia, Bosnia-Herzegovina, Bulgaria, Hungary, and Ukraine. And of course, that for these demonstration activities, there will be the use of design thinkings and these RTI tools to support SMEs. And how we will, of course, we are creating, it has been already done. Some SMEs will be invited via targeted calls and engagement campaigns, and they will be these iterative collaboration cycles, as I already demonstrated you through the scheme or figure that I showed you earlier. And of course, that these demonstrations serve, I will not say only as proof of concepts for scalability, but they create you also some bigger database, and then you can also not easily, but at least more easily scale to the transnational level. Next, please. And I will just say a couple of words, because I know that later we have Evgeny that will talk about the demonstration plan for Ukraine. So I'm certain that he will talk about it in more details. Now I will just go to just a couple of points in the context of Montenegro. As I told you earlier, each demonstration plan for each country is somehow is based on the same model, but needs to be somehow different depending on the challenges of its particular national challenges. So here we have the national context. We have, of course, the smart specialization strategy, priority on materials, and of course, we have mapped the stakeholders via know-how communities, and we envisage to have this will be done in September. In Montenegro, some SME training and mentoring. It will be like some demonstration day where we will also meet with SMEs, and then we will plan some training. And of course, this will provide then some networking with EU partners. And of course, then this will arise in some pilotings. And of course, what is the role to bridge, of course, between Western Balkans and EU material innovation ecosystems? Because of course, at the later stage, you hope that some of these SMEs will be also interested, or will be possible for them to scale at transnational level. Next, please. And here is just to show you a bit this and to have a bigger and greater picture, because when we try to understand something or to think of something, it is really important to have a larger idea what is it about. So here, if we are talking about the strategic framework for the research and technology and innovation transfer in the Danube region, you have the action plan, which is like the main horizontal plan. And then you have also these transnational rollout plans and demo plans, which are interconnected, but both are making inputs and are necessary for the action plan execution. Okay, next, please. And what are the expected results and impact metrics? First is the question, why are you doing something? What is the problem? Then what you will be doing, and then what will be the results? So here are the results and what is the impact. So of course, at the SME level, there will be some improved innovation capacity, and of course, some faster adoption of materials technologies. On the other side, on the transnational level, there will be some increased knowledge transfer and cooperation networks. And of course, at the policy level, better frameworks for commercialization of research. There are some indicators, also some KPIs that have been defined in the project. These KPIs are for all the demonstration plans and all the activities that will be done during the next almost year, if we can say, by the end of the project, by the end of June next year. So we will have at least 100 SMEs engaged, more than 30 tools. Here I wrote technologies, but I meant design thinking tools transferred, and 20 or more transnational collaboration launched. Next, please. And finally, of course, if you do something, you need really, because what you are doing, it really needs to make some sense also for the policymakers, because they are the ones that are deciding, if I can say so. And here we will have some established structured support for knowledge-based communities on one side. We will try and we will develop regional innovation support instruments for SMEs. The idea is also to create sustainable financing scheme for commercialization of material science, to also ensure inclusion of Western Balkans in EU level policy frameworks. Yes, next, please. And of course, what can be considered to be next steps? Of course, when you are implementing a project, one of the key points is the sustainability and transferability of your project, or not key, but very important points. And, you know, it is important to continue rollout beyond project lifetime. Also to try to expand demonstration results to other Danube and EU regions. So try to go further beyond borders. And the ideal would be to build some long-term partnerships between academia, SMEs, and policymakers, to invite wider community to join in sustaining innovation ecosystems, and of course to consider the RTIT project as a blueprint for knowledge-driven economic growth. Next, please. And finally, this would just be like a key message that the commercialization of material science can be considered as a community-driven effort. And as you see, it is not such an easy task. It involves an involvement, as you see, of a lot of actors. But if you really think of it and make a good plan and you work on it, I believe that we can create, and this is one of them, a really good mechanism that can nicely work and enable this faster transfers of materials excellence to the SMEs commercializations. Thank you so much. Thank you.
Thank you, Kruna, for very interesting presentation. And it's very important when scientists not only make fundamental research, but also apply research and received some new innovation products. And yes, of course, all business support organization and offices of transfer technology have to help them to find investor, technology partners who are interested in innovative products. And material science, it's now a very important topic. That's why I hope that this RTI project will be able to create a community of scientists who produce and develop interesting new materials, different type of new materials, as we described today in this session. And as you mentioned, that consortium of RTI project is international and covered the Danube region, and we have several countries, yes, and Ukraine is also part of this project. That's why you provided us a general overview of action plan of the project, and taking into account that now in Ukraine an organized international scientific research conference in Ukraine, maybe we will share also more detailed action plan for Ukraine. And it's a great pleasure for me to invite Evgeny Leonenko, who will share with us individual demonstration plan of Ukraine as part of Danube region in the frame of action plan to accelerate RTI transfer in the field of materials and material technology. And it will be also general information, but with more focus on Ukraine and Ukrainian scientists. And not only scientists, but also startups, innovation organization who potentially are interested in new materials. So, Evgeny, please take your floor.
Good day. I tell you about individual demonstration plan of Ukraine as part of Danube region in frame of the action plan to accelerate research technology innovation transfer in the field of materials and materials technologies. Strategy of the development of the innovation activity and the research technology innovation is covered all areas of Ukraine economy. Until now, Ukraine has not created effective mechanism that could ensure the development of the country against the backdrop of serious challenges of a global nature. As a result of the inverse type of market transformation combined with globalization process on the basis of market mechanism, Ukraine has adapted to certain segments of the world market as raw materials appendage and did not form its domestic markets. Ukraine has the opportunity and to innovative and digital transformation and apply digital technology and transform its raw materials and energy into value-added products that will accelerate an economic development without negative consequences. The development of the innovation strategy of the development of the innovation activity for the period up to 2030 and the legislation of Ukraine on scientific and technology activities will make it possible to create a national innovation ecosystem and ensure the development and effective interaction of the elements of the national innovation ecosystem, which will be able to become a driver of accelerated economic growth and will contribute to the introduction of new materials such as advanced materials, bio-based, sustainable, and technology solution. But unfortunately, at various strategy of the innovation process are the problems which should be solved with the involvement of the research technology innovation organization, in which the help of state policy tools main of them. Lack of established communication between scientists and business representatives who are interested in the development of innovation. Limited financial and material resources for the creation of innovation infrastructure. Insufficient awareness of employment of units responsible for commercialization in scientific institutions regarding the assessment of the level of readiness of scientists and technical development, the subsequent market effect of the transferred commercialization technology, the development of a commercial development strategy, technology transfer scenarios, which are different strategies of readiness. Lack of limited effectiveness of innovation infrastructure, which should promote the development of innovation entrepreneurships. The departure of qualified personnel, scientists, investors, enterprises abroad. The level of the development of sciences and technology and the degree of symbiosis of scientific organizations with industry and SME are decisive factor and development of new materials and technology in Ukraine. This stipulated the necessary of priority support of the development of science and for the acceleration of research technology innovation transfer in the field of materials and material strategy between scientific organization and industry and SMEs. Next slide. Next slide, please. No. What about objectives and stakeholders ecosystem? The individual demonstration plan to accelerate research technology innovation transfer in Ukraine can reduce the impact of negative factors by supporting innovation potential of Ukraine, ensuring normative and legal regulation in the field of materials, research technology, innovation transfer, and innovation activity. Promotion the development of the education system aimed at training qualified personnel to participate in materials, research technology, innovation transfer, and innovation activities. Ensuring effective interaction of sciences, the public sector, and business. Communication activities to attract the SME with the aim of informing about awarenesses and basic transfer of know-how and research technology innovation in the field of materials of innovation. Engaging stakeholders plays a pivotal role in driving innovation development in Ukraine and shaping the research technology innovation transfer strategy. The nation innovation system consists of research institutions, different clusters, and industry association, SME, and intermediaries. The Ukrainian know-how communities have the following members, but not limited. The Institute of Physics of the National Academy of Sciences of Ukraine, Dnipro University of Technology, Ukrainian Chamber of Commerce and Industry, National University of Yuri Kondratik Poltava Polytechnic, IT Dnipro Community, Ukraine Automotive and Mobile Cluster, Taras Shevchenko National University. Next slide. Activities and support services in the frame of individual demonstration plan of Ukraine. The Ukraine know-how community within the framework of the individual demonstration plan to accelerate research technology innovation transfer in Ukraine plan deliver a target of activities and support services. Capacity building workshop for SME and innovation intermediaries. Workshop will be organized to raise awareness among SMEs, researchers, and support and organizing about the opportunities and mechanism for research technology innovation transfer in materials and material technology. Second, thematic matchmaking and networking events in the frame of conferences. To foster stronger research industry connection, it will organize thematic matchmaking events focusing on collaboration opportunities in bio-based, sustainable and advanced materials. Third, tailored mention and coaching session. Selected SME and research institution will receive customized mention to develop project ideas, build innovation strategy, and prepare for future research technology innovation collaboration. Study tour. In order to deepen the gain the training, it plans to organize a study tour for participating SMEs to one of the know-how partners. Advisory help for access to funding and preparation project. Providing advice to members of the research technology innovation transfer knowledge community, SMEs, startup researchers on attracting national and European funding. Assisting in searching for an consulting in writing EU project. You can registration for this program by this link and QR code and contact a person in Ukraine for individual demonstration plan. Please, next slide, please. Thank you for your attention. I was the last speaker in this section. And if in a conference hall or in Zoom.
Okay, so without further interruption, because of the lack of time, we will move directly to the next section, the section Nanocomposite and Nanomaterials. And our first speaker of this section should be Professor Leonid Vasilechko, who present here on site. from the Lviv Polytechnic National University, Ukraine, and he will present us the interesting topic, structural characterization of europium ash, third precursor for the synthesis of europium dichalcogenide.
Але ж він должен бути підключений. Скільки йде за тему, можливо, я вас підписую. Давайте. Ми зараз тоді вивчаємо.
Hello, everybody. I'm glad to see all of you here and taking the auditorium. I propose to switch on in Ukrainian. I hope that everybody can understand me in Ukrainian. Okay? If there are online, yeah, okay, no problem. Okay, let's start. I am Leonid Vasileshko from Lviv Polytechnical University. My talk today is devoted to the study of crystal structure characterization of europium hydroxide as precursors for the synthesis of europium dichalcogenide. The work was done together with our colleague from Vilnius University, from Chemical Department of Vilnius University. Next slide, please. Okay, some works on our laboratory, the laboratory of oxide physics at Lviv Polytechnical University. The main object of our investigation are compound of rare earths. Historically, the first was the different mixed oxide compounds of rare earths with perovskite structure. That means aluminate, gallase, cobaltase, ferrite, manganites, and so on. Mixed oxides with garnet structure, mixed vanadite, vanadium space. Biologically important compounds are known are being conditioned, complex intermetallic system of rare earths, nickel and gallium. This one is collaboration with Max Planck Institute of Chemical Physics from Dresden. And since last year, we have studied, we are involved in the study of rare earth remedies in collaboration with scientists from Georgetown University, Vilnius University, and Institute of Physics, Training Academy of Science. We also have a long time established collaboration with International Center for Diffraction Data for the preparation of high quality diffraction data from materials. And since during the last decades, we prepare more than 1,000 patterns for the ICDD PDF4, PDF plus for data. Next slide, please. Some of previous findings, there is some, for example, the sequence of the concentration and temperature induced phase transition in the mixed lanthan nickel gallium and ceri nickel gallium system. We have found both concentration induced phase transition from cubic to tetragonal to rhombic to phase-centered orthorhombic, then again to tetragonal structure, depending on the nickel to gallium ratio. And also in this system, we found by in situ high temperature synchrotron diffraction experiments, we found very interesting sequence of the temperature-induced phase transition, again from tetraorthorhombic to orthorhombic F to tetragonal, and then to the cubic, high-temperature cubic structure. Note that this transition sequence of trace transition are reversible, and cooling down will again obtain tetragonal orthorhombic structure. Next slide, please. Also, we found very interesting phenomena, anomalous lattice expansion in intermetallic ytterbium palladium gallium compound. We have very large range of the negative thermal expansion in all three different crystallographic directions. From the physical point of view, this unknown the reason of such transition, but we observed this both with neutron and synchrotron diffraction data. Next, please. Also, very interesting phenomenon is the so-called lattice parameter crossover in orthorhombic system with the formation of metrically cubic structure preserving orthorhombic symmetry. Such phenomena were found in some perovskite system. Next slide. Another system we are studied is mixed cobaltite with perovskite structure. In this system, we have found unusual spin crossover phenomena and anomalous thermal expansion in cobaltite-based materials, which are connected, associated with spin phase transition from low spin to intermediate spin and then to high spin state. Next, please. One of the last, but not the least interesting phenomena, also negative thermal expansion in rare earth perovskites, including yttrium aluminate, YAP perovskite, and also there are some schemes which explain the negative thermal expansion phenomena in perovskites, in some perovskite. Next, please. Next slide. Yeah, and the last from previous studies, the unusual sequence of phase transition in cerium aluminate. One unusual, you see the low temperature phase of these materials has tetragonal structure, which contradict Landau theory of the phase transition, because high temperature structure are more high symmetry than lower symmetry than low temperature structure. These materials were published in the Handbook of Physical and Chemistry and Rare Earths in the separate chapter. And then next slide, please. And then I switched on to my today presentation. This work was done in the frame of the IMPRESS-U program, together with, led by Professor Sarah Stoll from Georgetown University, in the frame of IMPRESS-U program. Yeah, and as I told previous, our team consists from the group of Georgetown University, Vilnius University, colleague from Vilnius University will prepare the materials for our investigation, and the group from Ukrainian consists from two teams from Lviv Polytechnical University and Institute of Physics. Our task is precise structure investigation of the materials by X-ray diffraction and Raman spectroscopy. Institute of Physics. Next, please, one. Okay, just I switch for the tight European hydroxide materials. Series of the nanocrystallized powders were obtained in Vilnius University by co-precipitation method. You see in such a way the phase pure crystal structure was obtained, no traces of the porine phase were detected, and very nice rod-like nanoparticles were obtained with a dimension of about 50-50 and 300 nanometers. The rods are You see this form, this shape of the nanocrystal is demonstrated also as the X-ray pattern, in which the strong texture in two different direction axes are observable. Next one, next please. Crystal structure and base. Sorry. Maybe I will. No problem. Camera. Okay. Crystal structure and phase purity of the material was surely confirmed by full profile research refinement. Graphical results of such refinement you can see here, and crystal structure visualization of the hexagonal structure you see here, and structure parameter here. Yeah. Next one. We also study the related materials, namely neodymium hydroxide and three materials from solid solution between europium and neodymium hydroxide. You see that in all four cases we also have pure hexagonal structure of these materials, confirmed by Rietveld refinement. Next slide, please. Lattice parameter of the solid solution, of the three solid solution, both A parameter and C parameter fit well with the lattice parameter of the parent europium and neodymium hydroxide. If we see for the relative expansion, it might be seen that relative expansion in C direction circa 2 times higher than relative expansion in A direction. That means that expansion of the lattice in solid solution has strongly anisotropic character. Next slide, please. If we plot the lattice parameter of the five materials studied by us, you can see that this lattice parameter of this material pointed by stars, the lattice parameters fit very well with the lattice parameter of the all series of rare earth hydroxides. These data are taken from the Pearson database. That means the structure parameters of these materials can be parameterized as a function of the radius of rare earth cation. Next point. We also study thermal expansion of the material, both by DTG technique and in situ X-ray diffraction technique. Both this technique revealed stepwise decomposition of europium hydroxide about 380 degrees Celsius, which is evidenced both in DTA, DTG, and in situ X-ray diffraction. From the right pattern, you see gradual decomposition of the hexagonal structure, blue one pattern, to the monoclinic europium hydroxide. Yeah, and the composition is through the at this temperature we have coexistence both hexagonal and monoclinic structure. Next, please. Next slide, please. Next one. Similar picture show also neodymium hydroxide. The only difference that there are practically no intermediate change. The structure transforms different from hexagonal to monoclinic. And next one. Next one. And if we compare in situ and ex situ XRD, then can be seen that after heat treating heat treating up to 1000 Celsius, europium hydroxide and oxygen hydroxide transforms to the cubic modification of europium oxide. In contrast, neodymium materials transform to the trigonal modification of neodymium. The difference between these two materials. What will happen with the solid solution? We will see. We did not study yet thermal expansion of the solid solution material. Perhaps we will have coexistence both cubic and trigonal phase of the rare earth oxides. Next, please. If we compare, we also studied the thermal expansion of the europium hydroxide. You see that we have non-linear expansion and until the material transforms, decompose to the oxide. Yeah, but clear we see a deviation from the linearity, especially pronounced in a direction of hexagonal structure. If we compare relative expansion, again, we see the relative expansion in C direction is much higher than expansivity in A direction. From here, you see a similarity with concentration dependence of the lattice parameter. Previously, I showed you that also from the concentration, relative expansion in C direction is 2 times higher than in C direction. Next one. Similar thermal behavior also we observe for the neodymium material and a solid solution europium neodymium OH3. Yeah. And if we compare relative expansion of 3 material, we can see that in mainly relation expansion of the solid solution material feed to the parent europium and neodymium hydroxide, but some deviation, especially in C parameter, we can observe for the solid solution material. There is some unusual behavior because, as usually, solid solution material show behavior in between 2 parent materials. Yeah, in our case, solid solution material expansivity is higher than both solid solution materials. Next, please. So, in principle, it is all. I thought at the beginning that we studied this material mainly as a precursor for the final synthesis of the europium disulfide, which is main task of the IMPRESS-U project. And the results, the colleague from Vilnius prepare europium disulfide from the precursor. There are diffraction pattern of this material, and who is maybe interested in the results obtained, I recommend tomorrow see the poster number in the book of materials 73, presented by Svetlana Turchak, devoted to the synthesis and structure characterization of europium dihalogenide. And next one, I would acknowledge again the support of the US National Academy of Science under IMPRESS-U project, our colleague from Vilnius University, my colleague, young colleague from Lviv, our laboratory of oxide crystal from Lviv Polytechnical University, and especially thanks our heroes from Ukrainian army, giving us possibility to be here finally. And thanks all of you for your attention.
Hello. Thank you very much for very interesting presentation. And now we move to question. We have the first question from the hall. One moment.
So thank you for your presentation. I have one question regarding to the non-linearity in unit cell expansion of europium and neodymium when both compounds are in composite. Yes, here. Is this non-linearity refers only to a change in a crystal type of crystal lattice, or there is other mechanism of it?
No change of the crystal lattice, no change of the crystal structure until the decomposition of the materials. That means no change. The structure remains hexagonal until decomposition. The deviation from non-linearity, in principle, it is not rare phenomena, yeah. But structure, the symmetry of the material remains the same, not connected with the change in symmetry.
Okay, thank you very much.
Yeah.
Additional question? Maybe someone, we have also from conference hall, one more question.
Thank you very much for your nice talk. So I have a question. Regarding europium hydroxide and how you get europium dichalcogenide. So the question is, do you still observe impurities of oxide and hydrogen in europium dichalcogenide?
Impurity of
oxide and of hydrogen.
Hydrogen?
No, you use Europe. So if I did understand well, you use europium hydroxide to obtain europium dichalcogenide. Yeah. So how do you remove this OH group?
Okay. As I taught at the introduction, the synthesis of the material was performed in a group of from Vilnius University. We study the materials. I am not ready to answer how to remove. One, I know that the synthesis of the europium dichalcogenide from hydroxide is really not trivial task, yeah. And if you are interested, I can ask together my colleague from Vilnius, because we did and do this work together, yeah. The project is still run. We only start in May with this evaluation of this project. But if you're interested how they remove this, this may be the last, not last one, yeah, was obtained boron sulfur method, yeah. One only I can tell you now.
Okay.
Yeah.
Thank you very much.
Thank you for your interesting presentation. We have no time for question. And
yeah, thank you.
The next speaker must be Professor Alexander Sorokin. It will be online.
Hello, I'm here. Do you hear me?
Yes.
Okay. So you should see my presentation.
Wait, yes, it's okay. You can start your presentation.
Thank you very much for invitation me to make this report, and I want to make some interesting information about the possibility of formation luminescent liquid crystals based on sunny dye molecular aggregates. I think everybody knows that liquid crystals are very interesting organic materials with very high ordering, which can have different orderings and different types of it, like pneumatic, holysteric, and so on. And one of the direction of development in these materials is formation of luminescent liquid crystals due to embedding to the typical liquid crystalline materials some luminescence objects. It could be or some organic fluorophores or inorganic nanoparticles and so on. There's a very interesting direction due to the properties of such materials. One of the possible application is further development of the very thin and very smart and unique thin films for the screens. And for example, the other one direction is trying to formate the micro and even nano lasers based on such materials. And in this regard, the luminescent, this liquid crystals should not only have some luminescent, but very interesting, the luminescent with strong polarization. And to achieve it, some special dopants should be used. For example, it could be used or some specially synthesized materials for formation of this liquid crystal, or for example, effects of aggregated stimulated emission or using some luminescent aggregates. And one of the such type of very interesting aggregates, luminescent aggregates, which is not very highly used for up to now for these materials, but we are interested to provide it. This so-called J aggregates. So this is molecular aggregates formed by different organic fluorophores, which due to very high ordering of the molecules within these aggregates possess formation of molecular excitons of friendly types, which could be transfer energy through these aggregates. And such type of aggregates possess very unique excitonic properties, like very high and luminescent properties, very high extinction, and appearance of very narrow exciton band called J band on the name of the discoverers Edward Jelly. The problem of aggregates that they formate, for example, such very nice one-dimensional objects which has only less than 10 nanometers long fibers with micrometer long fibers, but these are rather soft matter, and the properties and the structure, the morphology of such objects could be strongly changed depending on the media in which such type of aggregates are formed. Very quickly after the discovery in 30s of the 20th years of the 20th century, aggregates find their application, for example, as photosynthesizers for photographic materials. After that, they have applied as effective luminescent probes for biology. And some of these aggregates currently are typical probe for mitochondrial potential measurement. Recently, aggregates was revealed as a very interesting synthesizers for optoelectronics, for example, narrow band photodiodes, also in as a luminescent probes, but with luminescent and near infrared properties, and also they're quite unique objects in these fields. But concerning formation of edge aggregates and liquid crystals are very few only communications was found. Some type of molecules can form themselves liquid crystalline ordering, and some of these aggregates were embedded into luminescent the liquid crystal materials and form luminescent such liquid crystals with achieved laser generation. But as for cyanide dyes, up to now there is no other communication for the formation of aggregates in liquid crystals, and we try on different molecules which we know very well their aggregation properties, and found that for some time, for example, such very well-known liquid crystal materials as 5CB, they indeed in a very narrow concentration range could form aggregates within this matrix. But the excitonic properties of these aggregates become worse, and we have seen more widened this excitonic band, J band, and hence much less excitonic coherence lengths. I will show you on the next slide. And we see from the luminescent microscopy imaging that the structure and the morphology of this aggregate could be drastically changed compared with their structure and morphology in water solutions. Unfortunately, due to very close molecular structure of our cyanide dyes and, for example, typical liquid crystals materials, to reveal the structure of these materials, we couldn't use such typical measurements as, for example, electron microscopy and, for example, atomic force microscopy, because most of these aggregates are believed to be in the volume of the liquid crystals. Also, we have found that the luminescent lifetime is strongly increased in this case, typically for J aggregates with very good excitonic properties. The lifetimes is strongly decreased, and this is connected with a high excitonic coherence length. Indeed, our estimations show that in liquid crystals, we have seen a very significant disorder in this aggregate, and so a very small excitonic coherence length. We also see the changing in, for example, spectral position, so on. But and this was quite surprising. The fluorescent quantum yield, it was nearly the same for the aggregates in liquid crystals and in water. And the question was, if we will see some polarization of luminescence in case of our J aggregates. Indeed, we see some polarization. Unfortunately, this only initial experiments which should be continued, and we have now more powerful microscopy device, and we hope that we much deeper conduct our experiments. But unexpectedly, we'll see that the polarization, luminescent of polarized emission was more intense when our polarizers was perpendicular to the excitation polarizers, which was oriented along the director of these liquid crystals and along the direction of supposed long axis of our aggregates. So we can see that this estimation results in about nearly magic angle, about 57 degrees of luminescence emission concerning the excitation of this luminescence. And we suppose that in the liquid crystals we have cylindrical structure of this type of aggregates, but all these experiments should be done further. We tried to embed in these liquid crystals other type of cyanidine, also which aggregates are also very well known, such type of pseudoisocyanine or PIC. And we see that this type of cyanidase is much worse incorporate into the liquid crystals with also strong changing of their morphology and strong changing of their optical properties with only small J-Y band and the very high wide emission, which is strongly shifted to the red part of spectra, with also some monomer luminescent founded. This is this shoulder on the luminescent spectra. So we conclude that our aggregates is very disorder, is maybe much more disorder compared with TDBC aggregates, but still some amount of this dye, which mostly presented in liquid crystal as in their monomeric form, they still form some small aggregates. And it was very interesting that for both type of our J aggregates, for TDBC1 and for PIC1, we have found a very strong photostability. For example, in water, this aggregates due to excitonic trapping on different defects, and these defects could be formed by elimination of this type of aggregates. The typical photostability is not so high, but in case of liquid crystals, we can see that the photostability is strongly higher compared with water solutions. One of the reasons which we supposed is a very weak penetration of the oxygen spices in the liquid crystals, and it's quite known phenomena. And we know that for organics, these oxygen spices are very strong traps, and they one of the main reason for the small photostability of organics, and is exactly much more intense for the J aggregates because they aggregate in our case. We also check how this incorporation of J aggregates into the liquid crystals influence on the liquid crystalline properties. For example, you can see the so-called Frederick's transition. This is how your matrix, how your director of the orientation of the molecules within liquid crystals is react on the electromagnetic electric field applied to the liquid crystals. And we see that despite some shifting of this Frederick's transition to the more voltage compared with pure matrix, this is not very good for the, for example, optoelectronic application where less voltage should be used for the better applications. We seen that this transition became much more sharper. So we have much less fluctuation of the molecules while they are redirect on the electric field, and such phenomenon could be useful for further optoelectronic applications. So the conclusion that we form stable J-aggregate dispersion of two cyanine dyes with much more better irrigation of TDBC dyes compared with PIC dyes. In both types, we have seen the changing of morphology of aggregates and decreasing of exciton coherence length, which reveals a very large statical disorder in this aggregate under influence of crystalline matrix. But for both cases, we have found a great enhancement of photostability, and also we have found the change of electro-optical properties of liquid crystalline matrix incorporated with both type of J aggregates. Thank you for your attention, and thanks to our army for the opportunity to live and work in Kharkiv. Thank you very much.
Thank you for your presentation. Question from conference zone. One question.
Thank you for your presentation. Was the 5CB with J aggregates in nematic phase or other phases?
It was nematic phase. Currently, we check how this aggregation in holosteric matrix.
Okay, thank you. You answered the second part of my question.
Okay.
We have one question from chat, from Zoom.
Yes, can I ask the question? The question concerns photostability or photodegradation of J aggregates. Can you explain?
Okay, thank you. You answered the second part of my question. Okay, thank you. We have one question from chat, from Zoom.
Yes, can I ask the question? The question concerns photostability or photodegradation of J aggregates. You showed that in liquid crystal matrix, photostability is much better, but I suggest that oxygen can also penetrate into the liquid crystals. And my question is, probably the reason may be due to the different thermal conductivity of the different media which surround these aggregates. Did you think about this reason?
Up to now, we have not clear explanation this effect. Also, it could be some special morphology of aggregates because depending on their structure, there also strong difference in optical properties can be demonstrated. So this is I supposed one of the obvious explanation, but this is only I show you some first result and clear explanation of different results which I demonstrate you. I inspected in further experiments. Okay.
And the last question from chat Zoom from Leonid Dolgov. If liquid crystal heated and become isotropic, will it influence on fluorescence?
We check how it's influence, but not only for the continuous luminescence, not for the temporal measurements, not for the lifetimes. So aggregates are stable and also in this continuous mode after the heating, but with less efficient fluorescence and with worse optical properties. So liquid crystals in the ordering phase are better for the G-IRGs compared with this continuous mode and without ordering.
Okay, thank you for your interesting presentation.
Thank you very much.
The next speaker must be Professor Alexander Rud online.
Hello.
Alexander, you are with us.
Hello. You share my presentation, or I shall do it myself? Well,
what you
you have my presentation. You will share my presentation.
Let we share your presentation.
Well,
just a moment. Your presentation is shared.
Yes. Thank you. Well, good afternoon, dear colleagues. First of all, I'd like to thank organizer for making the possibility to do this presentation, which entitled Effect of Titanium Aluminium CMX Phase on the Properties of Composites based on Sintered Aluminium Silicium Nickel Alloys. Next slide, please. Next slide, please. Yes. It is well known that aluminum alloys are playing a very important role in different fields of technique, industry, and public life. Naturally, the question for elaboration new composition of aluminum alloys with enhancing operational properties is very actual. There are just a lot of approaches to solve this problem. One of the most interesting is elaboration of metal matrix composites by powder metallurgy technique. As a rule, aluminum-based matrix is reinforced by ceramic particles, type of titanium C, alumina C, silicium C, etc. But often we have vice versa result with decreasing their mechanical properties. First of all, due non-wetting of reinforcing additives with aluminum matrix. And in our work, we develop, synthesize, and study the structural and phase state, physical and mechanical properties of composite materials with the content of different content of max phase, titanium 3, aluminum C2 as reinforced part. Next slide, please. We use aluminum, silicium, nickel system, and the chemical composition you can see. It is very big value of silicium atom, up to more than 25 white %. It is special type of alloy aluminum, having very small coefficient of thermal expansion, typical for steels. And this alloys can be produced only by powder metallurgy method, and are used in for together work with steels details. In our institute, we propose to very original method to produce powder of this alloy using melt spun, rapidly quenched melt spun ribbons with its subsequent grinding in planetary ball mill. Next slide, please. And as I said, we use max phase for strengthening composite. Max phase is very interesting materials. It is layered, they are layered ternary nitride carbides with a crystalline hexagonal structure. What is interesting, they combine the properties of both metals and ceramics. So low density, high thermal and electric conductivity, high strength, low elastic models, high corrosion resistance, etc. Next slide, please. Next one, please. We synthesized titanium 3, aluminum C2 max phase in our department, at our institute. We used simple sintering method of blended powders, initial blended powders, at just enough high temperatures, up to 1,500 centigrades. And the yield of max phase is just big, up to 95%. These microphotos demonstrate microstructure of synthesized max phase, what is typically for such type objects. Next slide, please. For production metal matrix composites, aluminium, nickel, silicium, nickel alloy powder, we used different percentage of max phase, namely 10, 20, 30, and 40 white percent. And also initial state was studied. Also, well, sintering process was performed under pressure at 60 MPa with using spark plasma sintering techniques. The first X-ray diagram of initial state of alloy shows the presence of aluminium in alloy, aluminium, silicium, and just small part of aluminium 3 nickel intermetallics particles. But in case of alloy with addition of max phase, for example, this demonstrates 40 white percent of max phase, titanium 3 initial titanium 3 aluminium C2. And what is it interesting? It was observed that the original titanium aluminium C2 phase underwent a fast phase transformation during the spark plasma sintering process, resulting in formation of titanium silicium C2, known as blue color. Practically, in the process of sintering, the first initial max phase undergo in the next one. So aluminium atoms were changed by silicium atom from aluminium matrix. This transformation is explained by this substitution of aluminium atoms in the max phase by silicon atoms from the surrounding aluminium C nickel alloy matrix. Well, it is very interesting results. Next slide, please. Of course, we study microstructure produced composites, and they demonstrate that in case of using max phase as additives, we practically synthesized metal matrix composites, where skeleton from max phase and between them are placed particles from aluminium, silicium, and intermetallics particles. Next slide, please. Next, please. Of course, we study thermomechanical properties, study thermophysical properties, namely CTE, and some of mechanical properties. CTE is proper for practically for all studied samples, is typical for original alloy, and is typical also for steel. Hardness is growing with enhanced content of max phase from 102 weakest hardness to practically 300 HV, sorry. But the most value of flexible strength is character is proper for composition with 20 percentage of max phase. So the elaborated composites, proposed composites have just nice thermophysical properties and mechanical properties, and can be used for implementation in industry. In next, please, one. Thank you for your attention. Thanks, of course.
Thank you for your presentation and questions. We have no question in the hall and no question in Zoom. Thank you again for interesting presentation. And the next speaker, Professor Marina Kosevich. Your presentation will be on site.
Is it okay?
Good afternoon. My presentation will be devoted to mass spectrometric study of non-covalent and covalent interactions of organic compounds with molybdenum disulfide nanosheet. The object of our study are composites of molybdenum disulfide, which is the well-known nanomaterial promising for biomedical and nanotechnology applications. And two-dimensional nanosheets or nanoplates of molybdenum disulfide are obtained from the crystalline material by various exfoliation techniques. The objective to produce nanocomposites is clear. One expects to obtain material with new properties and maybe of higher performance. We have prepared our nanocomposites by a standard technique of ultrasound treatment of the mixture of components in water and in organic compounds stored there both as exfoliation objects and for functionalization of nanomaterial. To make some systems, we have tested a row of various organic components, mainly of biological significance: amino acids, nitrogen bases, dyes, polymers, and fuels. And in such composites, both organic and inorganic components can be modified and undergo some transformation. Next one. So the aim of our study was to characterize nanocomposites by laser desorption ionization mass spectrometry. Of course, these materials were studied by various techniques, but we have the aim applied, namely this one. And answer the question how the properties of nanocomposites and the processes in nanocomposites are reflected in their laser desorption ionization mass spectra. And they may be covalent and non-covalent interactions and transformations. Next, please. So we applied a method of laser desorption mass spectrometry, which consists in irradiation of the material by laser pulses. In our case, ultraviolet laser 337 nanometers. Experiments were performed at the Center for Collective Use
scientific equipment of the National Academy of Science. And I would like to ask to answer at once one frequently asked question concerning the damaging effect of laser radiation. As many people here also find lasers, so many years of worldwide experience of laser diffraction and radiation applications permitted to establish the required non-damaging diffraction mode. If we use higher laser radiation, of course, we can damage and simply burn our material. And we reconstruct the composition of the sample from the mass spectra, combining both positive ions, negative ions. We obtain molecular ions, fragments, clusters, and interpret them from our point of view. Next slide. We started with molybdenum disulfide, and of course, as in any other techniques, various kinds of compounds produce different spectral characteristics. Organic molecular compounds produce molecular ions mainly in the positive ion mode and fingerprint characteristic fragmentation. But inorganic molecular solids are characterized by sputtering of single atoms or clusters composed of atomic components of the solid. And molybdenum disulfide is sputtered in the form of clusters composed of molybdenum, sulfur, and some number of oxygen atoms, which appear with oxidation of the material and ultrasound treatment in water. And molybdenum is known to be a polyisotopic element, so molybdenum containing clusters are represented by thick envelopes with the corresponding isotopic distribution. So it's all described in corresponding to the And in the literature on nanomaterials and nanocomposites, we often can meet with the illustration of the kind, types of interactions of compounds with nano objects. So it may be non-covalent interactions with the plane surface of nanoplate. It can be covalent interactions with the edges of such plate. And in the case of molybdenum disulfide, there can be catalytic activity of this compound leading to the results. I show examples of several groups of compounds. To start with polymers, polyethylene glycol. In the positive ion mode, we obtain a mass spectrum characteristic of pure polyethylene glycol containing bell-shaped distributions of oligomers of this polymer. In the negative ion mode, we show suppression of sputtering of clusters as compared to pure molybdenum, which occurs because of some shielding of polyethylene glycol covering the process of nanoparticles. Here, suppose that this type of spectra characterize non-covalent van der Waals interactions without any modification, which is good for biological applications if stabilization of nanoparticles is used for enhancing their compatibility and the availability of various nanoparticles. The next example is the organic salts. Exemplified by organic cationic dye, methylene blue, which is a medicine and popular text compound in social science. This is organic compound, organic salt consisting of organic cation and anion. It dissociates in water solution, and I would like to turn your attention that there is no localization of positive charge in someone sometimes written in the schemes, but the charge is near relocated, redistributed over the whole paracyclic cation. So in the mass spectra of this type of compounds, we usually see intact cation peak of the cation and no other peaks in the spectrum, which is characteristic of monomeric absorption of the cations on molybdenum disulfide. In this case, we have Coulombic interactions. We consider that molecular glucation loses chlorine anion and substitutes it by partially negatively charged sources of molybdenum disulfide. We obtain such type of I don't know it. A type of polyester bound by electrostatic interactions. Many methylene glucations and extended negatively charged molybdenum disulfide. So the next example is group of fuel compounds. These compounds molybdenum disulfide exhibit with catalytic activity, catalytic redox activity, and usually the fuels jump. In this case, oxidation of fuels on the molybdenum disulfide surface takes place, and so in this case, a diamond is formed by the sulfide bridge between two monomers, equivalent diamond and equivalent interaction. In the mass spectra, this such product goes in protonated and so I'll exemplify of compound by cysteine, which plays an important role in the biological system by stabilization of the tertiary structure of proteins by formation of liquefied. And again, this theme, and we are interested how all these interactions can be realized in the nanocomposite in with molybdenum disulfide. We obtained mass spectra both in positive and negative ion mode, and I will advance about negative ion mode. It contains typical molybdenum disulfide clusters, but as in case of polyethylene glycol, larger clusters were suppressed due to functional limitations, but not to such extent. And then we have observed several effects. At first, the expected one, oxidation of cysteine by formation of the sulfide bridges. We obtained a diamond in this system and corresponding peaks to the covalent diamond of cysteine in this mass. And there were such interesting peaks in mass spectra corresponding to cysteine with an extra sulfur atom. We made an assumption concerning possible weakness of this effect. That in this case, our cell is bound to sulfur at the edges of our molybdenum disulfide nanosheets, and then in the sputtering, the sulfur is extracted, cleaved from the sheet. If a handmade scheme to confirm, it was necessary to perform quantum chemical calculations, and it was performed by our co-authors by the quantum chemical calculations. But before showing the results, I would like to demonstrate the scheme from crystal maker side, which shows that the diameter of molybdenum atom is much larger than the radius of sulfur and other small elements. Here is the result of calculation in the ball and stick model and in space filling model. This account is radius ratio of the elements. And you can see that namely in this case, the number of calculations different configurations, but namely in this case, it can be seen that sulfur atom is extracted in the nanosheet. Compared with the bond length, distance between atoms, this is the standard distance between sulfur atoms, and here is which is larger in more this cysteine leading one continuity. And one result of such cleavage is that the consequence of removing of atoms from the edges is that the edge structure becomes distorted, and this made possible a cleavage, a liberation of single molybdenum atoms. And we have a corresponding molybdenum growth effect in our atmosphere. This effect is observed for the first time, as far as I know, it wasn't a report liberation of molecules in the nanosheets by. And the next one effect is known from the literature, healing effect of steel compounds. Alpha atom of steels can substitute so-called at the effect left of alpha atom at the surface of the molybdenum nanosheet. And decrease such then under laser disruption, this remaining part of the system can be dissolved. And indeed, we have corresponding in our mass spec. So this is how connection. Adoption must separate clear information, give us information, reflect the following effect in the molybdenum 15 nanocomposite. It is oxidation of 15 diamonds promoted by catalytic activity of molybdenum disulfide, leaving of alpha atoms from molybdenum disulfide due to edge binding or 15 and resulting molybdenum ion liberation and healing of defect by 15. And the last two slides, please, the next one, we will do one more class of compounds. These are nitrogen bases of nucleic acids, in particular C derivatives, which are used with medicine. And here, their derivative is also fuel compound. So in the mass spectra, we have molecular ion of the nitrogen base and equivalent oxidation product, equivalent diene. In this case, we also have a cluster of our nitrogen base with disulfide. And here along the modeling results, in this case, non-covalent interaction of our nitrogen base with the surface of the nanosheet can take place, and in the molecular ions are dissolved in this case, and there can be interaction, covalent interaction at the edges. Unfortunately, we are unable to calculate this dimerization process by that chemist to a large system and no possibility to move a chemical reaction. The next slide, please. So, general conclusions that total picture of laser disruption ionization mass spectra of the composites of molybdenum disulfide transuranic correlate with the processes in the composite. There is a systematization for these several types of compounds. Molybdenum disulfide polymer, in this case, no change in the mass spectra, they absorb which leads to non-covalent van der Waals interactions in such systems in such composites. In the spectra of molybdenum disulfide with organic dye and some other organic salts, abundant cations will produce H2 absorption of organic compounds on partially negative process of molybdenum disulfide, that is columbic interactions. And in the case of molybdenum disulfide with seals, I have shown only several examples, but reflected that with 10 various seals, so we detect the product of versatile non-covalent and covalent interactions, which occur due to catalytic and reductivity of molybdenum disulfide. And the last slide, please. Thank you very much for your attention.
Okay, we have one question in the conference hall.
Thank you very much for your presentation. I saw one example of healing of molybdenum disulfide surface, but other compounds are had two sulfur atoms in it and connected to the structure of molybdenum disulfide. Can they too heal the surface if they are absorbed with a laser?
Thank you for your question. This process is characteristic mainly for seol compounds, so it's necessary to have SH group. For example, our methylene blue heterocycle has sulfur in its composition, but it's bound in the cycle and it cannot penetrate into this simply sterically, and maybe electronically, of course, it can be cleaved from the heterocyclic structure. So it's characteristic mainly for seols, and it's stated in the literature. Seol compounds are used for this healing.
Okay, so thank you once again for the presentation. We should move forward according to our program to the next speaker, Professor Olena Lavrinenko, on-site speech from the Francevich Institute of Problem of Material Science of Ukraine. So, here is your microphone.
Dear Chairman, dear members of organizing committee, dear colleagues, thank you very much for invitation and for opportunity to present the result of our work at the NANO-2025 conference. In our presentation, we will talk about the specificity of the photocatalytic destruction of binary solution of organic dyes in the presence of titanium-based nanocomposite materials. Today, it is well known that the individual organic dye solutions are widely used for the testing of the photocatalytic activity metal oxide semiconductor materials. Especially the more often rhodamine B, methylene blue, malachite green, or orange are used as a model system. But the wastewater from food, laser, textile industry contains the more species in their composition. Hence, in the last 10 years, in the literature appears the publication where the binary organic solution were used for the testing the photocatalytic activity, especially the most widespread couple pair of organic dyes are methylene blue rhodamine B, methylene blue orange G, and rhodamine B, orange G. In the publication, the author at the author's opinions, the most important factor influencing the efficiency of the dye destruction from binary system are the difference in the molecule size and sorption process on the surface the photocatalyst as well. And another difference maybe lies in the presence one or more other bonds in the composition of the molecules. Another factors may be pH values, the concentration of the molecules, solutions, the mass of photocatalyst, and duration of the process, etc. The next slide, please. Thanks. In the aims of our work is to study the photocatalytic destruction binary organic dyes solution in the presence of titanium-based nanocomposites. We try answer the several questions. First one was the competition between the dyes molecules on the surface. The second was formation the new species within the interaction of organic molecules in the solutions, influence composition, chemical composition of the photocatalyst on destruction, and comparisons the destruction of the solution of the molecule, organic molecules from individual solution or as part of binary systems. The next slide, please. Also, for the performing this study, we selected 3 types of photocatalysts. There was titanium oxide formed by transformation, decomposition of metatitanic acid. The second composite was binary composites titanium dioxide doped with gold, with weight percent 0.2 weight percent of gold. This structure was obtained by transformation titanium tetraisopropoxide in the presence of aurum hydrochloric acid in the weak alkaline medium, and the precipitate was heat treatment at 600 degrees within 2 hours. And the third system was ternary system, titanium dioxide doped with nanoceria and argentum. This composite was formed by transformation of titanium tetraisopropoxide in the presence cerium and argentum nitrates in the alkaline medium in the presence of auxiliary substances, and the precipitate was heat treatment at 600 degrees within 2 hours. A brief characteristic of the nanoparticles was performed by XRD data, SEM-EDS data, and charge of 0 point that will be important for photocatalytical study. Model solutions 1-to-1 binary systems. We use 2 cationic dyes, methylene blue and rhodamine B, and 2 anionic dyes, orange methyl orange. The slide shows the molecular structure of these dyes, and on the photo we show we present the solutions, individual and the solutions, and binary their binary composition. The photocatalytical study was performed according to standard methodic. We selected 100 milligram of photocatalyst and add 80 milliliter of the individual organic dyes on 40 milliliter of one dye and 40 milliliter of second dye. The mixture was stirred in the dark 40 minutes to achieve sorption-desorption equilibrium, and the photocatalytic particles was removed by centrifugation process. And the UV visible treatment duration was from 5 to 110 minutes, and the optical density was measured using UV visible near spectrometer in the range of wavelength from 200 nanometer to 800 nanometer. Next slide, please. The mathematical data processing was performed using standard equation, the degree of decolorization of the solution, a rate constant of the destruction from binary dye solution. Yeah, I think we will know this equation. Next slide, please. The composition and structure of the powders. According to X-ray diffraction data, only anatase structure was formed in the system. The doping species not appears on the XRD patterns because the low concentration of the species. In the ternary system, the weight percent of the doping species was 2. This is very low and not appears in other phases. Some images show that the particles form fragile aggregates that are easily destroyed in the solutions of the dyes. The coherent scattering region or particle size, primary particle size was in the range from 8 to 10 nanometer. According to EDS data, except the titanium and oxygen in the structure of titanium dioxide, poor titanium dioxide were present sulfur, and in binary systems, the additional species was carbon and chlorine, and in ternary system, potassium, natrium, and nitrogen. The difference of these particles, the main difference in these particles is charge of 0 point. In neutral solution of the dye, the titanium dioxide particles have weak negative charge, but the binary system titanium doped with gold have big negative charge, whereas ternary system have weak positive charge. And the band gap energy of the particles is close to standard for anatase, 3.2 electron volt. Next slide. And this slide summarized the result of our previous work when we studied the catalytic absorption photocatalytic activity of the structures chosen for our experiment, but experimental part, but in the presence of individual dyes. As we may see, all particles show the slow absorption activity of the solution in the presence of binary system anatase doped with gold is 28% within the mixing in the dark absorption process. And for ternary systems, this percent is very bigger, larger, and 50% of methylene blue was sourced on the surface of the ternary system. And on the slide presents the roles of the photocatalytic activity in every photocatalyst for all chosen dyes. The next slide, please. This slide shows typical UV visible spectra, all dyes selected for our experiment for creation of binary systems. In all UV visible spectra, the peaks, strong peaks in the range from 400 to 600 nanometers corresponds to chromophore part of the dye. These peaks are characterized as the azo bonds in the systems. Then peaks close to 300 nanometer and 250 nanometer corresponds to naphthene and benzene rings, hence aromatic part of the dyes. It will be noted that for anionic dyes, the chromophore peaks are very wide, and hence, it is the same. Hence, we cannot use this mixture to estimate the effectiveness destruction one or another anionic dyes. The next slide, please. Okay, photocatalytic destruction of methylene blue and rhodamine B from the mixture solutions. The slide show UV visible spectra of the dyes degradation. Below are present the degree of decolorization of the solutions, the residual concentration of the dye, the kinetic constant, and the degradation efficiency coefficient that taught about the degradation one or another dyes in the solutions. As we may see on this picture, no another peaks appears except the methylene blue and rhodamine B. Hence, we may told that no new species appears in these systems. No, there was no new species was observed in these systems. For titanium tetra. For the poor titanium dioxides, the contact with mixture molecules with mixture shows that rhodamine B faster degradation than methylene blue, and the coefficient degradation efficiency coefficient get 0.77. And in another system, we may see this close the same results, but the coefficient is the 0.8 much larger. And for the last picture, when the ternary system interacts with the mixture of the organic dyes, we may see the different picture because there is the sorption process is more strong, and in 5 minutes, close to 5 minutes, all methylene blue sorbed on the surface of the nanoparticles, and in this time, 12% of rhodamine B was removed from the solution, and the process, catalytic absorption process, stopped. Okay, the next slide, please. In this slide, the next slide demonstrates the photocatalytic decomposition of the one cationic, one anionic. Not that. Okay, thank you. One anionic and one cationic dyes, methylene blue and orange G in the system. In this case, in the presence of anatase particles, the rate of degradation of methylene blue and methyl orange is the close, and the degradation efficiency coefficient is close to 1. But for another system, methyl orange degradation rate of degradation methyl orange is faster, and in this in first case degradation coefficient is close to 1.08, and in the second case it is lower and get to 0.4, close to 4. And the last slide Yes. The last slide shows the presence, the example, the system where the degradation, when the estimation of the influence one or another die is impossible because the peaks form a hide hollow and it is impossible to select it one or another. There is the system, as I told below, above, methyl orange G anionic dyes and rhodamine B with orange G, rhodamine B with methyl orange. It is impossible. And above you may see the UV visible spectra of methyl orange. Within the process of photocatalytic degradation, methyl orange may change his molecular structure and transfer from initial medium, it is yellow form, and the peaks located at the wavelengths 464 nanometer. But in acidic media, the methyl orange get red form, and the peak transferred to the wavelength close to 500 nanometer. And conclusion. In conclusion, we may tell that the in binary system no new species appears in the system. Hence, interaction within the dice molecules not appears. And the methyl orange may change his molecular forms, and the competition between molecules in the system depends on the chemical composition of the dye and structure of the photocatalyst. And efficiency of dye degradation from individual solution and as part of binary system is different, and depending on the composition, chemical composition of the dye, charge, electrokinetic properties of the particles, and chemical composition of the dyes. Thank you for your attention.
Okay, thank you very much for the interesting topic. Do we have any question in our conference hall? Okay, we have no question yet. So thanks once again. And we will move to our next speaker, Professor Anatoly Yevtukh, who will present his presentation online from the Lashkarev Institute of Semiconductor Physics of NAS of Ukraine. Professor Anatoly, are you with us?
Yes.
So we are ready to see your presentation.
Okay. Just a minute. But I can't share my presentation because something else is sharing.
Okay, we can share it for you. You have sent it to us previously, so you will just need to tell us when to switch the slide, okay?
Okay.
One moment.
Okay, let's.
Okay, if you can see the presentation, then you can start.
Yes. First of all, dear colleagues, I would like to thank the organizing committee for possibility to present result of our investigation. The title of my report is Frequency and Voltage Dependence of Negative Capacity in the MIS structure with Nanocomposite Ferrum Oxide Film. we obtain this result, joint investigation in Institute Lashkarov, Institute of Semiconductor Physics, and Shevchenko National University. Next slide, please. A short outlook of my presentation, introduction, film preparation and measurements, structure and content of the film, negative capacitance effect, dielectric property of the film's model, and conclusion. Also acknowledgement. Please, next slide. Introduction. As to negative capacitance effect, in this case was observed in many classes of devices in the under investigation different authors. One type of devices is forward bias rectifying device. Another two-dimensional electron-hole hazes where exchange correlation determines the physics. Another one is a metal insulator semiconductor device with ferroelectric gate dielectrics and dielectrics, and another is also the semiconductor insulator device, metal semiconductor device, insulator semiconductor with nanocomposite film. And as a rule, this effect very interesting and sometimes is unusual. But next slide, please. Why we investigate this effect and why negative capacitance effect is so interesting and important. First of all, interest to this effect is caused by we obtain new fundamental knowledge about interaction electric field with matter, dielectricity. And another, of course, is main interest practical application in electronics. First of all, it's high frequency electronics. Negative capacitance is equal to inductance. In modern high frequency electronics, in high frequency amplifier and receivers, as a rule, for realization of inductance, use the Archimedes coils. But as we can see on this photo, the Archimedes coils spend a large area on the chip of integrated circuits. It is very attractive to exchange large Archimedes coils by thin film with the same inductance. It's one of the idea for practical application. And another one, next slide, please. Another one is application in nanoelectronics. You can see here the structure of usual field effect transistor based on metal insulator semiconductor. But as you know, nowadays the modern nanoelectronic chips contain more than 1 billion transistors per chip. And nevertheless, one transistor consumes low energy, but due to huge quantity of the transistors, the consumption energy is high enough. And the problem is to reduce the consumption energy in modern nanoelectronic transistors. And in this case, it's very important to use one of the most idea to use negative capacitance effect. To reduce consumption of energy in most transistors, it's necessary to increase the speed of switching from on-off states. But in any case, this transition from on-off stage must be as fast as possible. And it's characterized subthreshold current in current voltage characteristic of the transistor. But subthreshold current has to be as low as possible. But this is value which defined the reciprocal threshold current and slope of current voltage characteristic. And in general case, this reciprocal value of slope of subtraction current have such expression. But as was demonstrated in conventional transistor, it is no possibility to reduce this value lower than 60 millivolt per decade. It's so-called Boltzmann limit, 60 millivolt per decade. But to overcome this limit and in such a way to reduce the power consumption by integrated circuits was proposed a different approach, type realization of transistor, field effect transistor, but main approach among them is this is Boltzmann limit. Lower is based on using negative capacitance, tunneling field effect transistor, and combined tunneling and negative capacitive field effect transistor. As you can see in this equation, if in our case here we can capacity of the semiconductor, capacity of the insulator, if the capacity of the insulator will be negative, this value will be lower and subtraction result will be higher, more sharp. In such a way, the main idea using negative capacitance in electronics is to reduce power consumption, and negative capacitance structure with negative capacitance allow to realize such approach. Next slide, please. But under investigation, most attention is attracted for ferroelectric dielectric. Ferroelectric, such as ferroelectric based on hafnium oxide, zirconium oxide, also two-dimensional molybdenum disulfide is considered, but ferroelectric is so-called non-linear dielectric. But we observe negative capacitance effect in case of linear dielectric, not ferroelectric, namely in iron oxide. The film preparation. We obtain our film iron oxide by physical deposition technique, namely ion plasma sputtering. The argon ions bombard the target, in our case is iron, sputter the atom from the target, they move to the substrate, we add some oxygen to the chamber and form a silicon iron oxide film on the silicon substrate. We investigated two types of structure. One of them as prepared, initial, and another was annealed at temperature 1000 degrees centigrade. The thickness of the films were 46 nanometer. For such structure, which we investigate, metal insulator semiconductor structure is a capacitor. We use measure the capacitive voltage characteristic, measure impedance of the structure, and obtain some interesting result. Next slide, please. No, but first of all, we investigated the structure and content of our film. Among the iron oxides, the three most important polymorph are investigated and separated is hematite, magnemite, and magnetite. We investigated this film by using IR spectroscopy, FTIR spectroscopy, and reveal such interesting peculiarities. As deposited film has hematite-like structure. Our film were amorphous. After thermal anneal, the structure is more magnetite structure became. And we observe also such peaks which we analyzed. It conclude such transition of the structure during the annealing. Relation of iron to oxygen was 4.74 weight%. We also investigated, next slide please, this material by XPS spectroscopy, but in this case we observed that this spectral demonstrates that very small content of ferro nanocluster. Next slide, please. Measurement the capacitor voltage characteristic, we observe such behavior. This is initial film. We measure capacitance in condition accumulation safest semiconductor by main carriers. We observe such behavior as a low voltages. We have the positive capacitance, but then transition to the negative capacitance. The parameter here is the frequency of testing signal. The higher peak is correspond to the lower frequency. We can conclude that intensity of the peak decrease with increasing the frequency and observe transition to the negative capacitance as frequency is lower, the voltage for transition is also lower. This is behavior in case of annealed film. Here we draw the dependency of the voltage transition from positive to negative capacitance dependence on the frequency. Yes, one K1 is for initial film, and red curve is for annealed film. We can see that after annealing, the transition to the negative capacitance is realized at lower voltages. Next slide, please. We also using the simple expression for flat capacitor determine the dielectric permittivity. This behavior is similar because this relation is linear, but the dielectric permittivity, dielectric constant in our case changes from 6 to -6. And the similar for annealed film. Next slide, please. To analyze the behavior of polarization our film in electric field, we investigated, as I say, impedance of the film and determined the tonnage of dielectric losses for the initial field and for the annealed field. The frequency is a parameter. The frequency increase in this direction. We can conclude that at low voltages, the tonnage dielectric loss is higher for the initial field compared to annealed, but at high voltages, the relation is opposite. The dielectric losses for the annealed field is higher. Next slide, please. Here we demonstrate the dependencies of maximal capacitance, positive, on the frequency for the initial film and annealed film, tonnage dielectric losses for positive capacitance, initial annealed, and also dielectric constant, real part of dielectric permittivity, and loss factor is imagined part of the electropermittivity. Next slide, please. To understand the reason such behavior and appearance of negative capacitance of the electric losses, we analyze the conductivity of the film under investigation. Thus, the electric losses in the dielectric is called polarization and electrical conductivity. We investigated the electric conductivity of the film, the dependency of the conductivity, specific conductivity of the voltage demonstrated here for initial film and for annealed film, and we determine the electron transport mechanism. In case of initial film is space charge limited current electron transport. We analyze more details this mechanism, determine the concentration of the traps. It's more than 4.3 multiplied 10 to 17 power per square per cubic centimeter. So the quantity of the trap is high enough. It means there many defects in the films. In that case, we also analyze the dielectric losses caused by electrical conductivity. Next slide, please. We obtain such a relation of loss factor compared to the value obtained from the tangents dielectric losses. We can see that the electric losses caused by conductivity is 2 orders lower than by polarization. So we can conclude that in case of low voltages, the dielectric losses mainly caused by polarization. But at high voltages, the conductivity play a more important role. But we estimated such loss factor, imaginary part of dielectric polarization, dielectric permittivity, we put into such equation, specific conductivity, frequency, and constant of the dielectric permittivity of the vacuum. And we demonstrated such behavior of this value on the voltage with the frequency as a parameter, and we can see that dielectric loss factor increase with the voltage, demonstrated in such way significant role of the conductivity in such film, because our film is not ideal. Next slide, please. Or how can we explain the negative capacitance effect? In case of positive capacitance, according to relation, capacitance is more than 0, is differential charge on voltage. In this case, as a rule, this demonstrated on this picture, the vector electric field, applied electric field, and polarization are directed in the same collinear, in the same direction. As you know, the vector polarization is from negative to positive. On the another side, the electric field with positive to negative. But in case of negative capacitance, we have such relation. We have negative capacitance. In this case, negative capacitance realized when increase in the charge leads to the decrease in the voltage, or vice versa. In our case, we demonstrated on this picture the vector of polarization in electric field directed opposite. In this case, the inner induced electric fields enhance the applied outer electric fields. And in this case, the dielectric constant is negative. Next slide, please. And we explain such behavior by delay in the polarization. We can see to more detailed analysis, allow to consider the current density through the dielectric and applying the voltage, which include the conduction current and also Maxwellian displacement current. And with here we have time of relaxation. Next stage, next slide, please. And analyze our structure, we obtain such expression for equivalent circuits of the capacitance. Here you will see the surface thickness of the capacitor, specific conductivity, Maxwellian displacement current, and average relaxation current. But we estimated the Maxwellian dielectric relaxation time and time of average relaxation time. According to this equation, we estimated Maxwellian relaxation time, and here we can see this such behavior. The value is 10 to -5, -6, -5. And if, according to this equation, in case is Maxwellian relaxation, dielectric relaxation time is lower than average dielectric relaxation time, in this case, the capacitance will be negative. So we explain such behavior, namely the delay retardation of polarization behind the applied voltage. Next slide, please. So in case if Maxwellian dielectric relaxation time lower than average dielectric relaxation time, negative capacitance. Here the data obtained from the literature about relaxation time in some dielectrics independent on polarization mechanism. Dipole polarization 10 to -5, 10 to -7, thermal activated ionic polarization, thermally electronic polarization, and more slow is phase charge polarization 10 to 3, 10 to -3. So we may conclude, according to our obtained value for Maxwellian dielectric realization time, that in our case, average dielectric realization time is larger than Maxwellian dielectric realization time, and the reason is delay polarization against the applied voltage. Next slide, please. As a conclusion, initial ferrum oxide, iron oxide field is amorphous, mainly hematite structure. During thermal release, transform into magnetite structure. Negative capacitance effect was revealed in non-stoichiometric film in mixed structure with such film as prepared and annealed. Transition from negative to positive depend on the frequency and applied voltage. The lower frequency, the lower voltage to transition from positive capacitance to negative capacitance. In case of annealed field, the transition from positive capacitance to negative capacitance is realized at lower voltages. Next slide, please. And the electric losses at low voltages are mainly due to polarization and are higher for iron oxide film initial. But at high voltage, they are mainly due to conductivity and are higher for annealed iron oxide film. And model is proposed to explain negative capacitance, which is based on the polarization inertia. Next slide, please. This investigation was supported by the project of National Research Foundation Ukraine. And next slide, please. Thank you for your attention.
Okay, thank you very much for the presentation. Do we have any question? Yes, we have one question.
Okay. Thank you very much for your interesting presentation. I have one question about the mechanism phase transformation hematite to magnetite. What forces influence this process? Thank you.
We observe by X-ray diffraction that initial film is amorphous, but after annealing, we determine this that initial film is hematite structure based on analysis infrared spectra. Typical peaks are observed at typical frequencies. But investigation in X-ray diffraction allows to observe the crystalline inclusion of hematite inclusions. In this case, we also, based on analysis of infrared spectra, conclude that in our case, we observe some peaks near 1070 reciprocal centimeter. This peak is related to ferrum oxide silicon or silicon oxide silicon bonds. In our case, the transition from hematite iron oxide to magnetite, during this transition, the oxygen is released and at the temperature is promoted to some oxidation of the silicon substrate in our case.
My questions was about the phase transformation because it is well known that under the condition of hypergenic condition in the presence of oxygen and water and in our environment, magnetite may transform to hematite at temperature 200, close to 200 degrees, and the process transformation hematite to magnetite is impossible because I asked about that. And I think X-ray diffraction may show that, but I think more useful was Raman spectroscopy that may tell the transformation magnetite to manganese due to the oxidation of ferrous cations in the structure, crystal lattice. And then the magnetite may transform to hematite, but in other process, it is impossible. Thank you.
But we analyzed this transition based on the analysis of thermodynamic Gibbs energy, and at the temperature of 1000 degrees centigrade, it demonstrates the possible transition from hematite to magnetite.
Thank you very much for the interesting question, interesting answer. Thanks again for our speaker, Anatoly Yevtukh. We will move forward according to our program. Here's right in coffee break, but we're a little bit shifted in time. So if you want coffee, you can just go and take it and then return back to our conference hall. But we will, without any interruption, move to our next speaker, Dr. Karina Valihura. I can see her in our Zoom, but if you are here, please tell us. Okay, okay, I can see. So if you are ready, you can share your screen with us.
Let me try. Is that? Oh yeah. Oh my God. What is that? Nano. Ой. Share. Is that sharing?
We still waiting 1 moment.
Yes, I'm not watching.
Yes, we can now see the presentation.
Yeah. Oh, where is that? Oh, sorry, I'm lost.
We see the presentation.
Oh, sorry. Okay. Hello, everyone. The title of my work is Gallium Palladium Magnesium Aluminum Oxide Catalyst for the Gerber condensation of ethanol into butanol and higher alcohols. For the beginning, log for the obtaining of the numerous substances valuable in the industry, in particular one butanol. One butanol now is considered as one of the most prospective biofuels. It is more preferable compared to ethanol because of higher energy characteristics. To realize a conversion of ethanol into butanol, it is possible to use the process of Gerber condensation. It consists in the doubling of the carbon chain. It involves the steps of dehydrogenation, aldol condensation, dehydration, and reduction with the
Karina,
formation.
thank you. Sorry for interruption.
Yeah.
Did you switch any slide? Because we still see the first slide.
Oh, I absolutely switch. I don't know. I'm watching my second slide.
Probably you're sharing with us the wrong windows. You're sharing with us. You can stop sharing and then choose the right windows where the second slide is already shown.
Oh, my bad.
Now we can see second slide. So you can work here.
What to do?
If you already understand how to switch the slide, now we see the second slide. Probably we can test and click on third slide. Will we see it or not?
Oof.
Can you please?
Yeah. Oh, wow. Wow.
Probably you can do it by arrow
I don't
on a
know.
keyboard.
Yeah, that's exactly. Is something moving?
Your mouse is moving on the screen.
Oh my God. Wow. Do you see? What do you see? I'm sorry.
We can see the second slide.
And now?
And now?
Also the second.
Yes.
Oof, because I'm clicking on I don't understand.
Stop sharing the screen and try once more.
Oh my God, I'm so sorry.
What's happened?
How to stop sharing the screen?
I stopped it for you, please.
Yeah, thank you.
Once again.
Oh, what a shame.
Don't worry, it happens with everybody.
And now?
Now we see a presentation and the first slide of it.
Oh
Please
my
try
God.
to go through the next.
Do you see that I'm changing something? Because I'm clicking slides. I'm really clicking slides.
Probably you changed the slide, but not in the screen that you share with us.
Oh.
You share with us the screen with not full screen mode presentation.
Wow.
when you try to share the screen, you should choose that one that is already with full screen mode. It will work properly.
And now?
And now we can see only your eyes, eyebrows, hair.
Amazing.
Part of ear. Eyes disappeared. Aha, yeah. You can see a very big palette of emotion, the visions of fear, despair, and doubt.
Great.
Probably you can send it to us via email and we will share it for you. You will have 5-10 minutes to do it, and we will give the floor now for the next speaker, and then resume
Yes,
back.
of course. Thank you. Thank you.
Okay, please send it to us via email now. Okay, and our next speaker is PhD student Edita Vlażlowska from Maria Curie Skłodowska University, Poland. Edita, are you with us?
Hello.
Okay, can you please share the presentation with us?
Yes, of course. Can you see my screen?
Yes, in full screen mode. So I kindly invite you to make a presentation. We are waiting.
You can see my screen? Good. Yes?
Yeah, it's in full screen mode, so please start.
Okay. Good afternoon, everyone. My name is Edyta Wlazłowska, and I am a PhD student at Maria Curie Skłodowska University in Poland. Today, I will talk about the electrochemical determination of europium using a carbon nanomaterial electrodes. Let me start with a few words about europium. It is a very reactive metal, the less dense and the soft among the lanthanides. In the Earth crust, it occurs only in small amounts, about 2.1 ppm. Europium has 35 no isotopes, but only 2 are stable. The main europium minerals are monazite and bastanazite. This slide shows the basic physicochemical properties of europium. As you can see, this metal has low mechanical strength, a relatively low melting point, and a moderate boiling point. It is not very resistant to corrosion, but it has medium electrical and thermal conductivity. An important point is that europium is considered relatively non-toxic, which makes it different from many other heavy metals. Europium are relatively rare in nature. That he plays a crucial role in modern technologies. Is one of the key elements. It is used in liquid crystal displays, television, smartphones, and even in energy saving fluorescent lamp. Europium ions are responsible for the characteristic red color on screens. Thanks to its fluorescence, europium is also applied in emergency signs, luminescence paints, and in the security features of euro banknotes. So Europe are indispensable not only in chemistry but also in electronics, opticals, energy, and even financial security. Because of the increasing application of europium is present in the environmental may also rise. although europium is not considered high toxic, its accumulation in water and soil can disrupt the biological balance, especially in a sensitive ecosystem. This is why we need a sensitive and selective methods to monitor europium in environmental samples and to assess the potential contamination risk. In the literature, many procedures for trace metal determination, including lanthanide, are described using different instrument techniques. Among them, stripping voltammetry is one of the methods that can be successfully applied to europium. Stripping voltammetry is an analytical technique that combines two steps: the accumulation of the analyte on the electrode surface and its subsequent electrochemical determination. This approach allows us to reach very low detection limits. The method is relatively inexpensive, fast, and simple to use. What is most important, it can be applied direct to environmental samples without any pretreatment. In this picture, we can see a scheme of the measurement system. The core of the experimental is a 3 electrode setup consisting for a working electrode, a reference electrode, and an auxiliary electrode. This configuration makes it possible to precisely control the potential of the working electrode while the current flows between the working and the auxiliary electrode. Meanwhile, the reference electrode provides a stable voltage reference, which is essential for accurate measurement. To improve the sensitive and selective of europium determination, we applied a composite electrode prepared by mixing two carbon materials, multi-wall carbon nanotubes and spherical glassy carbon. Carbon nanotubes provide excellent electrical conductivity and a very high surface area, which facilitates efficient analyte absorption. In turn, spherical glassy carbon ensures both mechanical and electrochemical stability. The combination of these two materials result in an electrode with an increased activity surface and high electrochemical activity. This made it possible to lower the detection limits and improve the analytical parameters of this adsorptive stripping voltammetry, including linearity and signal reproducibility. The determination of europium ions was carried out using adsorptive stripping voltammetry with a carbon nanomaterial modified electrode. We prepared of the measurement solution. I use acid buffer as the supporting electrolyte, kupferon as the complexing agent for europium, and lead ions as the electrode modified. The procedure consists of two key accumulation steps. In the first step, at a potential of minus 2.4 volt for 20 seconds, a thin lead film is electrochemical deposited on the electrode surface. In the second step, at a potential of minus 0.6 volt for 16 seconds, the europium and kupferon complex is adsorbed onto preformed lead film. After the accumulation stage, the stripping step is performed. It consists of a linear potential scan from minus 0.55 volt to minus 1.1 volt, while recording the peak current corresponding to the oxidation of europium ions. The developed procedure with a carbon nanotube modified electrode enable the determination of europium ions with a detection limit of 1.3 nanomole per liter. Such a low value clearly demonstrated the high sensitivity of the method. In the picture, we can see a calibration curve show excellent linearity. And the correlation coefficient confirms both the accuracy of the linear model and the high precision of the measurements. Therefore, the developed method can be considered reproducibly and well suited for analytical application and a trace europium concentration. In order to optimize procedure, achieve a low detection limit, it was optimized. Kupferon concentration of lead ion, accumulation time and potential time for lead film formation, accumulation time and potential for europium kupferon complex. This slide present a comparison of different adsorptive stripping voltammetry procedure used for europium determination. This procedure differ in the type of working electrode as well as in the choice of complexing agent or surface modifier. As shown, our electrode, a carbon electrode modified with lead film and multi-wall carbon nanotubes, achieve one of the lowest detection limit, which demonstrate its high analytical sensitivity. Only the mercury electrode provide a lower detection limit. Therefore, the developed method combine the advantages of high selectivity and sensitivity with simplicity and practical applicability, both for environmental analysis on routine quality control. In this slide, we can see to practically verify the developed adsorptive stripping voltammetry procedure for europium determination. We perform analysis of both certified reference materials and real samples of natural waters. The samples were analyzed without prior mineralization. The solution were introduced directly into the voltammetric cell after dilution without the supporting electrolyte. For the reference material in which europium were not original present, known amounts of this element were added, and the standard addition method was applied. The recovers obtained for europium from 96 to 104%. This result clearly confirmed the high accuracy, selectivity, and reproducibility of the method. Importantly, the determination were successful both in simple and in complex matrix, which proves the applicability of this procedure for environmental monitoring, including unprocessed samples. To conclude, the developed adsorptive voltammetry stripping procedure with a carbon nanomaterial modified electrode proved to be a highly effective for europium determination. We achieve a detection limit in the nanomolar range, which demonstrate the high sensitivity of the method. The use of kupferon as a complexing agent provide excellent selectivity. Importantly, the method is sample inexpensive and can be applied directly to environmental sample without pretreatment. Finally, the procedure was successful, verified on real water samples and reference materials, which confirms its potential for practical application. Thank you for your attention.
Thank you very much for the interesting topic. Do we have any question? I can see question in the hall, and because of the really tough deadline with our conference, we will move to the next speaker. So thank you once again, Edita. And we received the PPT from the Dr. Karina Valihura, and can now try once again. Now I will share it for you, and you will just tell us when we should switch the slide. In one moment. Will be. Yeah.
Yes. Sorry for delay with the presentation. Again, about the gallium palladium modified magnesium aluminum oxide catalyst in the Gerber condensation. So you can change the slide, please. So as I said, ethanol could be converted into 1-butanol using Gerber condensation, which consists in doubling of the carbon chain. And the main steps, like the key steps of this process, are the first and the second, dehydrogenation of ethanol and aldol condensation. Catalytic systems under study, the most common one are calcium phosphates and mixed magnesium aluminum oxides. And depending on the modifying additives, we can enhance those key steps of the process. Usually rare earth elements, in this case we use gallium, give improvement of acid-base properties, intensifying aldol condensation, and like transition metals like copper, nickel, and in this case palladium, they give enhancement of redox properties, increasing ethanol conversion. Next slide. In Institute of Physical Chemistry in Ukraine, it was made a very systematic study about magnesium aluminum oxide systems in the Gerber condensation. Like based on them, we know the best ratio of magnesium aluminum in the catalyst, and we developed a better improved method of fast synthesis of hydroxide precursor for magnesium aluminum oxide systems. In the like the drawback, like the weaker properties of those catalysts, these are not enough, pretty low conversion of ethanol and low stability usually. Next slide. and you can start the video, I think. That's why those additives were used. Hydroxyl sites not working. Недоступно.
Probably the video didn't work, so unfortunately, we can
Sorry,
just
but
explain.
at least there was at least there is a full picture that the systems they being synthesized by co-precipitation methods with nitrates of magnesium, aluminum, gallium, and in case with palladium also with sodium hydroxide. They've been dropwise implemented in the buffer solution with the control of pH, and resulting hydroxyl sites, they've been calcinated to have oxide catalyst. Next slide. Could we have? Oh, thank you. As I said, like these hydroxyl sites, they show the typical in XRD the typical reflexes of this mixed hydroxide system based on magnesium aluminum, and after calcination we have the mixed oxides. The main signals, the main reflexes, they correspond to magnesium oxide. We don't see separate phases of aluminum and gallium. They are supposedly very highly distributed, and some signals of palladium oxide nanoparticles we see. From the analysis of nitrogen absorption desorption, we see that the materials are mostly mesoporous, and we see the small decrease in the surface area with introduction of gallium and palladium. Next slide, please. Characterizing with ultraviolet visual diffuse reflectance spectra, we see the signals. They are typical to beta gallium oxide nanoparticles, which we were not observing on XRD, and also same we see palladium oxide nanoparticles, and additionally with XPS analysis we can see additionally the signals of phased palladium O2 oxide. Next slide, please. By a thermoprogram desorption of ammonia and CO2, we studied the acid-base characteristics. All the sites, they've been assigned into 3 groups. Into four groups depending on the temperature of desorption. They like weak, moderate, strong. We see that the addition of gallium palladium leads to a slight redistribution of the strength of the acid-base sites on the surface. And for magnesium, aluminum, gallium, total concentration of acid and base size increasing. For palladium, magnesium, aluminum, gallium, catalyst acidity is almost not changing, and basicity is decreasing. Next slide. In the experiments of temperature rising of the pre-adsorbed ethanol on the surface of the catalyst, two main products observed. They are ethylene and acetaldehyde. The ratio between them is different depending on the sample. It is indicating the ratio between strong acid and strong base sites. And for magnesium aluminum catalyst, the appearance of diethyl ether is registered. Butanol in the presence of palladium, magnesium, aluminum, gallium forms at comparatively lower temperature, and the formation of bifunctional active sites of dehydrogenation of ethanol and aldehyde condensation enhances the performance of palladium, magnesium, aluminum catalysts in the target process. Next slide. And also we did tests like more for more time in in different equipment. We tested also in the continuous catalytic experiment with the ramp of temperature 20 degrees every 44 minutes. Why 44 minutes? Because it's the cycle of a chromatographic analysis in the equipment. But we have like every point by point from 100 to 400. And we see that with addition of the gallium and then palladium, we see how temperature, like the temperature of the initiation of this conversion is going lower. So for palladium, the reaction goes at very mild conditions. So we even temperature 100 at 180, we already have 20% of conversion, which is for this kind of system, this is very high. And at those mild conditions, there are very few catalysts, they are able to do that. Next slide. As we see from all the results, like the palladium, of course, it was predictable that palladium additive gonna work, but in this process, we see that this additive gives very precious improvement, and we tested at other conditions. We know that at 200 degrees we have conversion, but it's pretty low, and like the bad thing that a lot of hydrocarbons, we have a lot of hydrocarbons there, which is not a target product. So what we did, increased pressure. In this case, for the Gerber reaction, increasing of the pressure of the process, suppressing suppressing the formation of hydrocarbons and leads to formation of butanol and Gerber alcohols. They are the products of the further condensation, like butanol, which we received from ethanol, again reacts with ethanol or butanol with butanol, and we have other higher alcohols, 2-ethyl 1-butanol, 1-hexanol, 2-ethyl 1-hexanol, octanol, and even higher sometimes. But they are also very, very precious, and they are even more expensive comparing to butanol. And if we a little bit increasing temperature to 250 at higher pressure, we receiving big jump in conversion, and what we see, this conversion and selectivity, they are stable during 18 hours of the experiment. Here, what is shown 18 hours here, and even more that we know from the experimental data. And next slide. So as the conclusion, the gallium and palladium modified magnesium aluminum oxides, they've been synthesized for the first time, and for the first time they've been tested in the catalytic reaction, showing, especially this with palladium and gallium, showing very big increase in conversion and instability. Next slide. And we want to thank you, to the financial support of the Spanish government that gave grants to University of Sevilla and to the University of Malaga, where I did this work, and they gave support for Ukrainian scientists, given the opportunity to continue our work during the war. So without those grants, this work would be impossible. So thank you for your attention.
Thank you very much for the interesting presentation. Do we have any question? No, we have no question. Probably we are tired a little bit, but we have next speaker also, Dr. Valeria Zuzulya. She'll present her topic on site, and let's give her a floor.
Hi, everyone. First, I would like to introduce myself. My name is Valeria Zuzulya, and I work as a junior researcher at Taras Shevchenko University of Kyiv in inorganic chemistry department. The topic of my report is on the screen, please. The rapid development of laser technologies, white light emitting diodes, creates a strong demand for highly efficient phosphor materials. Particular attention is paid to the compounds which contain phosphate, tungstate, and molybdate matrices doped with luminescent ion. Such matrices have next facilities: high radiation and thermal stability, wide absorption, and high quantum yields. So the matrices in the excitation spectra of such matrices, besides the typical FF transition of luminescent rare earth elements, can you help? The wide asymmetric bands is often observed. This band corresponds to the energy transfer from the matrix to the luminescent ion. So it confirms the possibility of charge transfer from matrix to the luminescent ion. So the objects of this study are phosphors containing phosphate, tungstates, and molybdates obtained in single crystals or nano or micro powders. The aim of this work is to determine the optimal synthesis conditions for such phosphorus, then to establish the influence of activator concentration on the luminescent properties, and to perform the crystal chemical study, and also luminescent properties were investigated. So crystals and powders were obtained using two methods: the solid-state sintering method and melt growth. For solid-state sintering, the initial compounds were grounded in stoichiometric ratio with a drop of ethanol. Then they were placed in porcelain crucibles and heated at 500 degrees for 5 hours. The mixtures were then reground again and sintered from 500 to 650 with 50 degrees increments and kept for 8 hours at each step. The process was monitored by infrared spectroscopy. For melt growth synthesis, the stoichiometric ratio of compounds were melted at the temperature of 1000 degrees and kept for 2 hours to achieve the homogenization. Then the melt was cooled down to 700 degrees and the melt was after that poured onto a copper plate, and the obtained crystals were washed with water to remove any residual melt. So crystals were studied by single crystal X-ray diffraction. The structure has a layered structure. Europium is located in 8-fold coordination environment. Europium polyhedra are connected by Europium polyhedra are building zigzag layers by being connected by common edges. Europium, the Europium O8 zigzags are connected by phosphate tetrahedra building layers, and then these layers are connected through tungstate tetrahedra, and potassium cations are located between these layers, acting as a charge transfer. Since this potassium gadolinium phosphate molybdate is isostructure, it does not require the detailed description. So using the continuous shape measure method, coordination polyhedron was calculated. The bonds are grouped in pairs, but the S value of 2.7 for gadolinium and 2.9 for europium still shows that the deviation is significant from triangular dodecahedron. In the infrared spectra of compounds, there are bands corresponding to phosphate, tungstate, and molybdate tetrahedra. The luminescent spectrum of europium compounds has typical FF transitions of europium 3+ with strong red emission. The absolute quantum yield was measured in an integrating sphere, and with an accuracy of 0.5, the value under direct excitation is close to 100%. So Later, we tried to obtain phosphorus using less europium. So we consider a framework, this framework where bismuth was substituted with a fixed amount of gadolinium, which was 1 mole%, and with europium in the range from 1 to 30 mole%. The confirmation of the formation of solid solutions is confirmed by infrared spectra and powder X-ray diffraction. In the excitation spectra, there is one band which corresponds to gadolinium excitation band, which confirms that gadolinium takes part in absorbing energy and transferring it to europium. So another approach we tried to use to increase the efficiency of the luminescence was to partially substitute potassium with cesium, since the cesium has a larger ionic radio. So the absolute quantum yield was 4.4 for the compound where X was equal to 0.5. And it's important to note that the amount of europium did not exceed 1 mole% in all samples. So the relative quantum yields measured from the excitation spectra appeared a bit higher, but the general tendency was the same. The higher relative quantum yields we may explain due to not counting the sample's absorption while measuring quantum yields. The conclusions are presented on the slides. Thank you for your attention.
Thank you for your presentation. Any questions? We have no questions. Thank you again for your presentation. And now we have a special session, EU programs and instruments for support science and innovation. And the first speaker of this session, Dr. Olena Fesenko, General Manager of EN Ukraine Consortium, with report EU initiatives and projects. Central Ukrainian EDIH, Seeds of Bravery, EN for support innovators and startups for stimulate digital and green transformation.
Today's session we will structure and divide it in 3 parts. The first one, I will discuss more details about EDIH and Seeds of Bravery projects. And after this, Andrei will continue with AAC accelerator. And finally, Alexander will provide you a little bit more information about Enterprise Europe Network. Maybe you know, but our department continues to work in 2 main directions. The first one is research direction, and we have quite a lot of projects, international project, national project. As the rule, we provide different type of services, optical characterization of different type of materials. We work with very wide line of materials. It could be different type of composites, organic, not organic. Also, we are working with biological objectives such as different molecules, macromolecules. Also, we work with cells, skin, and others. Maybe several weeks ago, we work even with eyes. So it's quite a lot different activities. And as a rule, we provide expertise in spectroscopy. It's Raman spectroscopy, infrared spectroscopy, and optical spectroscopy. It's one line of our activities. Another one is support innovation and innovation ecosystem in Ukraine. We have quite a lot projects which are focused on support innovation, startups, and cooperation between scientific and business area. And one of them is EEN, Enterprise Europe Network. You can see logo and banners here because this project support us during many years in organizing different events such as brokerage event, company mission, but also scientific events. For example, is this conference, we have special session, how to attract funding from different European resource programs. And if some of you wanted to prepare international project, for example, for Horizon Europe, you can contact with us and we will help you to find partner or can provide you advice how better to write this project. Maybe we will share with you experience what topic is better to include in the project, what is the structure, how to find correct partners or something like this. And so Enterprise Europe Network, who took part in our previous conference, I'm sure that you know about this network, and Alexander, he will share more information about it. I will focus more precise on other project. It's YEDIH, but I will provide you information maybe in 2 minutes. But I wanted also mention about Central YEDIH project. It is another project, and maybe you know that last year Ukraine created digital innovation hub network in Ukraine. Maybe better to say not create, but Ukraine joined to the digital innovation hub in Europe. And for this, in Ukraine were selected several organizations. Some of them it's universities, some of them it's institutes, some of them is Chamber of Commerce and other business support organization. All together, they built the consortium and provided different type of services. And now I will share a little bit more information about one of such YEDIH digital innovation central, namely Central Ukrainian YEDIH, which I represent as coordinator of this YEDIH. Next slide, please. Our YEDIH, because different YEDIH cover different region of Ukraine. Our YEDIH covers central part of Ukraine. From title, it is clear that it is Central Ukrainian YEDIH. It's mean that we cover central part of Ukraine. It's from Kyiv to Odessa, Poltava, Dnipro, and others. And we built the consortium. Our consortium consists of 6 partners. And now for the next slide, I will provide a little bit more about our services and our partners. Please, the next slide. And what's the main activities of EDIH? EDIH is have a general goal to attract digital technologies in science, innovation, in business, and our task to monitor different type of digital technologies which are on market and try to attract them and involve them in science process, innovation process. That's why we try to build and to identify partners and companies, startups, scientific research organization, which from one side needs such digital technology, from another side, which produce and develop such type of technologies. And for this, as I said, we created a consortium which consists of six partners. Our organization, Institute of Physics National Academy of Science, is coordinator of this consortium, and we have also partner from Poltava Polytechnic. Also, we have partner from Dnipro Polytechnic. Also, our partner Ukrainian Chamber of Commerce, cluster, and IT community. And altogether, we provide four main services. Please, the next slide. These services are divided for different types, and the main idea is to help research organization to go together with other scientific research European organization in close cooperation when they use different type of mathematics, digital solution for their researchers. And also from one side, from another side, we are looking from different startups, innovation organization, IT companies, which are interested in scientific products and which are interested in cooperation with scientists. The next slide. And as I said, we have four main services. It's a test before invest. If your organization has expertise and can provide different type of characterization, materials can create some materials which can be used from which have TRL after 6 and can be used in and can be interested for different companies. We can share information about in our database. From another side, we involve also in such a service as digital innovation, skills development and trainings. The next one is support in fundraising, in investor attracting. As I said, we can provide you services how to find partners, to create consortium, to prepare international project, how to apply to different programs, because we had quite long experience in preparation, different type of project. And now, next one, the last one, networking and access to innovation ecosystem, because it's a big network of European organization which covered more than 28 countries, and in each country they have their own network of digital innovation hub, which represented by universities, research organizations. So it's quite a big network which has very wide line of expertise. And if you're interested, you can contact with us. The last text, the last slide, you can find my contacts data. So it's general information about our activities. That's all from my side.
Okay, so one moment. The next presentation will be from me, PhD Andriy Yeremkevich. I want to share with you the information about the EAC Accelerator program, in particular the possibility from our consortium how we can help you to join this program and to have benefit from it. I will not to waste your time, jump immediately to the main part of the presentation. Here it is. You can see here the three main programs that financed by the European Innovation Council: the Pathfinder, Transition, and Accelerator. So Pathfinder is the most common and most understandable program for us as a part of the research community, because it's for basic research. The project with TRL 1, 2, and the beginning of 3. So it's the collaborative research in future emergence and technology FET. Probably most of scientific group already familiar with this type of project. It's focused on the basic research, as I told. That's why the grant preparation is really close to many another scientific grant. Here you should be more focused on your idea than on a business aspect, than globalism aspect of your idea. So it's the first program from USC. If you already win this program, or you have results from other program financing by EU funded, and your research already on the TRL 3, 4, or 5, that means that you have like lab test but not ready prototype, you can join the EAC Transition program. But today my speech is focused mainly on EAC Accelerator program. As you can see, it starts from the TRL 6, so you should have at least the created prototype. And you can join this program. Here you can see two sub-program, Accelerator Open and Accelerator Challenge. Here you can see 2023, because that's the year when we start our activity to support Ukrainian organization, research organization, and startups to join this program. But if you want to join Accelerator Challenge 2024, you should check that it's a little bit changed the focus of this area. So before you prepare your application, you should check if your application good fits to Accelerator Challenge 2025. If not, you can choose Accelerator Open. It's even easier to prepare. Yes, I will move to next slide. What it's about. If startups, SME, research institute have a high breakthrough product, service, business, and create new market and TRL 5 or 6, that means that EAC Accelerator is suitable for you. Please pay attention that on these particular words, breakthrough products that create new markets. So it should not be the improvement of already existed solution. It should be breakthrough products. If you seek for investing funding that cannot be secured in classical capital markets, so-called non-bankability, so you should in your application explain why you cannot find the usual grant form, why it's high-risky technology that cannot be funded by another fund or grant. And you should be small mid-caps, less than 500, approximately 500 participants on your startup, department, institute, and your TRL should not be higher than 9. If you want to invest component, choose, but I will explain later what it means. So we have two parts that you can apply for. First is grant component. As you can see, 2.5 million funding, but you should pay attention that it's funding rate 70%. It means that another 30% you should cover by the another sources. It may be your another grant that financing your idea, or probably finance from your organization. And also you can choose the investment component that is up to 15 millions. It's a direct investment capital, max to 25%, but it's only for the part of your work that already reach TRL 9. It's patient capital, so-called. If you do not yet reach the TRL 9, then you can see here that three type of financing. Grant only. It's if you have TRL 5, 6, 8, and you won't only receive that up to 2.5 million euro. If you want also join the investment capital, but you still have TRL 5, 6, or 8, you can choose grant first components. That means that you receive 2.5 million for creation your technology up to TRL 9, and only then you can achieve the investment component. And if you already have 9 TRL and ready to move forward, you can choose blended finance. Okay. And now let's talk about the main steps that you should go through if you choose this way for your idea. You have here 3 steps. You can prepare short proposal, full proposal, and the last step is interview with the jury. Short proposal, it's an application form that's really short, up to 10 pages. And here we have a really tricky moment that it's easy to prepare, but you should be very consistent, very sure in your idea, because you have really narrow space to explain it. But here, to move to the full proposal, you should receive only 2 goals from the 4 experts, 50% agree. And evaluation time 4 weeks, and the main part that submission is anytime. So when you are ready, you can prepare this proposal, submit it, wait for result. It's not a bad situation when you receive rejection, because you can submit it 1 more time, 2 more time, and every time you will receive good feedback from the expert who will judge your proposal. And if you succeed on the first step, short proposal, you move to the full proposal. Here we can only have 2 cutoff during the year and 2 strikes to receive approval. And you should have 3 experts that give you go. Evaluation time 5-6 weeks. And if your full proposal was successful, you move to the interview in Brussels, or for Ukraine, probably they will organize the online meeting where you will make your short pitch video up to 10 minutes in front of 4 jury members. Okay. Here I presented the forms that you should apply. You can see that it's quite easily filled form, standard, where you should complete the general information, the opportunity, what brings you to the idea, what is needed now, your solution, how to solve the problem. Then you should present the competition, impact on the market. Then you present your company, team, what funding component did you choose, any additional documents. Here should be the pitch video and explanation of your team, and submission button. So here is this component you can find here. I will not focus on this explanation. I just want to tell you that it should be like a flowing story, as we found the problem addressed for customer point of view, from customer point of view. Then we find the solution, why this is a breakthrough potential, you should explain, and why this solution should be solved now, not tomorrow, not yesterday. Market competition, here you should describe your business model, your competition, your growth, you should know that it's short form proposal, but in full form, you will should explain everything of these two, but you will have 60 pages. So now you just briefly describe the main branches of your activity, and if only you successfully go through the short proposal, then you will explain in every detail. And here, the second part is more easily to submit, but it's will be evaluated as the same way as the first part. So please pay this big attention. Describe your team, gender balance, recruitment plans, funding I already explained. Prepare the pitch deck. It's like a small presentation, up to 10 slides, not more. Everything that surpasses this 10 slide will be cut by the program. And pitch video, it's 2-3 minutes when you show exactly your team and their motivation to do this project. Here's the explanation what it should be. It's approximate how you can divide the information on these two slides. It's recommendations that work really good, but you are free to do it in that way that you can see. And video also here is described. How it will be evaluated. As it's shown, we have this circle with 3 equal parts. Excellence, risk implementation, needs for you, support, and impact. So in excellence, they will judge degree of high novelty, relevance of proposal to the objective and the objective of the challenge. All this scientific specific objective and the challenge you should check on the relevant website. I will give it on the last slide. And you should write your proposal, remember about it. Why it's the right timing, I already told it. Technological flexibility is your technology can be easily changed, applied, adapted, can evolve with accordance to the new day's challenges. And intellectual property rights, it's really it's really high evaluated. In impact, you should show the scale up potential. That means that your technology now working here, but they have planned for tomorrow and day after tomorrow. A broader impact, commercialization strategy. In short form, it's just will be enough small table, the roadmap of your plan, but in full proposal, you should be ready to explain it more deeply. And risk, it's team, milestones, level of risk, and how you will succeed with this risk, what you will do. It's the timeline that how it will be evaluated. Here to write it, it's 4 weeks. In practice is up to 8 weeks, 6 or 7 weeks, and then you will receive feedback from the commission. And if it's negative, you can start a process of re-preparing your grant. If it's positive, you can go forward to the full proposal. You will receive 2 coaches that will explain you in more detail how to adapt your scientific idea to the business opportunity, to the business needed now. He should be. Here you can find the references. They are not clickable now, but if you will need it, feel free to contact me and I will send this presentation to you. Also, this link will be clickable. Also, in the frame of this presentation, I should explain how we can support you during all the steps. And the answer is, in any way, if you just register your organization of funding portal and try to receive big number, you can contact us. We will explain how to do it. If you just preparing the short form and don't know how to move, we will send you all necessary documents, our training videos. We will explain you how to move step by step on what you should focus on, what is not so important on the short form. If you already prepared the short form, we can send to us the document and we will check it. We will find the weaknesses. We can send you tips and tips how to improve it. And if you already win the shortfall, we also can help you to find for you a relevant coach who can improve your form for the next step. And if you already even win the full form and preparing for interview, we can contact you with Ukrainian participants who already was in that step and who give you in-depth analysis how to be well prepared, what to expect. So that's the main information that I want to share with you for today. If you will be interested in this program, now in Ukraine still work in our group who can support you, feel free to contact us. Many thanks for your attention, and I will give a floor for my colleagues Alexander Beduk, who will explain how to work with Enterprise Europe Network in Ukraine.
Yes, no, not first, not first. Maybe the set, maybe the set. Okay. So, good evening, everyone. Let me introduce some basic information about AM. So, for short, very short, that's my speech. So, first slide, please. Okay, so what is today? The next slide, please. The next. Okay. Today's aim is a world language support network for small and medium-sized enterprise. It helps companies innovate, enter new international markets, and establish business connection. This information not only about SME, but about research group of university, for example, with their innovation, with their startup, and so on. So we help SME firstly, and second, not second, but together, we help startups, we help innovation, we help scientific group of university to internationalize their research. So some information about the yen is a key instrument of EU strategy to boost growth and jobs. Launched in February 2008, and funding from European Commission more than several millions euros per year. The next. Here's the main figures that demonstrate how big is is. More than 60 locations performed. More than 3,000 local experts from about 30 countries, not only Europe, but all over the world. The next. This is example of our partner, which take part in UNWORKS. Next. And how we help. We combined international business expertise with local knowledge to take your innovation into new markets. The next. No, here you can see the slide. So next maybe it's not. Oh yes, it's the same slide, but more information about all of this. One. So first, partnership, international partnership. We have the biggest, maybe the biggest database of business and technology office and request and R&D request. So this is partnership.us. We help in organization many brokerage event company missions, making events, which help our client to meet one another in the international conference. In hybrid, mainly on this conference in hybrid, so we can use on-site or online variant of participation in this events. Secondary, advisory. Our expert can advise the best market opportunities, provide particular advice, target market, market intelligence, so on. And the third innovation. Our expert help SMEs and of course research group from university to design their innovation. The next slide. And how it works. And look, business database contains 10,000 of different company profiles, different companies' office, different companies' request. So when users request, we can switch the partner which you many, I repeat, we organize many different matchmaking, brokerage, event company mission. And the main purpose of this events was the meeting, direct meeting between participants organization, SME of this events. The next one. Oh, yes. Here you can see the real success stories. Now here you see how the Swedish SME has agreed with Latvian and Danish partner. And another one, the next slide. You can see our United Kingdom SME contact with Czech power partners and help with success results. This is the next success story. The next story through the advisory report. The next one. Oh yes, Polish SME will be the task SME which have international support in general. With help of course, the next one. Innovation. Our expert help and as I say, practical, personal advice and international protection, their ideas. So The next slide. Maybe the success story. Yes, the success story. So for this slide, we can see success story. One Spanish research center work with Italian startup, and as a result, develop a green technology for using for seawater, using solar energy. The next. Then another success story when Greek company grows their capital in 20 times and their workforce in 4 times. The next one. It's real success story, not from Ukraine, because of course we have the success story from Ukraine too. By the way, as I know, we now have technical report about our work about 2 years. We have about, if I'm doing mistake, about 300 success story from Ukraine. By the way, from Russian University, which I represent, we have about maybe 8 success story for 2 years. And all the stories, most of the story about access to funding from Europe, something or get money for visit another country and so on. So it's a real success story when our client have money for grow the from the university for 2 years, about 30, or about 80 success stories. So the next one. It's several how the SMEs illustrated of what this, and you can see these figures. Next one. This is the same how in Europe people grows through the SME. And next one. Yes, it's the same figures. You can see these figures in my presentation if you want. And the next one. Okay, this is the case sector in which you walk through. You walk. By the way, I am member, for example, the health sector, and my colleague member of the sustainability sector, nano sector, and so on. So our contact point present maybe 7 or more. I don't know. I'm not sure. Sector group of life. So we can contact with experts from many countries. First of all, European country in this sector. For me, I work in sector. Next one. And this is feedback from different sites, from media, and next slide. Next slide. From the media, many feedback about how success even works. And next one. Yes, this is several slides about the feedbacks of SME and media about next. Yes, and how we can help. If you're interested, please go to the general site platform and find the contact point of Ukraine. Through this contact point, you can see, for example, Institute of Physics, University Center, and so on. Contact us and we help us. Of course, help us. Thank you for your attention.
Thank you. Dear college, it was the last speaker and the last special session for today.
I wanted only to add, because we received quite a lot of requests for traveling, yes, for excursion. And now we started to looking for different opportunities. And one of them, it's short travel. Okay, I will go to another side. It's more information for on-site participants. If you wanted to take part in excursion, please go to the reception and you will receive more detailed information about journey to mountains. Yes, and we plan to organize it tomorrow after the conference at 5 p.m. But it will be cost additional cost, and we will try to find company which organize us this excursion to mountains. So if you're on site and if you are interested to take part in this excursion, please go to Oksana on reception and she will provide you more details about it. It's short information, but now we thank you a lot for your time, that you were with us whole day. And now I wish you very nice evening in mountains. And thank you very much for our participants online. I hope that this day was interesting for you. And we are waiting for you tomorrow because our conference continues. Goodbye.